Hello and welcome. I'm glad you're here. Tonight we're going to wander through facts about our strange and beautiful universe. Not the alarming kind of facts that jolt you awake, but the gentle kind. The ones that make you feel connected to something larger, something older, something quietly magnificent. Facts about your body, about light and time, about creatures in the depths and particles too small to see. Before we begin, I'd love to know where you're watching from tonight. And how was your day? Drop a comment below. I always enjoy reading your comments. If you enjoy falling asleep to these videos, please consider liking and subscribing. It helps more people find their way here. So, adjust your pillow, let your breathing slow, feel the weight of your body against the mattress. Now let's begin. Your body contains about 37.2 trillion cells, but you're carrying around even more bacterial cells, roughly 39 trillion of them. You are not one thing, you are many things. Right now, as you lie there listening, your body is host to roughly 37.2 trillion cells that are distinctly, undeniably you. Each one carries your DNA, your genetic signature, the biological instruction manual that makes you uniquely yourself. These cells form your skin, your organs, your bones, the very neurons firing in your brain as you process these words. But here's the thing that shifts the ground beneath what we think we know about identity. You're carrying around even more cells that aren't you at all. About 39 trillion bacterial cells, to be precise. They live on your skin, in your gut, in your mouth. Tiny organisms with their own genetic code, their own evolutionary history, their own microscopic lives, playing out in the ecosystem of your body. Think about that for a moment. You are technically more bacteria than human, at least by cell count. It's a strange sort of democracy happening inside you right now. The bacteria outnumber your own cells, yet somehow you still feel like yourself. You still think your thoughts, make your decisions, exist as a coherent being despite being, in essence, a walking, breathing cooperative. Now, before this starts to feel unsettling, consider the weight of things. All those bacterial cells combined weigh only about 200 grams, less than half a pound. They're so small, so impossibly tiny, that even though they outnumber your cells, they barely register on a scale. It's a bit like saying there are more grains of sand on a beach than there are pebbles, yet the pebbles still make up most of the beach's mass. These bacteria aren't invaders, not really. Most of them are partners. They help you digest food, synthesize vitamins, train your immune system, even influence your mood through the gut-brain connection that scientists are only beginning to understand. In a very real sense, you couldn't survive without them. They've been with humans so long that we've co-evolved, shaped each other across millions of years. So when you think about who you are, maybe the answer is bigger than you imagined. You are a universe unto yourself, a collection of trillions of living things working in concert, each playing their part in the symphony of your existence. And somehow, impossibly, all of it feels like you. Glass is not actually a slow-moving liquid, despite the popular myth about old window panes being thicker at the bottom. There's a story that gets told about glass, one that feels almost magical in its strangeness. You've probably heard it, that glass is actually a liquid, just an incredibly slow-moving one. That the reason old cathedral windows are thicker at the bottom than the top is because the glass has been flowing downward over centuries, pulled by gravity in an imperceptibly slow ooze toward the earth. It's a beautiful idea, really. The notion that something so solid and reliable could secretly be in motion, that time itself could be made visible in the gradual sagging of ancient windows. It makes you look at glass differently, not as a frozen thing, but as something patient and alive in its own geological way. But here's the truth, and it's somehow just as strange. Glass isn't a slow-moving liquid at all. It's what scientists call an amorphous solid. Let me explain what that means, because the reality is more interesting than the myth. Most solids are crystalline. Their atoms are arranged in neat, repeating patterns, like a perfectly organized library, where every book has its place and everything follows a grid. When water freezes into ice, its molecules lock into these regular crystal structures. Same with metals, salt, diamonds, most of what we think of as solid. Glass is different. When glass cools from its molten state, it solidifies so quickly that its molecules don't have time to organize into those neat crystal patterns. They freeze in place wherever they happen to be, a random, chaotic arrangement locked into permanence. It's like a library where someone dropped all the books in a panic, and they solidified before anyone could put them back on the shelves. This is why glass is called amorphous, meaning without form or without structure. But make no mistake, it is solid, truly, genuinely solid. The viscosity of glass at room temperature is so astronomically high that it would take longer than the age of the universe, billions upon billions of years, for it to flow in any measurable way. It's not flowing, it's not moving. Those old windows are thicker at the bottom because of how they were made, not because the glass has been slowly oozing downward for centuries. Medieval glassmakers created uneven panes, and installers often put the thicker edge at the bottom for stability. But maybe there's something beautiful in that too. We wanted glass to be secretly liquid because it says something about the nature of stillness itself, that nothing is truly frozen, that everything moves eventually, even if we can't see it. And in a way, that's still true. Just not with glass, not in the way we thought. Bananas are naturally radioactive because they contain potassium-40, a radioactive isotope. Let's talk about something sitting in your kitchen right now, something ordinary and yellow and curved, something that is technically radioactive: bananas. Every banana you've ever eaten has contained a small amount of potassium-40, a naturally occurring radioactive isotope. It's in there along with all the regular potassium, the kind your body needs for muscle function, nerve signals, maintaining fluid balance. But mixed in with that ordinary potassium, about 0.0117% of it is this radioactive version, this variant that's unstable, that decays slowly over time, releasing tiny amounts of radiation as it transforms into other elements. Now, before you start worrying about your breakfast, let me put this in perspective. The amount of radiation in a single banana is minuscule. Scientists even have a term for it: the banana equivalent dose, or BEAD. It's used as a playful way to help people understand radiation exposure by comparing it to something familiar and harmless. One banana gives you about 0.1 microsieverts of radiation, a measurement so small it barely registers. To put that in context, you're exposed to more radiation on a cross-country flight due to cosmic rays at high altitude. You get more radiation from sleeping next to another person through the night because their body also contains radioactive potassium. Living in a brick house exposes you to more radiation than eating a banana, because bricks contain trace amounts of uranium. In fact, you'd need to eat about 10 million bananas at once for the radiation to be fatal. And at that point, the radiation would be the least of your problems. The sheer amount of potassium would cause fatal hyperkalemia long before the radiation did anything, and your stomach would probably rupture from the volume of banana. But here's what makes this fact beautiful rather than frightening. It reminds us that radiation isn't some alien, unnatural threat from nuclear power plants and sci-fi movies. It's everywhere. It's been everywhere since the beginning of the universe. The very atoms that make up your body contain radioactive isotopes. Carbon-14, which scientists use for dating ancient artifacts, is inside you right now, created by cosmic rays hitting nitrogen in the atmosphere. You are slightly radioactive, sitting there in the dark. The person you love is slightly radioactive. The banana bread cooling on the counter is slightly radioactive, and it's all completely, utterly fine. The universe hums with this low background noise of particles transforming, decaying, releasing energy in amounts too small to harm, but large enough to measure. It's one of those facts that seems like it should be alarming, but somehow becomes comforting instead. A reminder that we're made of the same stuff as everything else, participating in the same ancient atomic processes that have been unfolding since stars first formed. So the next time you peel a banana, maybe think of it as a small yellow reminder. You are part of something vast and ongoing, something that's been happening since long before you arrived and will continue long after you're gone. Even your breakfast is connected to the stars. The Eiffel Tower can grow more than 6 inches taller during summer due to thermal expansion of its iron structure. There's something quietly alive about the Eiffel Tower, though it's made entirely of iron. When summer arrives in Paris, when the sun climbs high and the metal heats in the long afternoon light, something happens that most visitors never notice. The tower grows, not metaphorically, not in fame or stature, but actually physically grows, stretching upward as much as 6 inches taller than it stands in winter. This is thermal expansion at work, one of those fundamental properties of matter that we rarely think about until it shows up in dramatic ways. Heat makes things expand. It's happening everywhere, all the time. The molecules in solid materials, metal, concrete, wood, are always vibrating, always in motion at the microscopic level. When you add heat, you add energy, and those molecules vibrate faster, bouncing around more vigorously, taking up more space. The Eiffel Tower is made of about 7,300 tons of iron. Not steel, but puddled iron, a material chosen by Gustave Eiffel for its strength and workability. Iron expands more than some other materials when heated, and with 7,300 tons of it standing 984 feet tall, that expansion becomes visible, measurable, significant. In summer, when temperatures can reach 40 degrees Celsius, over 100 Fahrenheit, the side of the tower facing the sun heats up more than the shaded side. This uneven heating causes the tower not just to grow taller, but to lean slightly away from the sun, bending, in a sense, toward the shade. It can tilt as much as 7 inches from its base, a giant structure moving like a plant following light, except in reverse. Then winter comes. The metal cools. The molecules slow their vibrations. The tower contracts, shrinking back down, pulling itself inward. It's breathing in a way, expanding and contracting with the seasons, year after year, since it was completed in 1889. This happens to all structures, of course. Bridges have expansion joints for this very reason. Railroad tracks have small gaps between segments to allow for expansion, otherwise they'd buckle in summer heat. The concrete of highways swells in warmth and contracts in cold, which is why roads develop cracks and potholes over time. But there's something particularly poetic about the Eiffel Tower doing this, perhaps because it's a symbol, an icon, something we think of as permanent and unchanging. We imagine it standing there above Paris, fixed and eternal, the same today as it was 100 years ago. But it's not fixed at all. It's constantly moving, shifting, responding to the environment around it. Even monuments breathe. It reminds you that nothing is truly solid in the way we imagine. Everything is negotiating with temperature, with pressure, with time. Even iron, cold, strong, industrial iron, is subject to the same basic physics as everything else. It expands when warm, contracts when cool, moves in ways too slow for us to perceive in the moment, but absolutely real over the course of a day, a season, a lifetime. Right now, somewhere, something in your house is expanding or contracting. The metal frame of your bed, the wood of your floor, the glass in your windows. All of it moving, shifting by tiny amounts you'll never notice, but that add up over time. The world is more fluid than it appears, more responsive, more alive in its own material way. Octopuses have 3 hearts. 2 pump blood to the gills, while the third pumps it to the rest of the body. Not metaphorically, not as some poetic description of love or courage, but literally. 3 separate organs pumping in your body, each with its own rhythm, its own job, all working together to keep you alive. This is the reality for the octopus, a creature so strange it sometimes seems more alien than earthly. While we make do with our single heart, working tirelessly, pumping about 100,000 times a day to push blood through our bodies, the octopus takes a different approach. 3 hearts, each specialized, each essential. 2 of these hearts, called branchial hearts, are dedicated to the gills. The octopus breathes through gills like a fish, extracting oxygen from water, and these 2 hearts sit near the gills, pumping deoxygenated blood through gill tissue where it picks up oxygen. It's a local system, a targeted approach. Why make one heart work harder when you can have specialized hearts right where the work needs to happen? The third heart, the systemic heart, pumps that newly oxygenated blood to the rest of the body, the muscles, the organs, that surprisingly large and complex brain. This is the central heart, the one doing what our single heart does, but with help. Here's where it gets even stranger. When an octopus swims, the systemic heart stops beating. Yes, stops. Completely. This is why octopuses prefer to crawl along the seafloor rather than swim through open water. Swimming is exhausting for them because their main heart literally shuts down while they're doing it. They have to rely on those 2 gill hearts alone, which isn't enough to sustain vigorous activity. So they crawl, 8 arms, pulling them along rocks and sand, staying low, conserving energy, letting all 3 hearts work in harmony. The blood itself is strange too. Ours is red because it uses iron-based hemoglobin to carry oxygen. Octopus blood uses copper-based hemocyanin instead, which makes their blood blue when oxygenated. Blue blood might sound like fantasy or aristocracy, but for the octopus, it's chemistry. Copper binds oxygen differently than iron, turns blue instead of red, and actually works more efficiently in cold, low oxygen environments where many octopuses live. So picture it: an octopus crawling along the ocean floor in near darkness. 3 hearts pumping blue blood through a body that can change color and texture in milliseconds. A brain that can solve puzzles and unscrew jars. Eyes that evolved completely independently from ours, but ended up remarkably similar. A creature so neurologically complex that 2/3 of its neurons are in its arms, giving each limb a kind of independent intelligence. They're solitary creatures, mostly. They don't form societies, don't pass knowledge down through generations the way dolphins or primates do. Each octopus figures out the world alone, with 3 hearts pumping and a brain working through problems no one taught it to solve. There's something both lonely and magnificent in that. A creature with 3 hearts, swimming through dark water with no companions, solving the puzzle of existence one problem at a time, and then dying shortly after reproducing. Most species live only 1 to 2 years. All that intelligence, all that complexity for such a brief time. Maybe that's why they need 3 hearts. Not for efficiency or evolution, but because the work of being alive, of moving through water, of hunting, of simply existing in all that strangeness, requires that much pumping, that much effort, that much coordinated rhythm just to make it through. A single teaspoon of honey represents the entire life's work of 12 bees. There's a jar of honey somewhere in your kitchen, probably. Maybe it's been there for months, maybe years. Honey doesn't spoil. It's one of those rare foods that lasts essentially forever, crystallizing perhaps, but never rotting, never going bad. Archaeologists have found honey in ancient Egyptian tombs, 3,000 years old, still perfectly edible. But let's talk about what it takes to make it. A single teaspoon of honey, the amount you might drizzle into your tea without thinking, or spread on a piece of toast, represents the entire life's work of 12 bees, 12 individual lives, each one lasting only about 6 weeks during the busy summer months, all of their labor combined into that one small measure. Each worker bee, during her lifetime, produces only about 1/12 of a teaspoon of honey. Think about that. Less than a teaspoon. A bee works every day of her adult life, flying out to flowers, gathering nectar, flying back, processing it, storing it, fanning her wings to evaporate excess water. And all of that effort, all those thousands of flower visits, results in an amount of honey you could lose in the bottom of a cup. To make 1 pound of honey, bees must visit approximately 2 million flowers. They fly the equivalent of 3 times around the world. A single colony might contain 60,000 bees working simultaneously, each one making hundreds of trips, each trip visiting perhaps 50 to 100 flowers, bringing back nectar drop by drop, storing it in hexagonal wax cells, transforming it through enzymatic processes we still don't fully understand. The nectar itself is mostly water, 70% to 80%, so the bees must evaporate most of it to concentrate it into honey. They do this by spreading the nectar in thin layers across the comb and then fanning it with their wings, creating air currents that speed evaporation. Thousands of bees fanning in coordination, essentially air conditioning the hive, reducing that watery nectar down to about 18% water content. Only then do they seal it with a wax cap, storing it for winter. And here's the thing that shifts your perspective. The The bees aren't making honey for us. They're making it for themselves. Honey is their winter food supply, their stored energy for when flowers aren't blooming and foraging isn't possible. It's survival food, concentrated calories that will keep the colony alive through cold months when nothing grows. When we take honey, we're taking their reserve rations. Beekeepers, of course, leave enough for the colony to survive, or supplement with sugar water, but the fundamental transaction remains the same. We're harvesting the product of countless small labors, millions of individual decisions by individual bees to visit one more flower, make one more trip, work one more day. There's a kind of accumulation at work here that mirrors something larger about existence. No single bee makes enough honey to matter. No single trip to a flower would be worth the energy expenditure if that's all there was. But millions of small efforts, coordinated across thousands of individuals, create abundance. The colony survives not through any one bee's heroism, but through the aggregate of all their small, persistent labors. Maybe that's comforting somehow. Maybe it suggests that small efforts matter, even when they feel insufficient in the moment. That the work you do, even when it feels like drops in a bucket, might be part of something larger, some accumulation you can't see yet, but that's happening nonetheless. Or maybe it just makes that teaspoon of honey in your tea feel a little more precious. 12 lives, 2 million flowers, 3 trips around the world, all of it concentrated into something sweet and golden that dissolves on your tongue in seconds. The next time you taste honey, maybe let it sit in your mouth a moment longer. Maybe think about the bee that made it, flying through summer air, navigating by polarized light and the position of the sun, returning to a hive humming with tens of thousands of sisters, all working toward the same goal without ever being told what to do, without supervisors or schedules or overtime pay. Just instinct and effort, flowers and flight, repeated until the work is done or the worker dies, whichever comes first. And somehow, impossibly, it's enough. The honey gets made. The colony survives. Life continues, all from efforts so small you could measure them in fractions of teaspoons. The human brain uses about 20% of the body's energy, despite making up only 2% of its mass. Your brain is expensive, not in money, though the health care around it can be, but in terms of pure energy. Right now, as you lie there in the dark, your brain is consuming roughly 20% of all the energy your body is producing. 1/5 of your total caloric burn, despite the fact that your brain accounts for only about 2% of your body weight. Think about that proportion for a moment. If you weigh 150 pounds, your brain weighs about 3 pounds. 3 pounds of tissue demanding 20% of your fuel. It's like having a tiny, incredibly demanding organ that acts like it owns the place, because in many ways it does. The brain is made up of approximately 86 billion neurons, each one a living cell that maintains an electrical charge, ready to fire signals at any moment. And they do fire, constantly, in patterns too complex to fully map. Every thought, every sensation, every unconscious regulation of breathing and heartbeat requires neurons to communicate with each other. And that communication costs energy. It takes energy to maintain the electrical gradients across neuron membranes, the difference in charge between inside and outside the cell that allows signals to propagate. It takes energy to produce neurotransmitters, the chemical messengers that cross the gaps between neurons. It takes energy to recycle those neurotransmitters afterward, to maintain cell structures, to repair damage, to build new connections as you learn and remember. Your brain never truly rests, even when you're asleep, especially when you're asleep, it's working. During REM sleep, when you dream, brain activity actually increases in many regions. The brain is processing the day's experiences, consolidating memories, making connections between ideas, doing maintenance work that can only happen when you're not consciously thinking. This enormous energy demand is why complex thinking can make you genuinely, physically tired. It's not just mental fatigue, it's real caloric expenditure. Studies have shown that intense cognitive work, like solving difficult math problems or learning complex new skills, can measurably increase the brain's glucose consumption. Your brain is literally burning fuel to think. This is also why glucose, blood sugar, is so critical to brain function. Unlike muscles, which can burn fat when glucose runs low, your brain depends almost entirely on glucose for energy. When blood sugar drops, cognitive function drops with it. You get foggy, irritable, struggle to concentrate. Your brain is essentially running out of gas. Evolution made this trade-off deliberately, in a sense. Not consciously, but through the long process of natural selection. Our ancestors who could think better, plan better, solve problems better, survived more often, and had more offspring. So brains got larger and more complex over millions of years, even though they're metabolically expensive. Even though carrying around this energy-hungry organ means you need to eat more, forage more, take more risks to get enough calories. But the payoff was worth it. Intelligence allowed humans to adapt to nearly every environment on Earth, to create tools and language and culture, to build civilizations. All of that came from this 3-pound organ that costs 20% of your daily energy budget to run. Right now, in the darkness, your brain is still running, still consuming energy, still firing neurons, still processing. Even as you drift towards sleep, even as consciousness begins to fade, the brain continues its work, regulating your breathing, maintaining your body temperature, cycling through sleep stages, dreaming dreams you may or may not remember. It's the most complex object in the known universe, as far as we can tell. More complex than any galaxy, any star, any quantum system we've discovered. 86 billion neurons, each connected to thousands of others, creating trillions of connections, patterns of activity so intricate that we're still just beginning to understand them. And it's running on about the same power as a 20-watt light bulb. All that complexity, all that processing, all your thoughts and memories and sensations and dreams, powered by less electricity than it takes to light a dim reading lamp. Somehow, your brain takes that small trickle of energy and creates everything you experience. The warmth of blankets, the memory of someone's laugh, the solution to a problem, the meaning of these words, the feeling of sleepiness spreading through your body like warm water. 20% of your energy, 2% of your mass, 100% of your experience. Maybe that's worth the expense. Water can boil and freeze at the same time at exactly 0.01 degrees C and specific pressure conditions, a point called the triple point. There's a moment, precise and rare, where water forgets what it's supposed to be. Not forgets exactly, water doesn't have memory, but reaches a state so perfectly balanced that it becomes all of its possibilities at once. This happens at what physicists call the triple point, exactly 0.01 degrees Celsius, and a pressure of 611.657 pascals. At this exact temperature and pressure, water exists simultaneously as solid ice, liquid water, and gaseous vapor, all in equilibrium, all at once. It sounds impossible, doesn't it? Water should be one thing or another, frozen or melted or evaporated, solid or liquid or gas. We experience these states as distinct, separate, like different rooms in a house that you move between but never occupy simultaneously. But at the triple point, the walls between those rooms dissolve. Imagine a container of water at this precise condition. You'd see ice floating in liquid water, and above the liquid, water vapor. But these aren't just three separate things happening to exist near each other. They're in equilibrium, meaning molecules are constantly moving between states. Ice molecules gain energy and melt into liquid. Liquid molecules evaporate into vapor. Vapor molecules condense into liquid. Liquid molecules freeze into ice. All of it happening at equal rates, a perfect dynamic balance where the amount of solid, liquid, and gas remains constant, even though individual molecules are continuously changing states. It's like a spinning coin that never lands, or rather, a coin that lands on heads, tails, and its edge all at the same time. This triple point isn't unique to water. Every substance has one, a specific temperature and pressure where all three states can coexist. For water, it happens to occur at conditions we can actually observe in a lab without too much difficulty. For other substances, it might require extreme cold or immense pressure, conditions we can barely create. Scientists use the triple point of water as a fundamental reference in defining temperature scales. The Kelvin scale, which scientists use for precise measurements, is defined such that the triple point of water is exactly 273.16 Kelvin. It's a fixed point, a constant of nature, something reproducible anywhere in the universe where water exists. There's something philosophically satisfying about the triple point, beyond just the physics. It suggests that categories we think of as absolute, solid, liquid, gas, are actually just stable points along a spectrum. That matter is more fluid than we imagine, more willing to be multiple things at once given the right conditions. We spend so much time thinking in binaries, in either or frameworks. Something is this or that. You're awake or asleep. Water is frozen or melted. But nature doesn't always respect those categories. At the right moment, under the right conditions, things can be both or all, or something in between. Maybe there's a metaphor there for human experience too. Maybe we're always at our own triple points, simultaneously solid in some ways, fluid in others, evaporating into possibility in still others. Not fragmented exactly, but existing in multiple states at once, in equilibrium, constantly shifting between versions of ourselves, while somehow remaining the same substance underneath. Or maybe it's just water doing something strange and beautiful because the physics happen to align just so. Either way, there's something quietly wonderful about knowing that somewhere, under controlled conditions, water can forget to choose, that it can be ice and liquid and vapor all at once, perfectly balanced, neither fully any of them and completely all of them, existing in a state of permanent in-betweenness that seems impossible but is absolutely, measurably real. The universe allows for this, encourages it even. At exactly the right pressure and exactly the right temperature, matter gets to be undecided, to hold all possibilities open simultaneously, to exist in a state of perfect ambiguity where the usual rules about identity and state simply don't apply. And then you change the pressure by a tiny amount, or the temperature by a fraction of a degree, and the balance tips. Water chooses. It becomes one thing, ice or liquid or vapor, and the moment passes. The triple point collapses back into ordinary physics, ordinary states, ordinary categories. But for that one precise instant, anything was possible. Everything was true at once. Maybe that's enough. The smell of freshly cut grass is actually a plant distress signal, a chemical cry for help. That smell you love, the one that means summer and childhood and lazy afternoons, is a scream. Not metaphorically, chemically, biologically, it's a distress signal, a cry for help broadcast in molecules instead of sound. When you mow the lawn, when you walk through freshly cut grass and breathe in that clean, green smell, what you're actually smelling is a complex cocktail of chemical compounds that grass releases when it's damaged. Scientists call them green leaf volatiles, or GLVs, and they're the plant equivalent of a 911 call. The main compound is called cis-3-hexanol, though there are others, cis-3-hexanol, hexanol, various esters and alcohols, all released when the grass cells rupture. These chemicals serve multiple purposes, and none of them are to make your Sunday afternoon more pleasant. First, they're a warning to other grass plants nearby. Yes, plants communicate. They don't have nervous systems or brains, but they can sense their environment and respond to threats. When grass releases these GLVs, neighboring plants detect them and begin producing defensive compounds, toxins that make them less appetizing to insects, thicker cell walls that are harder to chew through, various chemical defenses that take time to manufacture. It's a community alarm system. One plant gets attacked, cuts, or damaged, and it essentially shouts to its neighbors, "Danger! Prepare yourselves." Second, these chemicals attract predators. Not predators of the grass, predators of whatever is eating the grass. Many insects that feed on plants are themselves food for wasps, beetles, and other predatory insects. When grass releases GLVs, it's sending out a chemical beacon that says, "Something is eating me over here," attracting the natural enemies of whatever is causing the damage. It's a brilliantly indirect defense. The grass can't fight back directly. It can't run or bite or sting. But it can call in reinforcements, chemical signals drifting on the air, summoning tiny assassins to deal with the threat. Of course, when you mow the lawn, there's no caterpillar or grasshopper to fight off. The grass is releasing these signals in response to massive mechanical damage from whirling blades, calling for help that won't come, warning neighbors who will also be cut in the next pass of the mower. It's a futile distress call, chemically speaking, though the grass has no way of knowing that. And we've learned to love this smell. We've associated it with leisure and summer and the outdoors. We've made air fresheners that smell like cut grass, created perfumes with green, fresh notes, described the scent as clean and natural and good. There's something darkly ironic about that, maybe. Or perhaps it just shows how disconnected we are from the chemical conversations happening all around us. The silent language of plants that we can smell but not speak, that we interpret as pleasant while the plants are literally screaming. Other plants do this too, of course. That sharp herbal smell when you crush basil or mint? chemical defense compounds released when cells are damaged, the smell of a tomato plant when you brush against it, warning signals. Even that earthy smell after rain, petrichor, one of the most beloved scents in the world, comes partly from plant oils that accumulated during dry periods, released when rain breaks the soil crust. It's all communication, all chemical information flowing between organisms we usually ignore. Plants are not passive. They're not just green decorations sitting silently in the background. They're sensing, responding, defending, warning, calling for backup. They're doing all of this without brains or nervous systems, using nothing but chemistry and evolution. Strategies refined over hundreds of millions of years. So the next time you smell cut grass, maybe think of it differently. Not as a pleasant aroma, but as a conversation you're overhearing. A distress call broadcast on frequencies of scent instead of sound. A chemical cry echoing across a lawn, plant to plant, warning of danger that's already passed, calling for help that will never arrive, in a language we can perceive but never truly understand. And then, if you want, go ahead and enjoy the smell anyway. The grass doesn't know the difference, and there's something human about finding beauty in unexpected places, even in the chemical screams of wounded plants, drifting on summer air, smelling like childhood and home. Your stomach gets a new lining every 3 to 4 days to prevent it from digesting itself. Your body is trying to eat you. That's not quite right, but it's close enough to be unsettling. Your stomach produces hydrochloric acid, strong enough to dissolve metal, about pH 1.5 to 3.5, similar to battery acid. This acid is necessary. It breaks down food, kills bacteria and pathogens in what you eat, activates digestive enzymes. Without it, you'd be vulnerable to infection and unable to properly digest protein. But here's the problem. Your stomach is made of protein. The same acid that breaks down the steak you had for dinner would theoretically break down the stomach lining just as easily. You are, in essence, a bag of meat filled with meat-dissolving acid. So why doesn't your stomach digest itself? It does, actually. Or it would, constantly. Except for an elegant solution evolution arrived at over millions of years. The stomach lining is disposable, temporary, designed to be destroyed and replaced on a continuous cycle. Every 3 to 4 days, your stomach grows an entirely new lining. The cells that make up the inner surface of your stomach, the mucosa, are replaced completely, shed into the acid bath, and dissolved along with your dinner, while new cells grow underneath to take their place. It's a continuous process, cells dying and regenerating. A slow-motion sacrifice happening right now, as you lie there in the dark. These stomach lining cells are among the fastest regenerating in your body for exactly this reason. They're in a hostile environment under constant chemical assault, and they can only survive a few days before the damage becomes too great. So they die, and new ones grow, and the cycle continues. An endless rotation of cellular guards standing watch against acid they can't truly withstand, only delay. But cells alone wouldn't be enough. Your stomach also produces mucus, thick protective mucus that coats the lining, creating a barrier between the acid and the living cells beneath. This mucus is alkaline, helping to neutralize acid that gets too close to the stomach wall. It's about 1 millimeter thick, which doesn't sound like much. But at the cellular scale, it's a substantial fortress. The mucus itself is also constantly replaced. Your stomach produces about 1 liter of the stuff every day, roughly 1 quart of protective slime, secreted continuously, forming a renewable shield against the acid it's containing. And beneath the mucus layer, the cells are tightly packed, forming what's called a tight junction. Cells link together so closely that acid can't seep between them. It's like overlapping roof tiles, each one protecting the one below. No gaps for acid to exploit. Still, sometimes the system fails. Sometimes the acid breaks through, whether because of too much acid production, too little mucus, damaged cells, infection with H. pylori bacteria that weakens the lining, or a dozen other reasons. When this happens, you get an ulcer, a hole in the lining where the stomach has actually started to digest itself, creating a painful wound that can bleed, that can, in severe cases, perforate completely through the stomach wall. It's a reminder that your body is not a finished object, but an ongoing process, a constant battle between destruction and repair, acid and mucus, death and regeneration. You're not a static thing, but a dynamic system in precarious balance, cells dying and being born every second, tissues breaking down and building back up, your entire body in constant flux. About 330 billion cells die in your body every day. Most of them are replaced. Your skin regenerates entirely every 2 to 4 weeks. Your red blood cells last about 120 days before being recycled. Your liver can regenerate completely, even if 70% of it is removed. You are always becoming new, always replacing yourself. A ship of Theseus made of meat and chemistry, continuously reconstructed from the inside out. But the stomach lining is special because of how fast it happens, how necessary it is, how dramatic the consequence if it fails. Every 3 to 4 days, a complete replacement. New cells, new mucus, new protection against the acid you need to survive, but that would kill you if given the chance. It's happening right now. While you lie there, cells are dying in your stomach lining. New ones are growing beneath them. Mucus is being secreted. Acid is being produced. The whole precarious balance is maintained without you thinking about it, without you doing anything at all. Your body knows how to protect you from itself, knows how to walk the line between the acid you need and the damage it causes, knows when to grow, when to shed, when to replace. All you have to do is lie there and breathe. The rest happens on its own, in the dark, beneath your awareness, cells sacrificing themselves in an endless rotation so that you can wake up tomorrow and eat breakfast and never think about the small war being waged inside you every moment of every day. It's working right now, has been working your entire life, will keep working until it doesn't, until something breaks, until the balance fails. But for now, in this moment, it's holding. The lining is intact. The acid is contained. You are safe inside your own body, protected from yourself by layers of cells that die so you can live. Maybe that's all any of us can do. Build barriers, replace what breaks. Hope the balance holds a little longer. And somehow, impossibly, it usually does. A photon takes about 170,000 years to travel from the sun's core to its surface, but only 8 minutes to reach Earth. Light is fast. Everyone knows this. It's the fastest thing in the universe, the cosmic speed limit, 186,282 miles per second. Nothing with mass can ever reach this speed, and nothing can exceed it. Light itself exists at this boundary, always moving at exactly this velocity through vacuum, never faster, never slower. So when we say it takes 8 minutes for sunlight to reach Earth, That makes sense. The sun is about 93 million miles away. Light travels at 186,282 miles per second. Do the math, and you get roughly 8 minutes and 20 seconds. Simple geometry, simple physics. But here's what shifts your understanding of simplicity. That same photon, that particle of light that crosses 93 million miles in 8 minutes, took about 170,000 years just to escape from the center of the sun where it was created. 170,000 years. Think about that. Modern humans have only existed for about 300,000 years. The light reaching your eyes right now from the sun began its journey from the sun's core before the last ice age, before agriculture, before written language, before any of what we call civilization existed. Why does it take so long? The sun's core is dense, incomprehensibly dense, about 150 times denser than water, a plasma of hydrogen nuclei and electrons packed so tightly that matter behaves in ways we can barely reproduce in laboratories. In this environment, a photon can't travel in a straight line. It can't travel anywhere without immediately colliding with something. Nuclear fusion in the sun's core produces photons, gamma rays initially, incredibly high-energy light. But these photons don't zip straight out to the surface. They slam into electrons, into hydrogen nuclei, into other particles. They get absorbed and re-emitted, scattered in random directions, bouncing around like a pinball in the densest arcade machine imaginable. This process is called a random walk. Each photon travels a tiny distance, maybe a centimeter, maybe less, before hitting something and being absorbed. Then a new photon is emitted in a random direction, travels another tiny distance, collides again. Over and over and over, billions upon billions of interactions, each one scattering the photon in an unpredictable direction. It's not a straight path from core to surface. It's a drunken stumble, a three-dimensional maze with no solution, just random chance determining each turn. The photon might move outward, or it might move back toward the core. It might travel sideways, diagonal, any direction at all. Pure randomness, accumulated across incomprehensible numbers of interactions. The math of random walks tells us that the average time for a photon to diffuse from the sun's core to its surface is somewhere between 10,000 and 170,000 years, depending on which model you use, which assumptions you make. The uncertainty comes from how difficult it is to model millions of billions of random collisions, each one changing the photon's energy slightly, each one affecting its probability of being absorbed versus scattered. Some photons escape faster. They get lucky. Their random walk happens to trend outward. Others take much longer, wandering in circles in the sun's interior for hundreds of thousands of years before finally reaching the surface. But on average, we're talking about timescales longer than human history. And during all this bouncing around, the photon changes. Those initial gamma rays from fusion are incredibly high energy, dangerous, destructive. But each time a photon is absorbed and re-emitted, it tends to be re-emitted at slightly lower energy. Gamma rays become X-rays, become ultraviolet, become visible, light become infrared. The photon gets softer, gentler, through millions of interactions. Its energy distributed across multiple photons, spread out, diluted. By the time light finally escapes the sun's surface, it's mostly visible light, the yellow-white light we see, the light that warms Earth, the light that makes photosynthesis possible, that makes life possible. The dangerous gamma rays have been transformed through countless interactions into something plants can use, something our eyes can detect, something that won't immediately destroy organic molecules. Then, finally free of the sun's density, the photon travels in a straight line. Through the near vacuum of space, it moves at light speed, with nothing to stop it, nothing to scatter it, just open. Emptiness for 93 million miles. 8 minutes, and it reaches Earth. 8 minutes to cross the entire distance between star and planet. After 170,000 years, just to climb up through the star itself. When you stand in sunlight, when you feel warmth on your skin, you're feeling the end of an unimaginably long journey. That photon bounced around in darkness for millennia, slowly working its way outward, random collision after random collision, before finally breaking free and racing toward you at the speed of light. The light touching your face right now is older than pottery, older than the wheel, older than the domestication of animals. It was already ancient when it finally saw open space for the first time. And it crossed that open space, the vast, cold emptiness between here and the sun, faster than you can watch a sitcom episode. There's something profound in that contrast. The journey through density is slow, difficult, full of obstacles. The journey through emptiness is fast, direct, unimpeded. Maybe that's true of more than just photons. Maybe clarity and freedom always make things faster, while confusion and density slow everything down. Or maybe it's just physics. Random walks take time. Straight lines don't. Either way, the next time you're outside in daylight, maybe think about how old that sunlight really is. How long it traveled, how many times it bounced, how patient it had to be. If photons could be patient before finally reaching the surface and sprinting toward Earth. You're being warmed by ancient light, illuminated by photons that started their journey before humans learned to farm, that bounced in darkness for longer than civilization has existed, that only recently saw stars for the first time. And somehow, impossibly, it's here, crossing space at exactly the right speed, carrying exactly the right amount of energy, making Earth habitable, making life possible, making this moment, you, listening, breathing, drifting, happening at all. 8 minutes from surface to here, 170,000 years from core to surface, and all of human history squeezed somewhere in between. Neutron stars are so dense that a sugar cube-sized amount would weigh about 1 billion tons on Earth. Let's talk about weight, real weight, the kind that breaks your intuition about how matter works. Imagine a sugar cube, the kind you might drop into coffee, about 1 centimeter on each side, weighing maybe 4 grams. Light enough to hold between your fingers, small enough to dissolve in hot liquid in seconds. Ordinary, mundane, the kind of object you'd never think about twice. Now imagine that same volume, that 1 cubic centimeter, but made of neutron star material. That small cube would weigh approximately 1 billion tons. Not billion pounds, billion tons. With a B. 1 billion tons is roughly the weight of Mount Everest above sea level. It's the weight of 200 million elephants. It's the weight of all the fish in all the oceans combined. And all of that mass, compressed into a space the size of a sugar cube, sitting in your palm. Except it couldn't sit in your palm, of course. It would instantly fall through your hand, through the floor, through the Earth's crust, through everything, pulling itself toward the planet's core with gravitational force beyond anything we encounter in daily life, or more likely, The gravitational field around it would be so intense that it would distort space-time itself, pulling matter toward it, potentially consuming everything nearby. But let's back up. What is a neutron star? When a massive star, much more massive than our Sun, runs out of fuel, it can no longer support itself against its own gravity. The core collapses catastrophically in a supernova explosion. The outer layers are blown away into space, creating beautiful nebulae we see through telescopes. But the core collapses so completely that protons and electrons are crushed together, forming neutrons. And these neutrons pack together as tightly as matter can possibly be packed without becoming a black hole. A neutron star is essentially a giant atomic nucleus. Normal atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be a marble at the center, with electrons orbiting in the distant stands. But in a neutron star, there's no empty space. The neutrons are packed surface to surface, touching each other, compressed by gravity so intense it overcomes the quantum mechanical forces that normally keep particles apart. The result is matter at nuclear density, about 500 million tons per cubic centimeter, though some calculations put it higher, around 1 billion tons. At this density, a teaspoon of neutron star material would weigh as much as all of humanity combined. A tablespoon would outweigh Mount Everest. The entire star, containing about 1.4 times the mass of our Sun, is compressed into a sphere only about 20 kilometers across, roughly the size of Manhattan. An entire star, mass enough to dominate a solar system, squeezed into something you could drive across in 15 minutes if there were roads on the surface. Which there aren't, because the surface gravity is about 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, and you absolutely couldn't, you'd be crushed into a layer of atoms 1 nucleus thick. The gravity would be so intense that mountains on the surface can't be more than a few millimeters tall. Any irregularity in the surface higher than that would be crushed flat by gravity. It's smoother than a billiard ball, despite being made of incredibly dense, exotic forms of matter. Light itself bends around a neutron star. The gravitational field is so strong that photons following straight paths through space get curved around the star's surface. This means if you could look at a neutron star, you could see part of the backside curving around to the front, like looking at a funhouse mirror made of warped space-time itself. And many neutron stars spin, not slowly either. Some rotate hundreds of times per second, fast enough that their surfaces are moving at a significant fraction of the speed of light. These are pulsars, neutron stars with powerful magnetic fields that create beams of radiation, sweeping through space like a lighthouse, flashing precisely, regularly, like cosmic clocks, keeping time across the universe. The magnetic fields around pulsars are the strongest magnetic fields in the known universe, quadrillion times stronger than Earth's magnetic field. Strong enough that they would be lethal from thousands of miles away. Strong enough to distort the electron clouds around atoms. Strong enough to, in theory, rip the hemoglobin out of your blood if you got close enough. Though gravity would kill you long before magnetism became an issue. All of this, the density, the gravity, the magnetism, the spin, comes from matter being compressed beyond what we can truly imagine. The same fundamental particles that make up you, me, Earth, everything we know, just packed so tightly that normal rules break down and physics becomes something alien. That sugar cube of neutron star material represents matter at the edge of what's possible before it collapses entirely into a black hole. It's the densest form of matter that still exists as matter in any conventional sense. Push it any harder, make it any denser, and it crosses a line, the event horizon, and becomes something else entirely, something from which not even light can escape. But just before that line, just barely holding on to existence as particles rather than as pure gravitational warping, neutron stars sit, these impossible objects, spinning in deep space, pulsing like beacons, reminding us that matter can be stranger, denser, more extreme than anything we encounter in our everyday lives. 1 billion tons per sugar cube. A mountain that can't be taller than a millimeter. A star the size of a city, spinning faster than a helicopter blade. Magnetic fields that could kill from orbit. Gravity that could crush you into nuclear paste. And all of it is real. All of it exists out there, right now, dozens or hundreds or thousands of light years away. Neutron stars spinning in silence, dense beyond comprehension. Remnants of dead stars that couldn't quite collapse into nothingness. The universe contains things we can barely imagine. Objects so extreme they seem like science fiction, but are absolutely, definitively real. We've detected them, measured them, calculated their properties. Matter can be this dense. Gravity can be this strong. The universe allows it, demands it even under the right circumstances. And somewhere out there, a sugar cube's worth of matter weighs as much as a mountain, spinning in darkness, denser than anything you'll ever touch, stranger than most things you'll ever imagine. The human eye can detect a candle flame from about 1.6 miles away on a dark, clear night. We live in a world of bright screens and artificial light, where darkness is rare and sensitivity to faint light seems like an unnecessary skill. But your eyes, evolved over millions of years, refined through countless generations of ancestors who hunted at dusk and navigated by starlight, are remarkably sophisticated light detectors. On a perfectly dark, clear night, with no light pollution, your eyes adapted to darkness for at least 30 minutes. You can detect a candle flame from about 1.6 miles away. Some studies suggest even farther, up to 2.6 miles under ideal conditions. That's a single candle, one small flame, visible across a distance you'd need a car to travel in a few minutes. This isn't theoretical. It's been tested, measured, reproduced. Your eye, under the right conditions, can detect incredibly small amounts of light, as few as 5 to 7 photons arriving at the retina. That's not many. A photon is the smallest possible unit of light, a single quantum particle, and your eye can sense just a handful of them. Of course, not all of those photons actually trigger a visual signal. Some are absorbed by the cornea or lens before reaching the retina. Some hit parts of the retina that aren't sensitive. But when conditions align, when photons hit the rod cells in your retina, the ones responsible for low light vision, even a very small number can create a signal your brain interprets as light. The rod cells are extraordinary. You have about 120 million of them, concentrated in the peripheral parts of your retina. They don't see color. That's what cone cells are for, and you only have about 6 million of those. But rods are exquisitely sensitive to light, capable of responding to individual photons under the right circumstances. This is why, when you want to see something faint at night, a dim star, a distant light, you look slightly to the side of it. You're using your peripheral vision, where rod density is highest. The very center of your vision, the fovea where cone cells are concentrated, is great for detail and color in bright light, but terrible for seeing faint objects in darkness. Astronomers know this. They practice averted vision, deliberately looking slightly away from faint objects to see them better. It feels counterintuitive. Why would looking away help you see something? But it works because evolution distributed your light-sensitive cells based on different needs. Central vision for detail and color, peripheral vision for detecting movement and faint light, for noticing predators at dusk, for finding your way in starlight. Your eyes also adapt to darkness over time. This is dark adaptation, and it happens in stages. The first few minutes in darkness, your pupils dilate to let in more light. That's the quick mechanical adjustment. But the real magic happens over the next 20 to 30 minutes as chemical changes occur in your rod cells. In bright light, a chemical called rhodopsin in your rod cells is constantly being broken down faster than it's replaced. This makes your rods less sensitive. They're essentially overwhelmed by available light. But in darkness, rhodopsin gradually rebuilds, and as it does, your rods become more and more sensitive. After about 30 minutes in complete darkness, your eyes can be about 10,000 to 100,000 times more sensitive to light than they were in bright conditions. This is why when you first step outside at night, you can barely see anything. But after sitting in darkness for a while, details emerge. Trees become visible, stars appear. The landscape reveals itself in shades of gray. Your eyes aren't creating light. They're becoming sensitive enough to use the tiny amounts of light that are actually there. And there is light, almost always. Even on the darkest night, there's starlight, air glow from the upper atmosphere, reflected light from the moon even when it's not visible. The universe is not truly dark except in the deepest caves or artificial environments. There's almost always something to see if your eyes are sensitive enough. That candle flame at 1.6 miles is bright enough, just barely, to send enough photons across that distance for your dark-adapted eyes to detect. It's right at the threshold, the edge of what's possible. Move the candle farther away, and it fades below detection. Move it closer, and it becomes unmistakable. This sensitivity comes with trade-offs, of course. Rod cells are slow. They take time to respond and reset, which is why fast motion in low light appears blurry. They don't distinguish colors, which is why at night everything looks gray, and they can be overwhelmed easily. One flash of bright light, and you've lost your dark adaptation, rhodopsin broken down again, sensitivity gone, 30 more minutes needed to fully recover. But as a light detector, a photon counter, your eye is remarkable. Cameras need long exposures or high ISO settings to capture what your eye can see in real time. Night vision devices amplify light electronically to give what your eye does chemically for free. We don't think about this much anymore. We live in environments where light is abundant, where we flip switches and darkness disappears. We forget that for most of human history, for millions of years before that, being able to see in low light meant survival, meant detecting predators, meant finding food at dawn or dusk when many animals are active, meant navigating safely when the only light came from moon and stars. Your eyes carry that history. They're still optimized for a world darker than the one you live in, still capable of feats of sensitivity we rarely ask of them anymore. But the capacity remains. Go somewhere truly dark, far from cities, on a moonless night, and give your eyes time to adapt. Let the rhodopsin rebuild, let your pupils dilate, let your brain adjust to processing signals from rod cells instead of cones, and then look up at stars you've never seen before, faint and numerous, at the Milky Way, stretching across the sky a river of ancient light. At the universe revealing itself in detail your ancestors knew, but most modern people have forgotten. Your eyes can do this, have always been able to do this, can detect 5 photons, can see a candle from 1.6 miles away, can resolve details in darkness that seem impossible until you actually experience it. You just have to give them the darkness they were designed for, and the time they need to remember how to see it. Antarctica is technically a desert because it receives less than 2 inches of precipitation per year in most areas. When you think of a desert, you probably picture sand, heat, cacti, the Sahara, perhaps, or the American Southwest, sun-baked landscapes where water is precious and life clings to existence in the harshest conditions. You probably don't picture Antarctica, ice, snow, glaciers, a continent covered in frozen water, holding about 70% of Earth's fresh water in solid form, surrounded by ocean, the coldest place on Earth. But Antarctica is, by definition, a desert, one of the driest places on the planet. The definition of a desert isn't about heat or sand or camels. It's about precipitation, specifically the lack of it. Any region receiving less than 10 inches, 250 millimeters, of precipitation per year is classified as a desert. Antarctica receives less than 2 inches per year in most areas. The interior, the coldest and driest parts, receives less than half an inch, drier than the Sahara, drier than almost anywhere else on Earth. This seems impossible at first. How can a place covered in ice be dry? How can there be so little precipitation when there's clearly so much water? The key is understanding what precipitation means. It's not about how much water exists. It's about how much water falls from the sky as rain, snow, sleet, or hail. And in Antarctica, it almost never snows. Not in the way we think of snow anyway. The air in Antarctica is too cold to hold much moisture. Temperature and humidity are intimately connected. Warm air can hold a lot of water vapor. Cold air can hold very little. At the temperatures common in Antarctica's interior, -40, -60, sometimes -80 degrees Celsius, the air is essentially freeze-dried. There's almost no water vapor in it. Without water vapor, you can't have precipitation. Most of what we think of as snow in Antarctica isn't fresh precipitation at all. It's wind-blown snow from elsewhere, or frost forming directly from the tiny amounts of water vapor present, or snow that fell thousands of years ago and has been compacted into ice. The ice sheet itself is ancient. Some of the ice in Antarctica's interior is nearly 1 million years old, snow that fell long before humans existed, compressed over millennia into glacial ice thousands of meters thick. But very little new snow actually falls. The little that does fall tends to accumulate near the coasts, where slightly warmer temperatures and ocean moisture create conditions for actual precipitation. The interior is so dry that scientists compare it to Mars. Some valleys in Antarctica, the McMurdo Dry Valleys, have been ice-free for millions of years despite being in Antarctica, because they receive so little precipitation that ice can't accumulate, and sublimation, ice turning directly to vapor without melting, removes what little moisture exists. These dry valleys are among the most Mars-like places on Earth. NASA studies them as analogs for Martian conditions. They're cold, dry, inhospitable to most life, with landscapes of rock and frozen ground that look alien, not like any place you'd expect to find on Earth, much less on the ice-covered continent. So Antarctica is a desert not despite being covered in ice, but in a way because of the conditions that keep it frozen. The extreme cold prevents precipitation. The ice that's there is old, accumulated over unimaginable timescales, not recently fallen. It's a frozen desert, a polar desert, a place where water exists in abundance but is locked away, inaccessible, where new water rarely arrives and life barely exists. The interior of Antarctica is more barren than the Sahara, more hostile to life than most of Earth's surface, and yet paradoxically it contains most of Earth's fresh water. If all the ice in Antarctica melted, which it won't, not quickly, but if it did, sea levels would rise over 200 feet globally. Coastal cities would vanish. Entire countries would disappear underwater. The shape of continents would change. All that water currently locked in a frozen desert where it never rains. There's something beautifully contradictory about this. A desert made of water, a dry place that could drown the world, a frozen continent that defines our understanding of ice but rarely sees new snow. It reminds you that categories are human constructions, convenient labels we apply to make sense of complexity. Nature doesn't care about our definitions. A desert is any place with little precipitation, whether it's hot or cold, sandy or icy. Antarctica qualifies. It's drier than the Sahara, more hostile than the Gobi, more barren than any warm desert on Earth. And all that ice, it's not because Antarctica is wet. It's because for millions of years, tiny amounts of snow have fallen and never melted, accumulating centimeter by centimeter, year by year, building slowly into an ice sheet 3 miles thick in places, preserving ancient air bubbles and dust and the history of Earth's climate in frozen layers we can core through and read like tree rings. Antarctica is a desert that remembers, a place so dry that even the small amount of precipitation that does fall stays forever, building into glaciers, flowing slowly toward the sea over thousands of years, eventually calving into icebergs that drift northward and melt, returning to the ocean what fell as snow when mammoths walked the earth. Dry and wet, frozen and fluid, desert and ice sheet, all at once, depending on how you measure, what you count, what definition you apply. Maybe that's true of more than just Antarctica. Maybe everything contains contradictions if you look closely enough. Maybe the world is always more complex than the words we use to describe it. Or maybe Antarctica is just strange, a place at the edge of habitability, where normal rules break down and Earth reveals possibilities we don't encounter anywhere else. Either way, it's a desert, the largest desert on Earth, in fact, cold and white and covered in ice. And it almost never snows. The entire internet weighs approximately 50 grams, about the weight of a large strawberry. It seems like a nonsense statement at first. The internet is information, data, something immaterial that exists in abstract space. You can't pick up the internet. You can't put it on a scale. It doesn't have weight because it's not a physical thing. It's a network, a concept, electrical signals moving through wires and air, patterns of light in fiber optic cables, radio waves carrying data from towers to phones. Except it does have weight. Not much, but some. A real, calculable amount based on the physics of information storage and transmission. When you store data, you're storing it in electrons. Specifically, you're storing it in the motion and position of electrons. A bit, a single binary digit, a 1 or a 0, is represented by the presence or motion of electrons. In a hard drive, it's the magnetic orientation of regions on a spinning disk. In RAM, it's the charge stored in tiny capacitors. In flash memory, it's electrons trapped in transistor gates. In fiber optic cables, it's pulses of light, photons carrying information. All of these have mass. Photons don't have rest mass, but they carry energy, and energy has mass equivalence through Einstein's ERmc2. Electrons definitely have mass, about 9.1 x 1031 kilograms each, an almost incomprehensibly small amount, but not zero. Scientists have estimated that the entire internet, all the data stored on servers, all the information in transit at any given moment, all the electrons and photons carrying emails and videos and web pages and messages, has a combined mass of approximately 50 grams. 50 grams, the weight of a large strawberry, or about 2 ounces. That's the mass of all the electrons in motion that, at any given instant, represent the entire internet. Think about what that includes. Every email ever sent and stored, every video on YouTube, every social media post, every website, every photo in the cloud, every financial transaction, every search query, every streaming movie, every video call happening right now. All of it, globally, compressed into a weight so small you could hold it in your palm if it were somehow gathered together. Of course, it's not gathered together. It's distributed across millions of servers in data centers around the world, transmitted through countless miles of fiber optic cable, bouncing between cell towers, moving through the air as Wi-Fi signals, scattered across the planet in a vast, interconnected web. But if you could somehow collect all those electrons, all those photons, all the particles in motion that represent stored and transmitted data at this exact moment, they'd weigh about as much as a strawberry. This number is an estimate, of course, based on assumptions about how much data is stored globally, how much is in transit, the typical mass of electrons in various storage media, the energy of photons carrying information. Different calculations give slightly different results. Some say 50 grams, some say closer to 100, some suggest less. The exact number is less important than the concept. The internet, despite feeling massive and boundless, has a finite, measurable, surprisingly small mass. It highlights something profound about information. Information isn't nothing. It has physical reality. It requires energy to store, energy to transmit, energy to process, and energy, through Einstein's equations, is equivalent to mass. So information, in a very real sense, has weight. Not much weight, admittedly. The internet weighs less than an apple, but it's not zero. It's measurable, real. This becomes important in physics and computer science. There are theoretical limits to how much information can be stored in a given amount of mass or a given volume of space. These are called Bekenstein bounds, and they derive from thermodynamics and quantum mechanics. They suggest that there's a maximum density of information, that you can't store infinite data in finite space, that information storage requires physical substrate, and that substrate has limits. We're nowhere close to those limits with current technology, but they exist fundamentally, suggesting that information and physics are connected at the deepest levels. that you can't separate the abstract world of data from the physical world of particles and energy. The internet is light, but it's not weightless. Every time you send an email, you're moving electrons, creating electromagnetic fields, changing the state of transistors in servers. Every time you watch a video, photons are being generated and detected, energy is being transferred, particles are moving. Every time you post a photo, you're altering the magnetic domains on hard drives, or trapping electrons in flash memory cells, adding infinitesimally to the total mass of stored data. Most of that mass comes from the electrons themselves, sitting in memory cells, stored in capacitors and transistors. A smaller amount comes from electrons in motion, the data being actively transmitted at any given moment. And an even smaller amount comes from the photons carrying information through fiber optic cables at the speed of light. All of it together, about 50 grams, the weight of a strawberry, the mass of a few tablespoons of water, light enough to blow away in a strong wind, if you could somehow gather it all in one place, which you can't, obviously. The internet exists as a distributed system, spread across the planet, no single location containing more than a fraction of the total. But mathematically, hypothetically, if you could collect all the information-carrying particles at one moment, you'd have something you could hold easily in your hand. There's something humbling about that. The internet feels vast, endless content, infinite information, a digital universe that seems to expand without limit. We talk about the cloud as if it's this immaterial space floating above physical reality. But it's not immaterial. It's electrons and photons, mass and energy, distributed across physical servers that run on electricity generated by burning fuel or harnessing wind or splitting atoms. The internet is physical. It has weight, barely any, but some. And somehow, in that minuscule mass, we've encoded a significant fraction of human knowledge. Libraries, museums, conversations, videos, photos, the collected thoughts and works and daily trivia of billions of people. 50 grams, the weight of a strawberry, light enough to carry, heavy enough to matter. Trees communicate with each other through underground fungal networks scientists call the Wood Wide Web. The forest is not a collection of individuals. It's a network, a community, a conversation happening too slowly for us to hear, but constantly ongoing beneath our feet. For a long time, we thought of trees as solitary organisms, each one competing for light, water, nutrients, fighting for survival in a hostile environment where resources are scarce and only the strongest survive. It fit our understanding of evolution, of natural selection, of nature read in tooth and claw. But we were wrong, or at least we were seeing only part of the picture. Beneath the forest floor, invisible to casual observation, exists a vast network of fungal threads called mycelium. These fungi form partnerships with tree roots in relationships called mycorrhizae, literally fungus root in Greek. The fungi wrap around or penetrate tree roots, creating an interface where exchanges happen. The tree provides the fungus with sugars, products of photosynthesis that the fungus can't make on its own because it doesn't have chlorophyll, can't harness sunlight, can't convert carbon dioxide into carbohydrates. The fungus, in return, provides the tree with nutrients, phosphorus, nitrogen, other minerals, that its thread-like hyphae can extract from soil more efficiently than roots can. This is mutualism, a beneficial partnership, and it's been known for over a century. What we didn't realize until relatively recently is that these fungal networks don't just connect one tree to one fungus. They connect tree to tree to tree, forming underground networks that link entire forests together. A single fungal network can connect dozens or hundreds of trees, different species, different ages, even different genera, all linked through shared fungal partners. And through these networks, the trees communicate. They share resources. They help each other survive. Mother trees, the oldest, largest trees in a forest, are hubs in these networks, connected to more individuals than younger trees. And these mother trees do something remarkable. They recognize their offspring. Through chemical signals, through patterns of resource sharing that scientists are still working to fully understand. Mother trees can identify their own seedlings and preferentially send them resources through the fungal network. When a young tree is struggling, growing in shade, perhaps, not getting enough light to photosynthesize adequately, the mother tree can send it carbon, sugars, the products of her own photosynthesis, transferred through fungal intermediaries. It's not conscious care, not parental love as we understand it, but it's functional support. Older trees helping younger ones survive, increasing the odds that their genetic legacy continues. But it's not just parent to offspring. Trees will share resources with unrelated individuals, sometimes even with different species. A Douglas fir might send carbon to a paper birch through shared fungal networks. This seems to contradict basic evolutionary logic. Why help a competitor? But forests don't operate on simple competition models. They're ecosystems, communities where collective survival sometimes matters more than individual advantage. There's evidence that trees can send warning signals through these networks. When one tree is attacked by insects, it releases defensive chemicals to make its leaves less palatable. But neighboring trees, connected through fungal networks, also begin producing defensive compounds even before they're attacked. They're receiving signals through the network, chemical information saying, "Danger, prepare yourselves," and responding proactively. It's a kind of immune system for the forest, an early warning network where information about threats spreads faster than the threats themselves, giving trees time to prepare defenses, to harden themselves against attack. Scientists call this network the Wood Wide Web, a playful reference to the internet, and the analogy is apt. It's a decentralized network, no central control, information flowing between nodes, resources being transferred, the whole system functioning without any individual coordinating the activity. The fungi benefit too, of course. This isn't altruism on their part. They get sugars from multiple trees, which means if one tree dies or declines, they have other sources. The network provides them with stability, redundancy, insurance against the failure of any single partner. And there's evidence that fungi might, in some sense, be managing the network, directing resources not just passively, but actively, moving nutrients toward trees that need them most, maintaining the health of the forest because healthy trees mean more sugar for the fungi. It's a three-way relationship: tree, fungus, forest, each one dependent on the others, each one contributing to a system larger than any individual. This changes how we think about forests. They're not just collections of trees growing in proximity. They're superorganisms, in a sense, networks where individuals are nodes in a larger system, connected underground, in ways that affect how they grow, survive, reproduce. Old-growth forests have had centuries to develop these networks, thick, extensive, mature fungal highways connecting everything. When we clear-cut old growth and replant, we're not just removing trees, we're destroying these networks, severing connections that took hundreds of years to establish. The new trees we plant might grow, but they're isolated, not connected, unable to access the resource sharing and communication that made the old forest resilient. There's something humbling about discovering that trees, which we think of as simple, passive, almost furniture-like in their stillness, are actually engaged in complex social behavior underground. That forests are communities, communicating, cooperating, supporting each other in ways that increase collective survival. And we never knew. We walked through forests for thousands of years, cut them down, studied them, wrote poetry about them, and we never realized there was this whole conversation happening beneath us. Chemical signals flowing through fungal threads, resources being shared, information spreading tree to tree. It was invisible, too slow to see, too subtle to measure without careful experimentation, too different from our own experience to imagine. But it's real, demonstrable, measurable now that we know what to look for. The forest is talking, has always been talking. We just weren't listening in the right way, on the right time scale, through the right medium. Trees speak in chemicals and sugars, in nutrient transfers and electrical signals, in patterns that unfold over days and weeks and seasons. And they're saying things that matter, warnings about danger, gifts of carbon to struggling offspring, support to neighbors, maintenance of the community that they all depend on. When you walk through a forest now, maybe think about what's happening beneath your feet. The invisible network connecting everything, older than many of the trees themselves, facilitating conversations we're only beginning to understand. The wood wide web, humming with traffic, transferring resources, spreading information, maintaining the collective. And all of it happening in darkness, underground, silent except at frequencies we can't hear, through channels we can't see, in a language we're only learning to translate. The trees are talking. They've always been talking. We're just starting to listen. A day on Venus is longer than its year. Venus takes 243 Earth days to rotate once, but only 225 Earth days to orbit the Sun. Time doesn't work the same everywhere. We think of a day as 24 hours and a year as 365 days. Those ratios feel fundamental, like they're properties of time itself, rather than accidents of Earth's rotation and orbit. But they're not fundamental, they're local, specific to our planet, our distance from the Sun, our angular momentum, our history. On Venus, everything is different. A day on Venus, the time it takes for the planet to rotate once on its axis, for the Sun to rise, cross the sky, set, and rise again, lasts 243 Earth days, almost 8 Earth months for a single Venusian day. But a year on Venus, the time it takes to complete one orbit around the Sun, lasts only 225 Earth days. Read that again, slowly. A single day is longer than an entire year. Venus completes an orbit around the Sun before it completes a rotation on its axis. This seems impossible, like a calendar paradox, like time has folded in on itself incorrectly. How can a day be longer than a year? What does that even mean? It means that if you could stand on Venus's surface, and you can't, it's 900 degrees Fahrenheit with atmospheric pressure, 90 times Earth's sulfuric acid clouds, and no breathable air. But if you could, you'd see the sunrise move slowly across the sky and set over the course of an entire Venusian year, then darkness for most of another year, then sunrise again. One sunrise, one sunset, and Venus has orbited the sun twice. It gets stranger. Venus rotates backward compared to most planets. Retrograde rotation, it's called. While Earth, Mars, Jupiter, Saturn, and most other planets spin counterclockwise when viewed from above the sun's north pole, Venus spins clockwise. If you could see the sun from Venus's surface, through the thick clouds, which you can't, it would rise in the west and set in the east. Why? We don't know for certain. The most likely explanation is a massive collision early in Venus's history, an impact from another planetary body that struck with enough force to alter Venus's rotation. Maybe it was spinning normally before, and the impact reversed it. Maybe the impact slowed the rotation so much that tidal forces from the sun then flipped it around. Or maybe Venus formed with retrograde rotation for reasons related to the chaos of the early solar system. Planetary formation involves countless collisions, interactions, gravitational perturbations, and sometimes things end up spinning the wrong way just because that's how the angular momentum worked out. Whatever the cause, Venus is now locked into this slow, backward rotation, turning so slowly that the sun's tidal forces, the gravitational pull on the planet's body, have a significant effect. The thick atmosphere, the dense clouds, even the solid planet itself, all experience tidal stresses from the sun, creating friction that continues to slow Venus's rotation even further. Over millions of years, Venus's day is getting longer. Eventually, it might become tidally locked to the sun, with one side permanently facing the sun and the other in permanent darkness, the same way the moon is tidally locked to Earth. But that's millions or billions of years in the future, if it happens at all. For now, Venus exists in this strange state, spinning so slowly that its year happens faster, rotation and revolution out of sync, in ways that break our intuitive understanding of planetary motion. And because the atmosphere is so thick and rotates much faster than the solid planet, atmospheric superrotation, it's called. The winds at cloud level can reach 200 miles per hour, circling the entire planet in just 4 Earth days. So while the ground takes 243 days to rotate once, the atmosphere takes 4 days. The air moves about 60 times faster than the surface beneath it. Imagine standing on slowly rotating ground while the air above rushes past at hurricane speeds, clouds racing overhead, the sky in constant violent motion while the sun barely moves. It's alien, genuinely alien. Conditions so different from Earth that they feel like science fiction, but they're real, happening right now on the nearest planet to us, our so-called sister planet, because it's similar in size and mass and composition. But Venus is no sister to Earth, not really. It's a hellscape, runaway greenhouse effect, surface hot enough to melt lead, atmospheric pressure that would crush a submarine, sulfuric acid rain that never reaches the ground because it evaporates in the heat, a slow motion rotation that makes time itself seem broken. A day longer than a year, sunrise in the west, winds faster than the spinning of the world itself. Venus reminds us that planets don't have to follow Earth's patterns, that rotation and orbit are independent variables, accidents of formation and collision history, not synchronized by any universal law. That time, at least the divisions we use to mark it, days and years, is not constant across the universe, but varies wildly, depending on where you are, how fast you're spinning, how far from your star. On Mercury, a day lasts 176 Earth days, but a year only 88, though Mercury is tidally locked into a 3.2 spin orbit resonance, which means it rotates 3 times for every 2 orbits, creating a strange pattern where some parts of the planet experience 2 sunrises per Mercurian year. On Jupiter, a day is only 10 hours, the fastest rotation of any planet in the solar system, despite Jupiter being the largest. A year there lasts 12 Earth years, so Jupiter experiences more than 10,000 sunrises and sunsets in a single orbit. Every planet is different. Every moon has its own patterns. Time, measured by celestial mechanics, is wildly variable. Only on Earth does it feel normal, regular, intuitively sensible that days are much shorter than years. But that's just us, just here, just the particular combination of rotation rate and orbital period that happened to emerge from the chaos of solar system formation 4.6 billion years ago. Elsewhere, time is strange, slow on Venus, fast on Jupiter, locked on the Moon, variable in ways we can measure but struggle to imagine experiencing. A day longer than a year, the sun rising once, setting once, and you've gone around the sun twice in darkness. Venus doesn't care about our expectations. It spins at its own pace, backward, slowly, taking its time while racing around the sun, existing in a temporal relationship that breaks our calendar logic but makes perfect physical sense once you understand the mechanics. Time is local, always has been. Venus just makes it obvious. Your DNA, if uncoiled, would stretch about 10 billion miles, enough to reach from Earth to Pluto and back. Right now, sitting or lying wherever you are, you probably have a good sense of your physical size, your height, your reach, the space your body occupies, a few feet tall, maybe 6 feet with arms extended, a volume of perhaps 70 liters if we're measuring displacement. But that's only one way to measure size. If we measure differently, you're much, much larger. Inside nearly every cell in your body, all 37 trillion of them, is a nucleus, and inside each nucleus is DNA. Your DNA is a molecule, a very long molecule, shaped like a twisted ladder, a double helix that contains all the genetic instructions for building and maintaining you. In each cell, your DNA is organized into 23 pairs of chromosomes, 46 chromosomes total. Each chromosome is one very long DNA molecule wound around proteins called histones, coiled and supercoiled and packed tightly to fit into a nucleus that's only about 6 micrometers across, 6 millionths of a meter, far too small to see without a microscope. But if you could uncoil all that DNA from one cell, unwrap it from the histones, straighten it out, it would stretch about 6 feet, roughly 2 meters. That's just from one cell. One single cell contains enough DNA, if stretched out, to span your full height. Now multiply that by 37 trillion cells. The total length of all the DNA in your body, if it could somehow be uncoiled and stretched end to end, would be approximately 10 billion miles. Some calculations put it higher, around 20 billion miles, depending on the exact number of cells and assumptions about DNA length. But the order of magnitude is right. It's billions of miles. Unimaginable distances contained in a body that occupies a few cubic feet of space. 10 billion miles is enough to reach from Earth to Pluto and back. Twice over, actually. Pluto, at its closest approach, is about 2.7 billion miles from Earth. At its farthest, about 4.7 billion miles. Your DNA could make that trip multiple times and still have length left over. Or think of it this way: 10 billion miles is enough to travel from Earth to the Sun and back 54 times. It's enough to circle Earth's equator 400,000 times. It's a distance light takes almost 15 hours to cover, and light moves at 187,282 miles per second. All of that length compacted into you, into a space small enough to fit through a doorway, light enough to lift, contained enough to maintain coherent form and identity. How is this possible? DNA is incredibly thin. The double helix is only about 2 nanometers wide, 2 billionths of a meter. It's thin enough that even when stretched to human height, it's invisible to the naked eye. You'd need an electron microscope to see it, even at 6 feet long. And it's wound up tight, coiled and supercoiled, packed with extraordinary efficiency. The cell nucleus is basically a filing system, chromosomes organized, histones acting like spools that DNA wraps around, everything compressed and folded in ways that allow access when needed, but keep it from tangling into an unusable mess. This packing is so efficient that all your genetic information, the complete instruction manual for building you, maintaining you, passing on your traits to offspring, fits into a nucleus thousands of times smaller than the period at the end of this sentence, and yet it's still billions of miles of molecule, if stretched. This is what molecular biology looks like at scale. Objects so small we can barely visualize them, yet so long that they span astronomical distances when unfolded. It's a weird mismatch between width and length, like having a thread thin enough to pass through the eye of a needle, but long enough to wrap around the moon. That DNA isn't just length, though. It's information. About 3 billion base pairs in the human genome, arranged in specific sequences that code for proteins, regulate gene expression, contain your eye color and blood type, and susceptibility to certain diseases, and countless other traits. All of that information repeated in almost every cell, 37 trillion copies of your genetic blueprint, ready to be read, transcribed, translated into the proteins that do the actual work of being alive. And it's old. The DNA in your cells isn't newly made. Much of it has been there since you were a single-cell embryo, duplicated over and over as you grew from 1 cell to 2 to 4 to the trillions you are now. Some of those molecules have been with you your entire life, traveling with you through time, accumulating small copying errors occasionally, mutations that make you slightly different from the genetic template you started with. Every time a cell divides, it has to copy all its DNA, all 3 billion base pairs, all 6 feet of molecule, duplicated with remarkable accuracy. The error rate is about 1 mistake per billion base pairs, which sounds good until you realize that with trillions of cells dividing constantly, mutations happen regularly. Most are harmless, caught and corrected by repair mechanisms. Some cause problems: cancer, genetic diseases, aging effects. A few might even be beneficial, slight variations that make you marginally better at something, though you'd never notice. Your body is a library containing trillions of books, each one 3 billion letters long, each one a slightly imperfect copy of the original. All of them packed into spaces too small to see, stretching to lengths too large to comprehend. If unfolded, 10 billion miles of DNA in you right now. It's not doing anything dramatic at the moment. Mostly, it's just sitting in nuclei, coiled and packed, waiting to be read when cells need to produce proteins. But it's there. This impossibly long thread of genetic information doubled and doubled and doubled again across trillions of cells, containing everything needed to make you and maintain you and, if it comes to that, create new life that carries forward part of your genetic sequence. You are smaller than you feel in one sense, just a temporary arrangement of molecules, a pattern that will eventually disperse, no permanent substance. But you're also larger than you can imagine. Billions of miles of information folded into a form that walks and talks and thinks and feels and somehow manages to remain coherent despite being made of parts so small and strings so long and processes so complex that we're still figuring out how it all works. 10 billion miles, Earth to Pluto and back, all of it inside you. Lightning is 5 times hotter than the surface of the sun, reaching temperatures of about 30,000 Kelvin. Lightning is not cold fire, though it's fast enough that sometimes it seems that way. It's not a gentle discharge, not a soft transfer of electrons seeking balance. Lightning is violent, catastrophically hot, faster than thought. When lightning strikes, the channel of air through which it travels, usually no wider than a pencil, is heated almost instantaneously to about 30,000 Kelvin. That's about 30,000 degrees Celsius, or roughly 54,000 degrees Fahrenheit. The surface of the sun, by comparison, is about 5,800 Kelvin. Lightning is 5 times hotter. Think about that for a moment. The sun, that massive fusion reactor, 93 million miles away. The source of all Earth's energy. The thing so bright you can't look at it directly without damaging your eyes. Lightning is hotter. Not in total energy, obviously. The sun contains vastly more heat in total. But at the point of the strike, in that narrow channel, lightning exceeds the sun's surface temperature by a factor of 5. This extreme heat happens because of how lightning works. Inside a thunderstorm, ice particles and water droplets collide, transferring electrons, building up charge separation. The top of the cloud becomes positively charged, the bottom becomes negatively charged. The ground below becomes positively charged by induction. Eventually, the potential difference becomes too great. The insulating properties of air break down. A pathway of ionized air, a stepped leader, extends from cloud toward ground in a jagged path, branching, searching. When it gets close enough, a streamer rises from the ground to meet it. They connect. And then the main discharge happens. Electrons flow from cloud to ground in a pulse lasting maybe a millisecond, maybe a third of a millisecond. In that tiny fraction of a second, an enormous amount of energy moves through a very small space. The air in the channel heats so fast it doesn't have time to expand gradually. Instead, it explodes outward, creating a shock wave that propagates as sound. That's thunder, the sonic boom created by air heated to plasma temperatures faster than it can respond, expanding supersonically, creating a pressure wave that rumbles across miles of landscape. The light we see, the bright flash, the branching bolt, is the air itself glowing. At 30,000 Kelvin, air becomes plasma, the fourth state of matter. Atoms stripped of electrons, everything ionized, glowing with blackbody radiation across the visible spectrum and beyond. The lightning channel emits ultraviolet, visible light, infrared, radio waves, X-rays even. For a fraction of a second, that narrow column of air is hotter than the surface of the sun, brighter than any fire. Energetic enough to fuse sand into glass where it strikes, to vaporize metal, to set trees ablaze from the inside out, as the moisture in their sap turns to steam explosively. And then it's over. The current stops. The channel cools. The plasma recondenses into ordinary air, nitrogen and oxygen molecules, reforming. Everything returning to normal except for the damage left behind. Scorched earth, split wood, whatever was unfortunate enough to be in the path. Lightning strikes somewhere on Earth about 100 times per second. Right now, as you lie there are roughly 2,000 thunderstorms in progress globally, each one generating multiple strikes, channels of air being heated to solar temperatures over and over, constantly, the atmosphere in continuous electrical activity. Most lightning never reaches the ground. It stays within clouds, or jumps cloud to cloud, charge seeking equilibrium without ever connecting to the surface. But about 25% of lightning strikes hit the ground, and those are the dangerous ones, the ones that start fires and kill people and destroy electronics and leave those distinctive Lichtenberg figures, fractal burns, on skin and wood and sand. Humans struck by lightning sometimes survive. The current passes through them in a millisecond, often following the path of least resistance, across skin rather than through vital organs, if they're lucky. But the heat can cause severe burns. The shock can stop the heart or disrupt neural function, and even survivors often have lasting nerve damage, memory problems, chronic pain. Objects struck by lightning fare worse. Trees explode. The sap inside turns to steam so quickly the wood can't contain it, pressure building faster than cracks can propagate, the tree simply coming apart. Sand melts and fuses into glass, creating fulgurites, hollow tubes of glass following the path of the lightning into the ground, sometimes many feet deep, formed in fractions of a second and cooled into permanent records of the strike. Buildings hit by lightning can catch fire. Electronics can be destroyed by the electromagnetic pulse. Structural damage can occur if the current finds vulnerable pathways through the materials. And all of this from air heated, briefly, to 5 times the sun's temperature. There's something humbling about how much energy is stored in a thunderstorm, ready to be released in these brief, violent pulses. The storm looks dramatic from outside, dark clouds, flashing light, rumbling thunder, but the actual strikes are almost too fast to perceive. Blink and you miss the lightning itself, seeing only the after image, the burned pathway on your retina, the flash that's already over by the time your brain processes it. 30,000 Kelvin, 5 times the surface of the sun, in a channel no wider than a pencil, lasting less than a second. The universe allows this, encourages it even. The physics of charge separation, electrical potential, atmospheric breakdown, all of it conspires to create these moments of extreme energy, brief touches of stellar temperatures in ordinary air, the sky briefly hot enough to melt rock, and then back to normal as if nothing happened. Except something did happen. Trees split, sand fused, air shocked into sound waves that travel for miles. And somewhere, maybe, a person looking up at the wrong moment, seeing the flash, feeling the heat, struck by something 5 times hotter than the sun's surface. Their life changed or ended in the time it takes to blink. Thunder follows later, always later. Sound is slow compared to light, traveling at only 767 miles per hour through air. So you see the flash first, and then you wait. 5 seconds per mile, roughly. Count the seconds between flash and thunder, divide by 5, and you know how far away the strike was. But the heat? The 30,000 Kelvin moment? That's already over, already past. The channel cooled, the plasma dissipated, the air returned to its normal temperature. Only the damage remains, only the thunder, rolling in later, telling you something violent just happened, even if you can't see the evidence from where you are. Lightning is fast, hot, gone before you can react, 5 times the sun's surface temperature. And then nothing, just air again, just ordinary atmosphere, electrically neutral, calm, until the next strike. Sharks have been around longer than trees. They existed about 400 million years ago, while trees appeared around 350 million years ago. There's a version of Earth's history that feels right, intuitively correct, where landscapes come first and animals fill them in afterward. First the land, the rocks, the mountains, then plants colonizing the bare stone, then trees creating forests, and finally animals, fish in the seas, insects in the air, eventually sharks in the depths. It seems logical, progressive, a natural order from simple to complex, but it's wrong. Sharks came first. Sharks existed before trees. Sharks have been swimming through oceans for approximately 400 million years. They appeared in the Devonian period, sometimes called the Age of Fishes, when the seas were full of strange armored fish, early jawed vertebrates, creatures experimenting with body plans that would succeed or fail based on survival and reproduction. Sharks succeeded. Their body plan, cartilaginous skeleton, multiple gill slits, streamlined shape, replaceable teeth, turned out to be extraordinarily successful. So successful that sharks have remained relatively unchanged for hundreds of millions of years. They're often called living fossils, though that's slightly misleading, because modern sharks aren't identical to ancient ones. They've evolved, diversified, adapted, but the basic template has worked so well that major changes weren't necessary. Trees, on the other hand, appeared around 350 million years ago. Before that, land plants existed, mosses, ferns, early vascular plants, but nothing we'd recognize as a tree, nothing with woody trunks that grew tall and lasted for decades or centuries. The first trees were primitive by modern standards, Archaeopteris and similar species, more like giant ferns than modern oaks or pines. But they were trees, tall, woody, creating the first forests, the first canopies, the first forest floors. And sharks were already there, already swimming, already hunting, already using the same basic design they'd use for the next 350 million years. This timeline shifts our perspective. Sharks aren't relative newcomers to Earth's history, late additions to ecosystems that were already established. They're ancient, foundational, part of Earth's fauna before forests existed, before trees created soil by dropping leaves, before the carbon cycle looked anything like what we know today. Sharks survived the Devonian, the Carboniferous, the Permian extinction that killed 96% of marine species. They survived the Triassic, the Jurassic, the Cretaceous extinction that killed the dinosaurs. They survived ice ages, asteroid impacts, massive volcanic eruptions, climate shifts, continent rearrangements, ocean chemistry changes. Trees, by comparison, are young. Yes, 350 million years is ancient by human timescales. But in Earth's history, in the timeline of complex life, trees are late arrivals. They came after sharks had already been around for 50 million years, already diversified, already established themselves as successful predators. Think about what this means. Sharks witnessed the first forests. They were swimming through oceans when land was transforming from bare rock and low vegetation to towering forests. They existed when the first trees fell and began creating soil. They were there when coal deposits started forming from buried forest material during the Carboniferous. Sharks are older than Saturn's rings, which are estimated to be only 100 to 400 million years old. Older than the Appalachian Mountains in their current form. Older than flowers, which appeared about 130 million years ago. Older than grass, which only emerged about 55 million years ago. When dinosaurs walked the earth, sharks were already ancient. When mammals first evolved, sharks had been around for 200 million years. When humans appeared, 300,000 years ago, a geological eye blink, sharks had existed for more than 1,000 times longer. And they're still here, still swimming, still hunting, still using teeth that regrow in rows, still sensing electrical fields through ampullae of Lorenzini, still patrolling oceans with the same basic body plan that worked 400 million years ago. There's something both humbling and reassuring about this. Humbling because it reminds us how young we are, how recent, how brief our tenure on Earth has been. Reassuring because it shows that successful designs can last, that adaptation doesn't always mean constant change, that sometimes evolution finds a solution so effective it barely needs modification for hundreds of millions of years. Sharks aren't perfect. They're vulnerable to overfishing, to ocean acidification, to climate change. Many species are threatened or endangered because their slow reproduction can't keep pace with human predation. We're killing them faster than they can replace themselves after 400 million years of survival. But the species that remain, the ones we protect, the ones in waters we don't overfish, they're still fundamentally the same animals that swam before trees existed. Still apex predators, still efficient, still adapted to their environments in ways that work as well now as they did in the Devonian. Trees came later. Trees transformed the world, created soil and oxygen and habitats and wood, and all the things we associate with terrestrial ecosystems. Trees are vital, important, foundational in their own way. But sharks were there first, swimming through oceans that would look alien to us, under skies with different oxygen levels, seeing continents in different configurations, but swimming nonetheless, hunting, surviving, adapting enough to persist, but not so much that they lost what made them successful in the first place. 400 million years. Older than trees, older than dinosaurs, older than almost anything you can point to in the natural world except rocks and the ocean itself. Sharks, still here, still swimming, waiting patiently for the next 400 million years, if we let them. Every hydrogen atom in your body is approximately 13.8 billion years old as the universe itself. You are made of ancient things, not metaphorically ancient, not poetically old, actually, literally, measurably ancient, older than Earth, older than the Sun, older than the Milky Way galaxy, older than almost anything else you can point to except the universe itself. The hydrogen atoms in your body, and there are many of them, hydrogen makes up about 10% of your body weight, mostly in water and organic molecules, were created approximately 13 to almost 8 billion years ago in the first few minutes after the Big Bang. In those first moments, the universe was unimaginably hot and dense. Pure energy, matter and antimatter annihilating each other, particles forming and dissolving in fractions of a second. But as the universe expanded and cooled, things stabilized. Protons and neutrons formed from quarks, and in the first 3 minutes, literally just 3 minutes after the beginning of everything, those protons and neutrons began fusing into the lightest elements, mostly hydrogen, some helium, trace amounts of lithium and beryllium. That was it. The entire periodic table, everything we know about chemistry, all the elements that make up planets and stars and people. In those first 3 minutes, the universe made only the lightest ones. Hydrogen, helium, a bit of lithium. Everything else came later, forged in stars over billions of years. But hydrogen? Hydrogen is primordial, original, the oldest stuff there is. A hydrogen atom is simple. One proton, one electron, the simplest possible atom. And the protons in your body's hydrogen atoms have existed since those first 3 minutes. They haven't changed. They can't change. Not without nuclear reactions that don't happen in bodies. Don't happen on Earth except in particle accelerators or nuclear weapons. Those protons are 13.8 billion years old. They existed before the solar system formed, before the sun ignited, before Earth coalesced from the protoplanetary disk. They drifted through space as part of the primordial hydrogen cloud that filled the early universe. They were there when the first stars formed, when galaxies began to coalesce, when the cosmic microwave background was created. Some of those hydrogen atoms might have been inside stars at some point, pulled into stellar cores by gravity, fused with other hydrogen atoms to make helium, releasing energy that powered the star. But most of the hydrogen in your body probably wasn't. Most of it has remained hydrogen the entire time, drifting through space, incorporated into molecular clouds, eventually ending up in the solar nebula that formed the sun and planets. Then Earth formed. Some hydrogen ended up in water molecules in Earth's early oceans. Some got incorporated into organic molecules as life began. And over billions of years, through countless chemical reactions, those hydrogen atoms have been part of oceans, rain, plants, animals, humans. The hydrogen atoms in your body right now have been recycled countless times. They've been in water drunk by dinosaurs, by ancient humans, by every organism that ever lived and needed water. They've been in rain that fell on Pangaea, in ice that covered glaciers during ice ages, in rivers that no longer exist, in organisms that went extinct millions of years ago. But through all of that, the protons themselves, the cores of those hydrogen atoms, have remained unchanged. They're the same protons that formed in the Big Bang, just recombined with different electrons, arranged into different molecules, cycling through the biosphere and atmosphere and oceans, but fundamentally unchanged. You are approximately 60% water by weight. Water is H2O, 2 hydrogen. Atoms for every oxygen atom. So roughly 10% of your body mass is hydrogen, about 7 kilograms if you weigh 70 kilograms. That's roughly 4x 1027 hydrogen atoms, 4,000 trillion hydrogen atoms. Every single one of them, 13.8 billion years old. They've been on a journey you can barely comprehend. From the Big Bang through billions of years of cosmic history, through stars and nebulae and the formation of the solar system, through Earth's formation and evolution, through the origin of life and its diversification into millions of species, through geological ages and mass extinctions and ice ages and climate changes, through your ancestors going back billions of years, and finally, temporarily, ending up arranged in molecules that make up you. The oxygen atoms are younger, forged in stars that went supernova, scattered through space, incorporated into Earth during its formation. Carbon, nitrogen, calcium, iron, all the heavier elements. They're all made in stars, created through fusion and scattered by stellar explosions. But hydrogen is older. Hydrogen remembers the beginning, if atoms could remember. And it's not just in you. The hydrogen in your water, in the ocean, in the atmosphere, in other living things. It's all the same age. All primordial. All created in those first 3 minutes when the universe was making its first atoms. When you drink water, you're drinking something that's been recycled for billions of years. The water molecule itself might be relatively young, broken apart and reformed countless times through photosynthesis, respiration, evaporation, chemical reactions. But the hydrogen atoms in it are original, ancient, unchanged since the dawn of time. There's something profound about this, something that shifts your relationship to matter itself. You're not separate from the universe. You're made of the universe, literally made from atoms that were there at the beginning, that have been cycling through stars and planets and living things for cosmic ages, that will continue existing long after you're gone, after Earth is gone, after the sun burns out. Those hydrogen atoms will outlast everything. They're stable, essentially eternal, unless they're fused in a star or annihilated in a particle collision. They'll be around when the last stars burn out, when galaxies drift apart, when the universe becomes cold and dark. And for a brief moment, cosmologically speaking, a fraction of a second. Some of those atoms are arranged in patterns that make you, that think and feel and wonder about where they came from. You are 13.8 billion years old, in a very real sense. Parts of you, anyway. The hydrogen parts, the ancient parts that remember nothing, but have been through everything. When you look up at stars, you're seeing light from objects made of the same primordial hydrogen that's in your body. When you drink water, you're ingesting atoms that are older than Earth. When you breathe, some of the hydrogen in the water vapor you exhale has been waiting 13.8 billion years to be part of that breath. It's all connected. All the same age at the deepest level. All part of the same story that began with the Big Bang and continues now, in this moment, with you lying in darkness, made of ancient atoms arranged temporarily into consciousness, thinking about how old you really are. 13.8 billion years. Not your cells, not your body, not your memories, but your atoms, your hydrogen atoms, the oldest parts of you, the parts that were there at the beginning and will be there at the end, unchanged, ancient, patient, waiting to see what comes next. The fingerprints of koala bears are virtually indistinguishable from human fingerprints, even under a microscope. Evolution sometimes finds the same solution twice. It's called convergent evolution, when unrelated species facing similar environmental pressures or performing similar functions independently evolve similar traits. Wings in birds, bats, and insects, streamlined bodies in sharks, dolphins, and ichthyosaurs, eyes in vertebrates and cephalopods. But sometimes convergent evolution produces similarities so precise they seem impossible. Koala fingerprints are virtually indistinguishable from human fingerprints. Not similar. Not kind of alike if you squint. Indistinguishable. Even under a microscope, even to trained forensic experts, koala fingerprints and human fingerprints can be confused. They have the same whorls, the same loops, the same arches, the same ridge patterns, the same minutiae, the tiny details forensic scientists use to identify individuals. If you found a koala fingerprint at a crime scene and didn't know to look for it, you might think it was human. The patterns are that similar. This is deeply strange because koalas and humans are not closely related. Our last common ancestor lived about 160 million years ago, a small, probably nocturnal mammal that existed during the age of dinosaurs. Since then, primates evolved in one direction, eventually leading to humans. Marsupials evolved in another direction, eventually leading to koalas. 160 million years of separate evolution. Different continents, different environments, different ecological niches. Primates developed grasping hands for climbing and manipulating objects. Marsupials developed pouches for raising young. These are profoundly different lineages. And yet both independently evolved nearly identical fingerprints. Why? The answer, as far as we understand it, is grip and touch sensitivity. Fingerprints aren't decorative. They serve a function. The ridges on your fingers increase friction, improving your ability to grip objects, especially in wet conditions. They also enhance your sense of touch. The ridges amplify vibrations when you run your fingers over textured surfaces, helping you feel fine details. This is why you can tell the difference between silk and cotton just by touch. Why you can detect tiny irregularities in smooth surfaces. Why you can grip a smooth glass even when it's wet. Koalas need similar abilities. They spend their lives in trees, gripping branches, often smooth eucalyptus branches with bark that can be slippery. They need to grip securely, sometimes in rain, sometimes at angles where they're supporting their entire body weight with their hands. And they need tactile sensitivity to assess branches. Which ones are strong enough to support them? Which ones are too weak? Which leaves are the right ones to eat? So koalas evolved fingerprints independently, starting from different ancestors through different intermediate forms, arriving at the same solution, and not just any fingerprints. Fingerprints so similar to human fingerprints that they could fool an expert. This suggests that fingerprint patterns aren't arbitrary. There's probably an optimal configuration for skin ridges that maximizes both grip and tactile sensitivity. And both humans and koalas, through millions of years of trial and error, through random mutations and natural selection, found that same optimal configuration. It's like two engineers working separately, both designing the same tool, because that particular design is objectively the best solution to the problem they're trying to solve. Other primates have fingerprints too: chimps, gorillas, monkeys. That makes sense because they're closely related to us, inherited the trait from common ancestors. But koalas aren't primates. They're marsupials, as different from us as kangaroos or opossums, and yet they have fingerprints that match ours better than some primates. This raises interesting questions. Are fingerprints inevitable for any tree-dwelling animal with grasping hands? Would aliens, if they evolved hands, develop fingerprints? Maybe. If the physics of grip and tactile sensitivity are universal, if ridged skin patterns really are the optimal solution, then maybe any intelligent species with hands would develop them. Or maybe it's just a coincidence, a quirk of evolution, two separate solutions that happen to look identical, but serve slightly different functions in ways we don't fully understand yet. Either way, the similarity is remarkable. If you put a koala print and a human print side by side, Even experts have difficulty telling them apart without additional context. Size of the print, presence of claw marks, that sort of thing. But the patterns themselves, nearly identical. This caused brief concern in Australia, actually. If koalas could theoretically leave fingerprints at crime scenes that looked human, could they contaminate evidence? Could a koala climb through a window and leave prints that investigators would assume were from a person? It's unlikely, of course. Koalas don't often enter buildings, and when they do, they don't usually touch things investigators would dust for prints. But theoretically, yes, a koala could leave a print that might be mistaken for human if you didn't consider the context. There's something charming about that. The idea that somewhere in Australia, a koala might be an unwitting accomplice to a crime, leaving behind fingerprints that point to human involvement. But mostly, it's just evidence of how clever evolution can be, how it can find the same solutions independently across vast time scales in completely different lineages, how the laws of physics and biology constrain what's possible, channeling evolution towards certain outcomes even when the starting points are different. Koalas and humans both needed better grip and tactile sensitivity. Both evolved hands that could grasp, and both independently developed the same solution to improving those abilities: ridged skin on the fingertips, arranged in whorls and loops and arches that increase friction and amplify vibrations. The exact same solution arrived at separately, 160 million years after their ancestors diverged. Evolution doesn't have foresight. It doesn't plan. It just selects for what works, generation after generation, mutation by mutation, survival by survival. And sometimes, what works for one species in one environment is exactly what works for a completely different species in a completely different environment, millions of years later, on a different continent. Koala fingerprints and human fingerprints, indistinguishable, separated by 160 million years of evolution, connected by the physics of friction and the biology of touch. The same answer to the same problem, found twice. Time moves slower in stronger gravitational fields, a phenomenon called gravitational time dilation. Time is not constant. This is one of the strangest discoveries of modern physics, one of those facts that seems like it should be science fiction, but is absolutely, measurably real. Time moves at different rates depending on gravity. Einstein predicted this in his General Theory of Relativity, published in 1915. He showed that gravity isn't just a force pulling objects together. It's a curvature of space-time itself. Massive objects bend the fabric of space and time around them, and that bending affects everything, including the passage of time. The stronger the gravitational field, the slower time moves. This seems impossible. Time feels universal, absolute, the same everywhere. Seconds tick by at the same rate whether you're at sea level or on a mountain, whether you're on Earth or the moon. That's our experience, our intuition. But our intuition is wrong. Clocks at sea level run slower than clocks on mountaintops. The difference is tiny, nanoseconds per day, but it's real and measurable. Atomic clocks are precise enough to detect it. If you put one atomic clock at the base of a mountain and another at the summit, the one at the summit will run slightly faster because gravity is slightly weaker there, farther from Earth's center. This isn't a malfunction. It's not measurement error. It's time itself moving at different rates. GPS satellites have to account for this. The satellites orbit about 12,500 miles above Earth's surface, where gravity is weaker than at ground level. Time moves faster in orbit, about 45 microseconds per day, faster than clocks on the ground. If GPS didn't correct for this, the system would accumulate errors of about 10 kilometers per day, making navigation useless. So GPS satellites run clocks that are adjusted to tick slightly slower than they naturally would, compensating for the faster passage of time in weaker gravity. Without this correction, the system fails. This is gravitational time dilation, and it's not theoretical. It's engineering. It's built into systems we use every day. The effect gets more dramatic in stronger gravity. On the surface of the Sun, where gravity is about 28 times stronger than Earth's, time moves about 2 parts per million slower. Over a year, a clock on the Sun would lose about a minute compared to a clock floating in deep space far from any gravitational field. Near a black hole, the effect becomes extreme. Close to the event horizon, where gravity is intense beyond anything we experience normally, time slows to a crawl relative to distant observers. An astronaut falling toward a black hole would experience time normally from their own perspective. Their heart would beat regularly, thoughts would flow at normal speed, everything would feel fine. But to someone watching from a safe distance, the astronaut would appear to slow down as they approached the event horizon. Their movements would become sluggish. Their fall would appear to take forever. Their clock would tick slower and slower. They would seem to freeze at the event horizon, never quite crossing it, though from the astronaut's perspective, they'd cross and fall in quickly. This is one of the strange predictions of relativity. Observers in different gravitational fields don't agree on the passage of time. It's not that one clock is wrong and the other right. Both are correct from their own reference frame. Time genuinely passes at different rates in different gravitational fields. This has been tested countless times. Atomic clocks flown on airplanes, satellites in orbit, experiments with particles in accelerators, all confirm that time dilation is real. Einstein's equations predict the effects precisely, and measurements match the predictions. It's not just gravity that affects time, velocity does too. This is special relativity, the theory Einstein published in 1905 before general relativity. Objects moving at high speeds experience time more slowly than stationary objects. Particles created in accelerators live longer than they should because they're moving so fast that time slows down for them. Both effects are real, both happen, and sometimes they work together. GPS satellites experience both. Time speeds up because of weaker gravity, general relativity, but slows down because of their orbital velocity, special relativity. The gravitational effect is larger, so the net result is that time in orbit runs faster than on the ground, but both effects have to be accounted for. This breaks our intuition about time as a universal backdrop, a stage on which events occur at the same rate everywhere. Instead, time is flexible, variable, dependent on gravity and motion. It's part of space-time, woven together with the 3 dimensions of space into a 4-dimensional fabric that can bend and stretch and warp. You experience this right now, though the effect is too small to notice. Your head is farther from Earth's center than your feet, so it's in a slightly weaker gravitational field. Time passes slightly faster for your head than your feet, about 90 nanoseconds per year, roughly the time it takes light to travel 90 feet. You'll never notice this, It's far too small, but it's real. Your head is aging slightly faster than your feet. Over a lifetime, the difference accumulates to less than a microsecond, meaningless in practical terms. But philosophically, it's profound. You are not experiencing time uniformly across your own body. Different parts of you are moving through time at slightly different rates. This is the universe we live in, not the Newtonian universe of absolute space and time, where clocks everywhere tick at the same rate, and simultaneity is universal. We live in Einstein's universe, where time is relative, where gravity bends space-time, where observers in different conditions can't even agree on what now means. It's strange, counterintuitive, difficult to reconcile with everyday experience. But it's real. Satellites prove it every day. Atomic clocks prove it. Particle physics proves it. The universe doesn't care what we find intuitive. Time is relative. Gravity affects it. The stronger the gravity, the slower the time. And somewhere, near a black hole, time is moving so slowly that an outside observer would see it nearly stop, though to someone there, experiencing it directly, time would feel perfectly normal, perfectly regular, exactly like it's always been. Clocks ticking, moments passing, time flowing forward, just slower or faster, depending on where you stand. The mantis shrimp can punch with the acceleration of a .22 caliber bullet and see colors we can't even imagine. There are creatures on Earth that experience reality in ways we can't comprehend. The mantis shrimp is one of them. Let's start with the punch. Mantis shrimps are not actually shrimp. They're stomatopods, marine crustaceans only distantly related to true shrimp. They're about 4 to 6 inches long, brightly colored, and hiding in burrows or crevices in tropical waters. They look almost harmless, decorative even, with patterns in greens and blues and oranges that seem designed to be beautiful rather than threatening. But they have clubs, or spears, depending on the species. Modified front appendages that fold beneath their bodies and can strike with ridiculous speed and force. When a mantis shrimp strikes, its club accelerates at about 10,400 Gs. That's 10,400 times the acceleration due to gravity. The club reaches speeds of around 50 miles per hour in water, which is incredibly fast given the resistance water provides. The strike happens in about 3 milliseconds, faster than you can blink, faster than most high-speed cameras can capture without special equipment. The acceleration is comparable to a .22 caliber bullet. Not the speed, the bullet moves much faster, but the rate of acceleration, the g-forces involved, are similar. This strike is so fast, so forceful, that it creates cavitation bubbles in the water, areas where the pressure drops so low that water vaporizes momentarily, creating bubbles of water vapor. When these bubbles collapse, they produce secondary shock waves and brief flashes of light called sonoluminescence. The mantis shrimp hits so hard, it literally boils the water around its strike, creating shock waves that can kill or stun prey, even if the initial strike misses. The club itself is a marvel of biological engineering. It's made of layers of different materials, calcium carbonate minerals arranged in a helical structure that prevents cracks from propagating, similar to how fiberglass works. The surface is one of the hardest biological materials known, harder than most mollusk shells, hard enough to crack aquarium glass if the shrimp strikes it. They use this punch to smash open the shells of crabs, snails, and other hard-bodied prey. One strike, and the shell shatters. Or they use it to kill fish with the shockwave, stunning them for easy capture. Some species have spear-like appendages instead of clubs, and they use these to impale soft-bodied prey like fish, piercing through scales and flesh with the same incredible speed. But the really alien part of mantis shrimp isn't the punch, it's the vision. Human eyes have 3 types of color receptors, cones that detect red, green, and blue light. We combine signals from these 3 receptors to create our perception of color. Dogs have 2 types, which is why they see fewer colors than we do. Birds have 4 types, which is why they can see colors we can't, including into the ultraviolet range. Mantis shrimp have 16 types of color receptors. 16. Let that sink in for a moment. We have 3 and can distinguish millions of colors. They have 16. The range of colors they can perceive is literally beyond our ability to imagine, because we don't have the neural architecture to process that much color information. They can see into the ultraviolet range. They can see into the infrared range. They can see circular polarized light, which humans can't detect at all without special equipment. Each eye can move independently, giving them complete control over what each eye looks at. And each eye has 3 separate areas for processing depth perception, meaning they can judge distance with a single eye, something most animals can't do. Their color vision doesn't work the way ours does, though. Researchers initially thought that with 16 color receptors, mantis shrimp would have incredibly precise color discrimination, able to detect the tiniest differences in wavelength, seeing gradations we couldn't dream of. But testing showed something strange. Mantis shrimp are actually not great at distinguishing similar colors. They can differentiate colors that are quite different, but struggle with subtle shades that humans can easily tell apart. The current theory is that their vision system works differently than ours. Instead of comparing signals from different receptors to compute color the way we do, each of their 16 receptors might respond to a specific narrow band of wavelength. This would make color recognition faster. They wouldn't need to process and compare signals, just identify which receptor fired, but less precise for subtle gradations. It's a completely different approach to vision, optimized for speed rather than precision, which makes sense for an animal that needs to rapidly identify prey or threats while also coordinating incredibly fast strikes. So the mantis shrimp sees a world we can't imagine, full of colors that don't exist in human experience, detecting polarized light patterns that are invisible to us, processing visual information in ways that seem alien because they literally are alien, evolved independently, optimized for different needs, built on different principles, and it can punch with the force of a bullet, creating cavitation bubbles and shock waves, shattering shells, stunning fish, all in 3 milliseconds. It's about 6 inches long, lives in burrows, looks like a colorful little creature that should be harmless. But it experiences reality in ways we can barely conceive, sees colors we've never seen, can't see, don't have words for, strikes faster than we can blink with more force than we can generate with our entire bodies. The mantis shrimp is a reminder that Earth contains other forms of consciousness, other ways of perceiving the world, other sensory experiences that are completely inaccessible to us. We share a planet with creatures that might as well be from different dimensions, experiencing light and color and time in ways that make our own perception seem limited, narrow, just one possibility among many. 16 color receptors, a punch that boils water, vision into ultraviolet and infrared, polarization detection, independent eye movement, all in a creature 6 inches long, hiding in tropical waters, looking beautiful and harmless until it strikes. The ocean contains multitudes, and the mantis shrimp, small and strange, and impossible to fully comprehend, is one of them. There are more possible iterations of a chess game than there are atoms in the observable universe. Chess looks simple from the outside, a board with 64 squares, 32 pieces, each moving according to fixed rules, black and white taking turns, no randomness, no hidden information, no luck, just two players thinking, planning, trying to outmaneuver each other. And yet the number of possible chess games is so large, it defies comprehension. After just one move by each player, white moves, black responds, there are 400 possible board positions. After 2 moves each, there are 72,084 positions. After 3 moves each, about 9 million positions. The number grows exponentially, exploding into absurdly large numbers very quickly. The Shannon number, named after Claude Shannon, the mathematician who first calculated it, estimates the number of possible chess games at around 10,120. That's 10 followed by 120 zeros. A number so large it has no common name, no intuitive referent. To put this in perspective, the observable universe contains approximately 1080 atoms. That's already an incomprehensibly large number. Every atom in every star, every planet, every gas cloud, every bit of matter we can detect in all directions as far as we can see. But 10,120 is vastly larger. It's 1040 times more than the number of atoms in the observable universe. You could count every atom in every star in every galaxy, then multiply that by 10,000 trillion, and you still wouldn't reach the number of possible chess games. This seems impossible. How can a game with such simple rules produce this much complexity? The answer is combinatorial explosion. Every move creates a branching point. Each branch creates more branches. After a few moves, the tree of possibilities becomes vast beyond comprehension, even though each individual move is simple and deterministic. On average, there are about 35 legal moves available in a typical chess position. Not all of them are good moves, but they're legal. They follow the rules. Each of those moves leads to a new position, each of which has about 35 more legal moves, and so on. The number of possible games grows as roughly 35 to the power of n, where n is the number of moves. An average chess game lasts about 40 moves per side, so about 80 plies total. A ply is a single move by one player. That gives you 3580 possible games, which is in the ballpark of the Shannon number. Of course, many of these games are nonsensical, random moves that no competent player would make. Many are illegal due to rules like not being allowed to move into check. And many are effectively identical in strategic terms, even if the exact sequence of moves differs. But even if we filter for only reasonable games, only strategic games, only games that grandmasters might actually play, the number remains astronomical. There are more good chess games than could ever be played by all humans who have ever lived, working continuously for the entire history of the universe. This is why chess remains interesting, why it hasn't been solved the way simpler games have been, why new strategies emerge even after thousands of years of people playing. The possibility space is too large to exhaust, too complex to fully map. Computers have changed chess dramatically. Modern chess engines can calculate millions of positions per second, can search deeper into the game tree than any human. They play at a level no human can match. But even the best computers can't solve chess completely, can't analyze every possible game, can't reduce it to a formula where you always know the perfect move. There are too many branches, too many possibilities, too much complexity hidden in those simple rules. The best we can do is search a few moves ahead, evaluate positions based on heuristics and experience, and make educated guesses about which moves lead to favorable outcomes. Even computers do this. They use sophisticated evaluation functions and pruning techniques to avoid searching hopeless branches. But they're still estimating, still choosing based on incomplete information about the full game tree. This is true of many complex systems. Simple rules can generate infinite complexity. The game of life, a cellular automaton with just 4 simple rules, can produce patterns that no one has fully cataloged, behaviors that emerge unexpectedly even after decades of study. Fractals are generated by simple equations repeated iteratively, but they contain infinite detail, infinite variation. The universe itself might be this way. Relatively simple physical laws, gravity, electromagnetism, the strong and weak nuclear forces, applied across billions of years, generating galaxies and stars and planets and chemistry and life and consciousness, all from initial conditions and basic rules, complexity emerging from simplicity, vastness hiding in small spaces, a chessboard, 64 squares, 32 pieces, and more possible games than atoms in the universe. You could play chess every second for the age of the universe, 13.8 billion years, and barely scratch the surface of what's possible. Every game ever played, every tournament, every casual match, every computer simulation, all of it together represents a tiny, infinitesimal fraction of the full possibility space. There are chess games waiting to be played that no one has ever seen, that no one will ever see, positions that will never occur in the entire future history of the game. Beautiful combinations that exist mathematically but will never be discovered. Strategies that would work but will never be tried. And this is just chess. Just one game with simple rules, played on a small board. Imagine what other complexity is hiding in seemingly simple systems. What other vast spaces exist, unexplored, in the possibilities generated by basic rules and simple components. The universe is larger on the inside than it appears from the outside. Chess proves it. 64 squares, an infinity. The placebo effect works even when people know they're taking a placebo. There's something strange about belief in the body. Something that doesn't fit neatly into our models of how medicine works. For decades, we've known about the placebo effect, the phenomenon where patients improve after receiving treatments with no active ingredients. Sugar pills, saline injections, fake surgeries where doctors make incisions but don't actually do anything. And patients get better. Not all of them. Not every time, but enough that it's measurable, significant, real. The standard explanation was belief. Patients thought they were receiving real treatment, so their brains triggered healing responses. Expectation became reality through some mechanism we don't fully understand. Perhaps stress reduction, perhaps immune system activation, perhaps changes in how the brain processes pain signals. This made sense. Belief is powerful. Hope is powerful. If you think you're being treated, your body might respond accordingly, even if the treatment is fake. But then researchers tried something that seemed like it shouldn't work. They gave patients placebos and told them they were placebos, explicitly. This is a sugar pill. It contains no active medication. It should not work based on any pharmacological mechanism. And the patients got better anyway. In studies of chronic pain, irritable bowel syndrome, depression, and other conditions, patients who knowingly took placebos, who were fully informed that what they were taking had no medical ingredients, still showed measurable improvement. Not as much improvement as with active medications in some cases, but more improvement than patients who received no treatment at all. This shouldn't work. If the placebo effect depends on belief, then knowing you're taking a placebo should eliminate the effect. You can't believe something will work when you know it's fake, can you? Apparently, you can. Or more precisely, belief isn't the whole story. The current theories suggest several mechanisms might be at play. One is conditioning. If you've been conditioned throughout your life to associate taking pills with feeling better, your body might respond to the ritual of pill taking even when you consciously know the pill is inert. It's like Pavlovian conditioning, but with medicine instead of bells and food. Your brain has learned, take pill, feel better. It doesn't necessarily matter what the pill contains. The act of taking it, the ritual, the context, triggers physiological responses that were learned through previous experiences with real medication. Another theory involves attention and care. Clinical trials where placebos work involve regular check-ins with healthcare providers, attention to symptoms, someone listening and taking your concerns seriously. This context, being cared for, being monitored, being taken seriously, might itself have therapeutic effects independent of any specific treatment. Some researchers think it's about expectation at a level deeper than conscious belief. You might consciously know the pill is fake, but some part of your brain still expects the ritual of medicine to produce healing. That expectation, even when contradicted by conscious knowledge, might be enough to trigger physiological changes. The mind-body connection is more complex than we thought. We can't simply divide experience into mental and physical with clean boundaries. Pain is physical, but it's also processed by the brain, interpreted, given meaning. Stress is psychological, but it produces measurable changes in immune function, inflammation, healing rates. When you take a pill, even a sugar pill you know is fake, you're engaging in a ritual that carries meaning. You're doing something active about your condition rather than passively suffering. You're participating in your care. You're in a context where healing is expected, where people are trying to help you, where improvement is possible. And somehow, all of that matters. Somehow, the context and ritual and expectation produce real physiological changes, even when you consciously know the treatment should be inert. This has huge implications for medicine. It suggests that how we deliver treatment matters as much as what treatment we deliver. That the therapeutic relationship between doctor and patient isn't just about diagnosis and prescription, but contains healing potential in itself. That bedside manner, attention, compassion, things we often think of as nice but not medically necessary, might actually be part of the treatment. It also complicates clinical trials. When testing new medications, we give some patients the real drug and others a placebo to control for the placebo effect. But if placebos work even when people know they're placebos, what does that mean? How do we measure the specific effect of the medication versus the effect of the clinical trial context itself? Some researchers are now studying open-label placebos, explicitly telling patients they're receiving placebos and observing the effects. Early results suggest this could be a legitimate treatment option for some conditions. Give people sugar pills, tell them honestly what they are, and some people still get better. It's almost like magic, except it's not. It's biology and psychology interacting in ways we don't fully understand, where consciousness and physiology aren't separate systems, but deeply intertwined, where what you know and what you believe and what you experience all feed back into each other in complex loops. Your body responds to meaning, to context, to ritual, even when your conscious mind knows better. This doesn't mean real medication doesn't work. Antibiotics cure infections. Chemotherapy kills cancer cells. Surgery repairs damaged tissues. Medical science is real and effective, but it does mean that healing is more than just biochemistry, that the experience of being treated, of being cared for, of engaging in rituals of healing produces effects we can measure even when the treatment itself is inert. The placebo effect isn't just about fooling people. It's about activating the body's own healing mechanisms through context and expectation and meaning. And those mechanisms work, at least partially, even when you're not fooled, even when you know exactly what's happening. Your brain is powerful. Your body is responsive. The boundary between mind and body is blurrier than we like to think, and sometimes knowing you're taking a sugar pill is enough. The ritual matters. The context matters. The act of doing something, of trying, of participating in your own care, that matters. Not for everything, not for all conditions, but for some things, sometimes, it's enough. A sugar pill. No active ingredients. Complete transparency. And people get better anyway. The placebo effect working in plain sight, even when the magic trick is explained. Quantum particles can be in multiple states simultaneously until observed, a property called superposition. Reality is not what it seems. This sounds like a philosophical statement, something abstract and debatable. But in quantum mechanics, it's literally true, measurably true, verified by thousands of experiments over nearly a century. Quantum particles, electrons, photons, atoms, can exist in multiple states at the same time until you measure them. This isn't about uncertainty in our knowledge. It's not that the particle is in one state but we don't know which one. The particle genuinely exists in multiple states simultaneously, a superposition of possibilities that collapses into a single, definite state only when observed. This is superposition, and it's one of the most counterintuitive concepts in physics. Imagine flipping a coin but never letting it land. While it's in the air, spinning, is it heads or tails? You might say it's one or the other, we just don't know yet. The coin has a definite state, heads or tails, but that state is hidden from us until it lands and we look. Quantum particles don't work that way. A quantum particle in superposition isn't secretly heads or tails. It's both, simultaneously. Actually both, not just unknown. The particle exists in a state that combines both possibilities until something forces it to choose. The classic demonstration is the double-slit experiment. You shoot particles, photons or electrons, at a barrier with two slits. Behind the barrier is a screen that detects where the particles hit. If particles are little bullets that go through one slit or the other, you'd expect two bands on the screen, one behind each slit. But that's not what happens. Instead, you get an interference pattern, multiple bands, light and dark, exactly like what you'd see if you sent waves through the slits. This suggests the particle somehow goes through both slits simultaneously, interfering with itself like a wave, then hits the screen as a localized particle. It's behaving as both wave and particle, spread out through space in superposition until it hits the detector. But here's where it gets truly strange. If you put detectors at the slits to see which slit each particle goes through, the interference pattern disappears. Simply observing which path the particle takes forces it to choose one slit, collapsing the superposition, and you get two bands instead of the interference pattern. The act of observation changes the outcome, not because observation disturbs the particle mechanically, but because observation forces the particle to have a definite state. Before observation, it's in superposition, going through both slits in some sense. After observation, it went through one slit or the other. This has been verified countless times, with increasingly sophisticated experiments. Particles do behave this way. Superposition is real. What does it mean? Nobody knows for certain. There are interpretations, different ways of thinking about what's happening, but no consensus on which interpretation is correct. The Copenhagen interpretation says particles don't have definite properties until measured. Reality is fundamentally probabilistic, and measurement collapses the wave function, forcing the particle into one state or another. The many worlds interpretation says every possibility happens, but in different branches of reality. When you measure a particle in superposition, the universe splits. In one branch, you see one outcome. In another branch, you see the other, and both versions of you exist in separate but equally real universes. Other interpretations involve pilot waves, or consciousness causing collapse, or retrocausality, or various other exotic ideas. All of them match the experimental data, and we have no way to definitively test which interpretation is correct. What we know is the math works. Quantum mechanics makes predictions about probabilities, about where particles will be detected, about how systems evolve, and those predictions are confirmed with extraordinary precision. It's one of the most successful theories in physics, accurate to more decimal places than almost any other scientific theory. But it describes a reality that's fundamentally weird, where particles can be in two places at once, where observation isn't just passive recording, but active participation in determining what's real, where the line between possibility and actuality is blurry, conditional, dependent on measurement. This isn't just theoretical, it's the foundation of modern technology. Quantum mechanics explains how semiconductors work, how lasers work, how atomic clocks work. It's essential to understanding chemistry, the structure of atoms, the behavior of materials. And emerging quantum technologies, quantum computers, quantum cryptography, quantum sensors, depend on superposition and other quantum effects to function. We're building devices that exploit the fact that particles can be in multiple states simultaneously. Quantum computers use quantum bits, qubits, that are 0 and 1 at the same time, performing calculations on superposed states that collapse into answers when measured. It sounds like magic, but it's engineering based on well-tested physics. Still, the implications are unsettling. If particles don't have definite properties until measured, what does that say about reality? Are we creating reality by observing it? Or is reality already there, just described by probabilities until we look? Does a tree falling in a forest make a sound if nobody's there to hear it? In classical physics, obviously, yes. In quantum mechanics, it depends on what you mean by sound, and there and here. The question becomes genuinely ambiguous. At the quantum level, things don't have definite positions until measured. They're spread out, probabilistic, existing in superposition of all possible locations weighted by probabilities. Only when you detect the particle, force it to interact with a measurement device, does it localize, does it decide where it is. And yet somehow, this quantum weirdness averages out at larger scales. Tables and chairs and people don't exist in superposition. They have definite positions, definite properties. Quantum effects become negligible as systems get bigger. A process called decoherence, where interactions with the environment effectively measure the system constantly, collapsing superpositions before they can accumulate into observable effects. But at the smallest scales, at the foundation of reality, things are probabilistic, uncertain, superposed until observed. A particle can be in two places at once, or it's neither here nor there until you look, or it's in all possible places simultaneously with different probabilities. Or the universe splits, and it's in one place in this universe, and another place in another universe, and both are real. We don't know which description is true. We know the math works. We know the experiments confirm it. We know superposition happens, but what it means, what it says about the nature of reality, remains one of the deepest mysteries in physics. A particle in superposition is neither this nor that, or both this and that, or potentially this or that, or all of these descriptions simultaneously depending on how you think about it. Maybe the universe is content being undecided. Maybe at the deepest level, reality is possibility rather than actuality, and only observation, measurement, interaction forces it to choose. Or maybe our concepts, particle, position, state, are just inadequate for describing what's really happening at scales where quantum effects dominate. Either way, particles exist in superposition. They're in multiple states at once until something forces them not to be. And somehow, from this weirdness, from this fundamental uncertainty at the quantum level, emerges the solid, definite, seemingly certain world we experience every day. How that happens, how quantum superposition averages out to classical reality, is still being worked out. But it does happen, somehow. And at the foundation of everything, reality is less solid than it appears, more probabilistic, more strange, more willing to be multiple things at once, until forced to choose. The human body emits visible light, but it's about 1,000 times less intense than what our eyes can detect. You glow, not metaphorically, not poetically, literally. You emit visible light right now, photons streaming off your body at every moment. You've always been glowing. Since birth, throughout your entire life, you've been a source of light. You just can't see it. The light you emit is bioluminescence, though not the kind you find in fireflies or deep-sea fish. Those creatures produce light through specialized chemical reactions, using proteins like luciferase, to convert chemical energy into photons efficiently enough to be visible. Your light is different, weaker. It comes from metabolic processes, the countless chemical reactions happening in your cells, producing reactive oxygen species and other molecules that sometimes emit photons as byproducts. It's not evolutionarily designed for any purpose. It's just a side effect of being alive, of chemistry happening at body temperature, of energy transforming and occasionally leaking out as visible light. Scientists in Japan used extremely sensitive cameras to detect this light. Not infrared radiation, that's heat. And yes, you emit plenty of infrared as your body maintains its temperature. This is visible light, photons in the wavelengths we could see if they were bright enough. But they're not bright enough. Your body's glow is about 1,000 times less intense than the threshold of human vision. The intensity varies throughout the day, following a circadian rhythm. You glow brightest in the late afternoon, around your mouth and cheeks, dimmest in the morning. The pattern suggests it's linked to metabolic activity, to the daily rhythms of cell function, though we don't fully understand why the timing works out this way. The color is mostly in the green to red range, with some blue, corresponding to the energy levels of the chemical reactions producing the photons. It's not dramatic, not the vivid bioluminescence of jellyfish or the bright flash of fireflies. It's subtle, faint, invisible to our eyes, but detectable with sensitive instruments. This happens in all animals, probably. Anything with metabolism, with chemical reactions running at biological temperatures, likely emits low levels of visible light. We've just never seen it because evolution didn't optimize our eyes for detecting such faint signals. We're built to see sunlight, reflected light, things orders of magnitude brighter than our own glow. But it raises interesting questions. If we had different eyes, more sensitive eyes like some deep-sea creatures have, would we see each other glowing? Would a dark room never be truly dark, filled instead with the faint light of living bodies, a gentle glow from every person present? Maybe in such a world, darkness would feel different, less absolute. You'd always see at least the outline of people nearby, glowing faintly, metabolizing, alive. There's something beautiful about this fact. You're not just a collection of matter, not just atoms arranged in particular ways. You're active, dynamic, constantly undergoing chemical transformations that release energy. Some of that energy escapes as light, as photons carrying away the excess from reactions that keep you alive. You're a little furnace, burning fuel, producing heat and light and motion. The heat you feel and use to maintain body temperature. The motion you experience as life, as movement, as the work of staying alive. And the light you emit but never see, radiating outward at every moment, too faint to notice but absolutely real. It's not much light. If you were in perfect darkness with perfectly sensitive eyes, you still probably couldn't see yourself glowing. The intensity is just too low, scattered across the entire surface of your body, never concentrated enough to overcome the noise of your visual system. But it's there, has always been there, will be there as long as you're alive and metabolizing. When you die, the light fades. The chemical reactions slow, stop. The glow disappears. In this very subtle sense, the metaphor of life as light is literally true. While you live, you shine, however faintly. When life ends, the light goes out. This is true for all living things. Plants glow faintly as they metabolize. Animals glow. Bacteria, probably, though they're so small and dim it would be nearly impossible to detect. The entire biosphere is glowing, invisibly, constantly, a gentle radiation of photons that represents the chemical activity of life itself. You're part of that glow, contributing your share of photons to the universe, light that travels away from you at 186,082 miles per second, carrying energy away from the chemical reactions in your cells. Some of those photons might travel far before being absorbed, across rooms, across fields, into space if they happen to head upward and avoid obstacles. They're part of the electromagnetic radiation filling the universe, indistinguishable from other photons, carrying no information about their origin, just pure light, moving at light speed until something absorbs them. You are always emitting light, always contributing photons to the universe, a tiny source, overwhelmed by sunlight during the day, by artificial light at night, by moonlight, starlight, any other source bright enough to matter. But in perfect darkness, with perfect instruments, you could be detected by your glow. Your living, metabolizing body, producing faint, visible light as a byproduct of staying alive. There's something poetic in that, something that makes the phrase inner light feel less metaphorical. You do have an inner light, in the most literal sense. It's just very, very dim, but it's real, measurable, a consequence of chemistry and life, and the fact that reactions sometimes produce photons as they proceed. You glow, always have, always will, as long as you're alive. Too faint to see, but bright enough to measure, a living source of light, however small, shining in darkness, invisible but real. If you could fold a piece of paper 42 times, it would reach the moon. Exponential growth is counterintuitive. We're not built to understand it instinctively. We think linearly, twice as much, 3 times as much, 10 times as much. Addition feels natural. Multiplication feels manageable. But exponential growth, where each step multiplies rather than adds, that breaks our intuition quickly. Consider a piece of paper. Standard printer paper is about 0.1 millimeters thick. Fold it once, and it's 0.2 millimeters thick. Fold it twice, 0.4 millimeters. 3 times, 0.8 millimeters. This seems reasonable, linear almost. You're roughly doubling the thickness each time, but the actual thickness is still small. After 3 folds, you're still under a millimeter. Keep going. After 7 folds, you're at about 1.3 centimeters, roughly half an inch. Still manageable. You could hold this in your hand, but you can't actually fold a piece of paper 7 times. The physical constraints, the bending radius, the number of layers, the material properties, make it impossible with normal paper. Brittle Gallivan, a California high school student, famously managed 12 folds using a very long piece of thin gold foil and a mathematical model she developed for predicting folding limits. But even that required special materials and conditions. So this is a thought experiment. If you could fold paper 42 times, ignoring physical impossibility, what would happen? The thickness doubles with each fold. So after n folds, the thickness is 0.1 millimeter times 2n. After 10 folds, about 10 centimeters, or 4 inches. After 20 folds, about 105 meters, or 344 feet. Taller than a 30-story building. After 30 folds, about 107 kilometers, or 67 miles. Higher than commercial airplanes fly. After 40 folds, about 110,000 kilometers, or 68,000 miles. More than a quarter of the way to the moon. After 42 folds, about 439,805 kilometers, or 273,000 miles. The moon's average distance from Earth is about 384,400 kilometers, or 2 1/38 miles. 42 folds would get you past the moon. This seems impossible. 42 doesn't sound like a large number. You could count to 42 in less than a minute. But exponential growth turns small numbers of steps into enormous distances. Each fold doubles. Start with 1/10 of a millimeter, essentially nothing, and double it 42 times, and you've traveled to the moon. This is the power of exponential growth, the thing that makes compound interest work, that makes populations explode, that makes pandemics spread faster than we expect, that makes technology accelerate in ways that surprise us. We see this pattern in Moore's law, the observation that computer processing power roughly doubles every 2 years. Start with computers from the 1970s, room-sized machines with less power than a modern calculator, and double their power 25 times over 50 years, and you get smartphones, AI devices, millions of times more powerful than the original machines. We see it in information storage. The first hard drives held kilobytes. Modern drives hold terabytes, billions of times more capacity, achieved through decades of doubling and doubling again. We see it in viral spread. One person infects 2. Those 2 infect 4. 4 becomes 8. 8 becomes 16. After 20 generations of doubling, which might take only a few weeks, depending on the disease, one initial infection has become over 1 million cases. After 30 generations, over 1 billion. The early stages look slow. 1 fold, 2 folds, 3 folds. You're still dealing with millimeters. 1 infection, 2 infections, 4 infections seems manageable. But the growth is relentless, and the later stages are explosive. By the time you realize how fast things are accelerating, you're already past the moon. This is why exponential problems are dangerous. They look harmless at first. Linear thinking says, we have time, the numbers are still small. But exponential growth doesn't respect that intuition. It accelerates regardless, each step larger than all previous steps combined. After 41 folds, your paper is about 220,000 kilometers thick. The 42nd fold adds another 220,000 kilometers, doubling the total. That single fold, the last one, adds as much height as all previous folds combined. That's the signature of exponential growth. Each step equals the sum of all previous steps. The most recent doubling always contains as much growth as the entire history before it. You can apply this to almost anything that grows multiplicatively. Bacteria colonies, where each cell divides into 2. Compound interest, where each year's interest earns interest in future years. Chain reactions, where each event triggers multiple future events. All of them follow this pattern. Slow start, deceptive middle period where growth looks linear, then sudden explosion into numbers too large to conceptualize. 42 folds to the moon. It sounds like magic, like the kind of exaggeration people make for effect, but it's just math. Just exponential growth applied consistently. Start small, double, double again. Keep doubling. 42 times. And suddenly you're reaching across space, spanning distances that normally require rockets and years of planning, all from folding a piece of paper that starts out 1/10 of a millimeter thick. The universe allows this, encourages it even. Exponential growth is everywhere, in populations, in technologies, in physical processes. It's fundamental to how things scale, how small changes accumulate into large effects. But we don't see it coming, can't intuitively grasp it. Think it's safe when we're at fold 7 and the paper is only 1/2 inch thick. We're bad at exponential thinking, bad at seeing where the doubling leads, bad at respecting the power of consistent multiplication. 42 folds. 10 minutes of folding, if it were physically possible, and you'd have built a tower to the moon from paper. All because each step doubles, and doubling, repeated enough times, can take you anywhere. The Great Pyramid of Giza was built with such precision that its base is level to within 2 centimeters across its 230-meter width. There's something haunting about precision achieved without modern tools. The Great Pyramid of Giza was built around 4,500 years ago during Egypt's 4th dynasty, probably during the reign of Pharaoh Khufu. It was constructed from approximately 2.3 million stone blocks, each weighing between 2.5 and 15 tons, fitted together so tightly that you can't slip a credit card between many of them. And the base, a square with sides each 230 meters long, about 755 feet, is level to within 2 centimeters across its entire width. 2 centimeters, less than an inch, across a base the length of 2.5 football fields. Think about what that means. You'd need to survey the ground, remove irregularities, create a level platform of bedrock or carefully laid foundation stones, all with consistent elevation across hundreds of meters. And you'd need to do this without laser levels, without GPS, without digital measuring tools, without any of the precision instruments we take for granted in modern construction. How did they do it? We don't know for certain. The Egyptians left no construction manual, no detailed technical documentation. What we have are the pyramids themselves, their precision speaking to methods we can only infer. The most likely technique involves water. Water seeks level naturally, controlled by gravity. If you create channels or trenches in the bedrock and fill them with water, the water surface will be perfectly level, giving you a reference plane you can measure against. You could dig trenches in a grid pattern across the pyramid site, fill them with water, mark the water level on the walls of the trenches, drain them, and then cut the bedrock to match those marks. Repeat this process carefully, and you can create a level platform accurate to within centimeters across hundreds of meters. It's simple in concept but demanding in execution. You'd need careful surveying, consistent measurements, skilled workers, and time, lots of time, to cut and shape bedrock with copper tools and stone pounders. But it's possible, achievable with technology available 4,500 years ago. It just requires patience, skill, and extraordinary attention to detail. The pyramid's orientation is also remarkable. Its sides align almost perfectly with the cardinal directions: north, south, east, west. The alignment is accurate to within a few arc minutes, which is astonishingly precise. Some researchers believe they used stellar observations, possibly tracking the circular path of stars around the celestial pole to find true north. Ancient astronomers were sophisticated. They understood the sky, tracked celestial movements, could predict eclipses and seasons. Using stars to orient a massive structure would have been within their capabilities, especially if they had years to observe and measure. The internal passages and chambers also show precision. The Grand Gallery, a corbelled passage leading to the King's Chamber, has walls that rise at exactly 26 degrees over 47 meters of length. The King's Chamber itself is built from granite blocks weighing up to 80 tons each, transported from Aswan over 800 kilometers away, then lifted into place about 60 meters above ground level. How they lifted these blocks is still debated. Ramps, probably. Either straight ramps, zigzagging ramps, or spiral ramps, wrapping around the pyramid as it rose. Each method has advantages and problems. We've found no definitive evidence for exactly which approach was used, though remnants of ramps have been found at other pyramid sites. What's clear is that the precision wasn't accidental. The Egyptians were capable engineers, sophisticated mathematicians, skilled surveyors. They understood geometry, could calculate volumes and weights, could plan massive projects, and execute them over decades. The Great Pyramid took perhaps 20 years to build, involving thousands of workers. Not slaves, as popular imagination often assumes, but paid laborers, probably working in rotating shifts, supported by a massive infrastructure of food production, tool manufacturing, and logistics. It's estimated that to complete the pyramid in 20 years, workers would need to place a block every 2 to 3 minutes during daylight hours, every day for 2 decades. That's a logistical achievement as impressive as the engineering, coordinating that many people, that much material, maintaining quality and precision while working at such a pace. And yet they did it. The pyramid stands as evidence. 2.3 million blocks fitted together, base level to within 2 centimeters, sides aligned to cardinal directions, internal chambers precisely placed and constructed, all with Bronze Age technology and human labor. It's not supernatural. It doesn't require aliens or lost ancient super technology. It requires skilled workers, good planning, sophisticated understanding of engineering and mathematics, and time. But that makes it more impressive, in a way. This was human achievement, human capability, human patience and skill. People who lived 4,500 years ago without computers or electricity or power tools built something so precisely that modern engineers are impressed. The pyramid has survived because of that precision, because the blocks fit tightly, because the foundation is solid and level, because the geometry is sound. It's outlasted empires, outlasted the civilization that built it, outlasted 45 centuries of earthquakes and weather and human interference. Much of the outer casing is gone now. Smooth white limestone that once covered the entire structure, giving it a bright, polished appearance, was removed over centuries and used for other buildings in Cairo. What remains is the stepped core, rough but stable, still standing, still level, still precisely aligned. And that base, 230 meters square, level to within 2 centimeters, remains a testament to what humans can achieve with simple tools, deep knowledge, and meticulous care. 2 centimeters of error across 230 meters. In modern construction, with laser levels and computerized surveying, we can do better, but not much better. And we have advantages the Egyptians lacked: precision instruments, power tools, thousands of years of accumulated engineering knowledge. They had copper tools, stone, rope, wood, water, and human labor. And they created something level to within 2 centimeters across the length of 2 football fields. 4,500 years ago. Still standing, still level, still precise. A monument not just to Khufu, not just to ancient Egypt, but to human capability itself, what we can accomplish when we combine skill, knowledge, organization, and patience. The Great Pyramid, level to within 2 centimeters, built without modern tools, enduring across millennia. Still there, still impressive, still reminding us that ancient people were not primitive, not ignorant, not less capable than us, just working with different tools toward different goals, achieving precision we still respect today. Your brain generates about 12 to 25 watts of electricity, enough to power a low-wattage LED light. Inside your skull, right now, there's electricity flowing. Not metaphorical energy, not the spark of inspiration or the fire of thought. Actual electricity, electrons moving, voltage differences across membranes, electrical signals propagating through networks of neurons at measurable speeds with measurable power. Your brain operates on about 12 to 25 watts, depending on how active you are, how hard you're thinking, whether you're awake or asleep. That's roughly the same amount of power as a compact fluorescent bulb, or several LED lights, or a laptop computer running on battery saver mode. It's not much power in absolute terms. A hairdryer uses 1/500 watts. A microwave uses 1,000 watts. Your entire body, at rest, consumes about 100 watts total, and your brain, making up only 2% of your body weight, uses up to 25% of that energy budget despite its small size. But what it does with that power is remarkable. 25 watts running 86 billion neurons, each one a tiny biological circuit capable of receiving signals from thousands of other neurons, integrating those signals, and deciding whether to fire its own signal down the line. Each neuron maintains an electrical potential across its membrane, about 70 millivolts of difference between inside and outside, like a tiny battery constantly maintained by molecular pumps that move sodium and potassium ions against their concentration gradients. When a neuron fires, that voltage difference collapses momentarily as ions rush across the membrane, creating an electrical pulse called an action potential that travels down the neuron's axon at speeds up to 120 meters per second. Then the cell pumps the ions back out, resetting the voltage, ready to fire again. This happens billions of times per second across your brain. Neurons firing, signals propagating, networks activating in patterns that somehow produce consciousness, memory, perception, thought, emotion, everything you experience as your inner life. And it runs on 25 watts. The electricity is measurable from outside the skull. This is what electroencephalography, EEG, detects. Electrodes placed on your scalp, picking up the collective electrical activity of millions of neurons firing in synchrony. The signal is weak by the time it reaches the surface, only about 10 to 100 microvolts, but it's detectable, analyzable, useful for diagnosing epilepsy and sleep disorders and other neurological conditions. The patterns of activity change depending on what you're doing. When you're awake and alert, the activity is fast and desynchronized, lots of different regions firing independently, creating high-frequency, low-amplitude waves. When you relax with your eyes closed, alpha waves appear, synchronized firing at about 8 to 13 hertz, a rhythmic pulse that spreads across the brain. In deep sleep, the waves become slower and larger, delta waves at 0.5 to 4 hertz, whole regions of the brain firing together in slow, rolling patterns. This electrical activity isn't separate from thinking. It is thinking, or at least the physical substrate of thinking. Every thought, every memory, every sensation corresponds to some pattern of neurons firing, some configuration of electrical activity spreading through your brain's networks. When you see something, light hits your retina, triggering electrical signals that travel to your visual cortex, where millions of neurons fire in patterns that represent edges, colors, motion, eventually assembling into your perception of a coherent scene. All of it is electricity, controlled and channeled through biological circuits. When you remember something, neurons that fired together when the memory formed fire together again, recreating the pattern, pulling the memory back into awareness. The strengthening of connections between neurons, synaptic plasticity, the physical basis of learning, happens through electrical activity, triggering chemical changes that make future firing more likely. Everything your brain does involves electricity, and it all runs on 25 watts, roughly what it takes to light a closet. This efficiency is astonishing compared to artificial systems. The most powerful supercomputers consume megawatts of electricity, millions of watts, to perform calculations that, in some domains, still don't match what your brain does effortlessly. Image recognition, language processing, motor control, tasks your brain handles in real time with 25 watts still challenge computers consuming 1,000,000 times more power. Part of the brain's efficiency comes from parallelism. All 86 billion neurons operate simultaneously, each one performing simple computations, but all contributing to the overall processing. It's like having billions of slow processors working together instead of one fast processor doing everything sequentially. Part comes from the architecture. Neurons aren't connected randomly, but in specific patterns shaped by evolution and learning, creating networks optimized for the tasks brains need to perform: vision processing, language, motor planning, emotion. Each has dedicated regions with specialized connectivity. And part comes from the medium itself. Neurons use chemical signals at synapses, which is slower than pure electrical signaling, but allows for complex modulation, learning, and plasticity. The brain isn't just computing, it's constantly rewiring itself based on experience, strengthening some connections, weakening others, adapting to new information. All of this powered by the energy equivalent of a nightlight. When you think hard, working through a difficult problem, learning something new, concentrating intensely, your brain's energy consumption increases slightly. Blood flow to active regions increases to deliver more oxygen and glucose. You can see this in fMRI scans, areas lighting up as they work harder, consuming more resources. But the total power draw doesn't change dramatically. Your brain doesn't have a turbo mode that suddenly requires hundreds of watts. It works within its power budget, about 20% of your total energy expenditure, whether you're solving equations or daydreaming or sleeping. The electricity itself, the 25 watts, dissipates as heat. Your brain is warm, typically about 37 degrees Celsius, slightly warmer than the rest of your body. This heat is carried away by blood flow, radiated through your skull, helping maintain thermal equilibrium. But before it becomes heat, that electrical energy does work. It maintains gradients, propagates signals, processes information, creates the patterns of activity that correspond to your conscious experience. 25 watts of electricity flowing through networks of neurons, producing something as complex as a human mind. Enough power to light a small bulb, producing instead thoughts, memories, emotions, sensations, the entire subjective universe of your experience. It's been running since before you were born. Your brain started developing in the womb, neurons forming, electrical activity beginning, patterns establishing themselves that would eventually become you, and it will keep running until you die. This 25-watt engine of consciousness humming along in the darkness of your skull, invisible, untouchable, but absolutely essential to everything you are. Right now, as you lie there listening or reading, your brain is using about 25 watts, creating these thoughts, processing these words, maintaining awareness, directing your breathing, your heartbeat, all the unconscious processes that keep you alive. All of it running on less power than it takes to charge a phone. Efficient. Remarkable. Mysterious in how it works, but measurable in what it costs. 25 watts. The price of consciousness, paid continuously, in electricity generated by chemistry, in signals propagating through meat, in patterns emerging from chaos to create order, meaning you. Tardigrades can survive in the vacuum of space, extreme radiation, and temperatures from near absolute zero to 150-degree Ks. Tardigrades, sometimes called water bears or moss piglets, are microscopic animals, typically about 0.5 millimeter long, visible to the naked eye if you know where to look, but easier to see under a microscope. They have 8 legs, stubby and clawed. They lumber along in a slow, bear-like walk, hence the name water bear. They look almost comical, like tiny, chubby, translucent bears wandering through moss and lichen, but they're nearly indestructible. Put a tardigrade in the vacuum of space. No air, no pressure, exposure to unfiltered cosmic radiation, and it survives. They've been sent to low Earth orbit on the outside of spacecraft, exposed directly to space for 10 days, then brought back to Earth. Most of them survived. Given water and normal conditions, they revived and went on living as if nothing had happened. Expose them to radiation doses that would kill almost any other animal, several thousand times the lethal dose for humans, and they survive. The radiation damages their DNA, but tardigrades have mechanisms to repair it, to reconstruct broken genetic information, to continue functioning despite cellular damage that would be catastrophic for most organisms. Heat them to 150 degrees Celsius, hot enough to boil water, hot enough to cook most living things almost instantly, and they survive. Cool them to near absolute zero, just a few degrees above the lowest possible temperature in the universe, and they survive. Freeze them in solid ice for years, and they revive when thawed. Dry them out completely, removing all water from their bodies until they're desiccated husks, and they enter a state called cryptobiosis, essentially suspended animation, where metabolism stops, life processes halt, but the structure remains intact. In this state, they can survive for decades, maybe longer. We don't know the upper limit because we haven't tested it long enough yet. When conditions improve, when water becomes available again, they rehydrate, resume metabolism, and continue living, as if the decades of desiccation were just a pause, an interruption, not a near-death experience. This seems impossible. Life requires water. Life requires stable temperatures, protection from radiation, pressure, breathable environments. Every biology textbook describes the conditions necessary for life, the narrow range of parameters within which organisms can survive. Tardigrades ignore all of that. How? The key is cryptobiosis. When conditions become unfavorable, when their environment dries out or becomes too hot or too cold, tardigrades essentially shut down. They produce protective molecules, tree halos, and other compounds that replace water in their cells and stabilize proteins and membranes. They curl up into a structure called a tun, pulling in their legs, forming a compact shape that minimizes surface area. In this state, their metabolism drops to less than 0.01% of normal. They're not dead. The cellular machinery is intact, DNA is preserved, structures remain organized, but they're not alive in any active sense. No energy consumption, no growth, no reproduction. Just waiting, in perfect stasis, until conditions improve. This allows them to survive extremes that would destroy active cells. Radiation damages DNA, but inactive cells in cryptobiosis can repair the damage when they rehydrate, because the repair mechanisms are still present, just dormant. Freezing damages cells by forming ice crystals that puncture membranes. But tardigrades in cryptobiosis have protective compounds that prevent crystal formation or minimize damage. They can survive vacuum because they don't need to breathe in cryptobiosis. No metabolism means no oxygen requirement. The vacuum doesn't kill them because they're already in a state where they don't need air. And when they rehydrate, the process reverses. Water enters the cells, replaces the protective compounds, metabolism restarts, DNA damage is repaired if necessary, and the tardigrade resumes life where it left off. They've been revived after being frozen in Antarctic ice for 30 years. They've survived being launched in rockets, exposed to space, irradiated with gamma rays, baked, frozen, dried, and subjected to pressures 6 times greater than the deepest ocean trenches. Nothing kills them, as long as they have time to enter cryptobiosis first. This has made them subjects of intense scientific interest. If we understood how tardigrades protect themselves, could we apply that knowledge to preserving human cells, tissues, organs? Could we develop better ways to store biological samples, to protect astronauts from radiation on long space missions, to extend the preservation time for donated organs? Some of their protective mechanisms are being studied for exactly these applications. The proteins they produce, the way they stabilize cellular structures, the DNA repair mechanisms, all of it could potentially be adapted or mimicked in other organisms. But for now, tardigrades remain unique in their hardiness. No other animal can survive such extremes. Some bacteria can, using spores or similar mechanisms. Viruses, which aren't technically alive, can persist in harsh conditions. But among animals, complex multicellular organisms with nervous systems and digestive systems and all the machinery of animal life, tardigrades are unmatched. They've probably survived multiple mass extinctions. Whatever killed the dinosaurs, whatever caused the Permian extinction that wiped out 96% of marine species, tardigrades endured. When conditions became impossible, they entered cryptobiosis and waited it out, decades or centuries or millennia, until things improved. They're everywhere. In moss, in lichen, in soil, in freshwater, in the ocean. Wherever there's moisture, there are probably tardigrades, living their slow, patient lives, grazing on bacteria or plant cells, reproducing, surviving. And when conditions turn harsh, they simply stop, shut down, wait, for as long as it takes. Then when rain comes, or ice melts, or whatever catastrophe ended, finally ends, they wake up, resume, continue, as if nothing happened. Tiny, nearly invisible, virtually indestructible, water bears, trudging through moss, surviving the unsurvivable, outlasting everything. 400 million years of evolutionary history have made them resilient beyond anything else we know. And they do it all while being small enough to live on a speck of moss, simple enough to see under a school microscope, humble enough that most people have never heard of them. But they're there, in your backyard, probably, in the moss on trees, in the soil, in puddles and ponds, surviving, waiting, ready to endure whatever comes next, the vacuum of space, extreme radiation, temperatures that would destroy almost anything else. Tardigrades just shut down and waited out, patient, resilient, nearly eternal. The toughest animals on Earth, and possibly anywhere. The Voyager 1 spacecraft, launched in 1977, is still communicating with Earth from over 15 billion miles away. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2, on missions to explore the outer solar system. Jupiter, Saturn, their moons. Maybe Uranus and Neptune if the trajectories worked out, if the spacecraft lasted long enough, if everything went according to plan. Everything went better than planned. Both spacecraft completed their primary missions, sending back stunning images and data from planets humans had never seen up close. Jupiter's Great Red Spot, Europa's icy surface, Saturn's rings in unprecedented detail, Uranus's strange tilted rotation, Neptune's Great Dark Spot. Each encounter was a success, each flyby providing years of scientific data. But the missions didn't end there. After passing the outer planets, both Voyagers kept going, flying outward into the space beyond, heading toward interstellar space with no more planets to visit, nothing to observe except the gradual thinning of the solar wind and the increasing influence of the galaxy beyond. And they're still going, still flying, still transmitting. Voyager 1 is now over 15 billion miles from Earth, about 24 billion kilometers, or 160 astronomical units. An astronomical unit is the distance from Earth to the Sun, so Voyager 1 is 160 times farther from the Sun than we are, in a region of space where sunlight is so faint it's barely distinguishable from starlight. It's the most distant human-made object in existence, the farthest anything built by humans has ever traveled, and it's still talking to us. Every day, Voyager 1 transmits data back to Earth using a 23-watt transmitter, about the power of a refrigerator light bulb. That signal travels at the speed of light across billions of miles of empty space, spreading out, weakening, until it reaches Earth over 22 hours later, arriving as one of the faintest signals ever detected. By the time it reaches Earth, the signal is incredibly weak, about 10 neutrinos 16 watts, a tenth of a quadrillionth of a watt. It's so faint that NASA uses massive radio dishes, 70-meter antennas of the Deep Space Network, to detect it, amplifying the signal millions of times just to extract the data. But it works. We receive the data. Voyager sends information about magnetic fields, cosmic rays, the density of particles in interstellar space, and we decode it, analyze it, learn from it. The spacecraft is powered by radioisotope thermoelectric generators, RTGs, which convert heat from decaying plutonium-238 into electricity. When Voyager launched, the RTGs produced about 470 watts. Now, 47 years later, they produce about 220 watts as the plutonium decays. The power output decreases by about 4 watts per year, and eventually, probably around 2025 to 2030, there won't be enough power to run the transmitter and instruments. When that happens, Voyager will go silent. It will keep flying, keep moving outward at about 38,000 miles per hour, but we won't hear from it anymore. It will become a ghost ship, sailing through interstellar space in silence, carrying its golden record, a phonograph record with sounds and images from Earth, intended for any intelligent life that might find it in the distant future. But for now, it's still transmitting, still talking to us across a gulf of space so vast that light takes nearly a full day to cross it. The signal delay is over 22 hours one way, which means communication is incredibly slow. If we send a command to Voyager, instructing it to change orientation, switch instruments, adjust its trajectory slightly. It takes 22 hours for the command to arrive, and another 22 hours for the confirmation to return. Nearly 2 days per interaction. This makes real-time control impossible. Everything must be planned in advance, commands uploaded, the spacecraft left to execute them autonomously while we wait for confirmation that they worked. And it does work. Despite being built with 1970s technology, computers less powerful than a modern calculator, instruments designed before integrated circuits were common, systems that have been running continuously for nearly half a century. Voyager 1 continues to function. Some instruments have failed, yes. Some have been turned off to conserve power, but the core systems remain operational. The spacecraft can orient itself, can transmit data, can execute commands, all while operating in an environment it was never specifically designed for. With radiation levels and particle densities we could only estimate when it launched. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind from the sun meets the interstellar medium. It became the first human-made object to enter interstellar space, the first to leave the protective bubble of our sun's influence and enter the space between stars. It's still within the sun's gravitational influence, still technically part of the solar system in that sense. It won't reach the Oort cloud, the shell of icy bodies at the very edge of the sun's gravitational dominion, for about 300 years, and it won't exit the Oort cloud completely for another 30,000 years. But it's in interstellar space now, surrounded by particles from other stars, measuring the density and composition of the galaxy itself rather than just our local stellar environment. And it's telling us what it finds. Data about cosmic rays, magnetic field strength, plasma density, all transmitted back across billions of miles at 23 watts, arriving on Earth as whispers we can barely detect, but that contain information from the edge of everything we've ever reached. Eventually, Voyager will go silent. The plutonium will decay, the power will drop below minimum levels, the transmitter will shut down, and we'll lose contact. But the spacecraft will keep flying, coasting through space at constant velocity, untouched by friction, because there's nothing to slow it down, moving in whatever direction its last trajectory took it. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. It won't notice. The star's gravity is too weak at that distance to affect the trajectory significantly. Voyager will just drift past, another piece of cosmic debris, silent and dark, but carrying its golden record, its message from Earth, out into the galaxy. Maybe someday, billions of years from now, something will find it. Maybe intelligent beings will intercept this ancient artifact, decode its message, learn about the species that built it, or maybe it will drift forever, undiscovered, a monument to exploration that no one ever sees. But for now, it's still flying, still transmitting, still connected to Earth by a thread of radio waves, a conversation across the largest distance humans have ever maintained with something we build. Voyager 1 launched in 1977, over 15 billion miles away, whispering back to us at 23 watts. Still there, still talking, the loneliest object in existence, and yet still, somehow, not alone. Because we're listening. Approximately 8% of human DNA consists of ancient viral genetic code that infected our ancestors millions of years ago. You are not entirely human. not in the sense that all your DNA came from your human ancestors. About 8% of your genome, roughly 100,000 fragments scattered across your chromosomes, came from viruses. Not viruses that infected you. Viruses that infected your ancestors millions of years ago integrated their genetic material into the germline, eggs or sperm, and were passed down through every subsequent generation, becoming a permanent part of the human genome. These are called endogenous retroviruses, or ERVs, and they're in every human, every cell, every copy of your DNA. Here's how it happens. Retroviruses, the family includes HIV and several other pathogens, work by inserting their genetic material into a host cell's DNA. That's how they reproduce. They infect a cell, convert their RNA genome into DNA using an enzyme called reverse transcriptase, and splice that DNA into the host's chromosomes. Then they use the host's cellular machinery to make new viruses. Most of the time, this happens in regular body cells, somatic cells. And when those cells die, the viral DNA dies with them. No lasting impact beyond the individual infection, but occasionally, rarely, a retrovirus infects a germline cell, a sperm cell, or an egg cell, something that will contribute to the next generation. If that infected germline cell successfully produces offspring, the viral DNA gets passed on. It becomes part of the organism's genome, present in every cell of the offspring's body, including their germline cells. If those offspring reproduce, they pass it on again, and again, and again. Over millions of years, through countless generations, that viral DNA accumulates. Sometimes it mutates into non-functionality, becoming a genetic fossil, sequence that's clearly viral in origin, but no longer does anything. Sometimes it gets deleted. Sometimes it duplicates, creating multiple copies. But sometimes it gets co-opted. Sometimes evolution finds a use for it. There are sequences in the human genome, originally from ancient retroviruses, that now serve important functions. Some regulate gene expression, turning genes on or off in response to signals. Some play roles in immunity, helping defend against modern viral infections by producing proteins that interfere with viral replication. And remarkably, some viral genes are essential for pregnancy. The placenta, the organ that connects mother and fetus, allowing nutrient exchange while keeping their blood systems separate, relies on proteins called syncytins. These proteins help cells fuse together to form the multinucleated structure of the placenta, creating the barrier that protects the fetus while allowing molecules to pass through. Syncytins are viral proteins. Their genes came from ancient retroviruses that infected our ancestors millions of years ago. Evolution co-opted these viral fusion proteins, originally used by viruses to merge with host cells, and repurposed them for placental development. Without viral DNA, placental mammals might not exist. Pregnancy as we know it depends on genes stolen from viruses tens of millions of years ago. This is true across mammals. Different mammal lineages have co-opted different viral genes for placental function, which suggests that retroviruses infected mammals multiple times independently. And each time, evolution found ways to use the viral genetic material for reproductive purposes. It's a form of horizontal gene transfer, acquiring DNA not from your parents but from an outside source. Most of life relies on vertical inheritance, DNA passing from parent to offspring. But viruses enable horizontal transfer, moving genetic information between unrelated organisms, sometimes across vast evolutionary distances. And when that transfer happens in germline cells, it becomes permanent. The viral DNA integrates into the genome, becomes part of the species' genetic heritage, persists across millions of years. About 8% of the human genome is viral in origin. That's more than the roughly 1.5% that codes for proteins. You have more ancient viral DNA than you have genes that directly make the proteins your body uses. Most of it is inactive, silenced by mutations or epigenetic modifications that keep it from expressing. But it's there, a record of ancient infections, a genetic fossil record showing which viruses infected human ancestors at what points in evolutionary history. Researchers can trace these ERVs, comparing them across species to build evolutionary trees. If humans and chimpanzees share a particular viral insertion in the same location, that virus must have infected a common ancestor before the two lineages split. If humans have it but chimps don't, the infection happened after divergence. It's another source of evidence for evolution, another way to trace relationships between species, another window into the deep past encoded in DNA. And it's ongoing. There are endogenous retroviruses specific to humans, acquired after we split from other primates. There are probably ERVs entering human populations right now. Retroviruses infecting germline cells in rare cases, potentially becoming permanent parts of the human genome in future generations if those infections happen to successfully reproduce. This changes how we think about identity, about what it means to be human. Your genome isn't just human, it's a mosaic, a patchwork of sequences from your human ancestors, mixed with sequences from viruses that infected those ancestors, all of it blended together into the code that makes you. Evolution doesn't care about purity. It uses whatever works, whatever provides an advantage, whatever happens to be available. Ancient viral genes, inserted by infection, have been sculpted by millions of years of selection into functional components of human biology. You are 8% virus at the genetic level, not infected but incorporated, not foreign but integral. The viruses that made you possible, that contributed to placental development, that helped build the immune system, that regulate genes throughout your body, 8%, hundreds of thousands of fragments, scattered across every chromosome, in every cell. Ancient viruses, long dead as active pathogens, living on as part of you. Permanent residents in the human genome, guests that became family over millions of years. You carry them wherever you go, pass them on to your children. They're part of your inheritance, your evolutionary heritage, your identity. 8% virus, 92% human, 100% the result of billions of years of life, mixing, merging, incorporating whatever works into a genome that's less a pure lineage than a collaborative project. You are not just your ancestors. You are also their infections, their parasites, their viruses, transformed over time into something new, something functional, something essential. Part human, part virus, all of it you. A single bolt of lightning contains enough energy to toast 100,000 slices of bread. Toasting a slice of bread takes energy. You're heating the bread to about 150 degrees Celsius, driving off moisture, triggering Maillard reactions that turn starches and sugars brown, creating that crispy texture and nutty flavor. A typical toaster uses about 1,000 watts and takes a few minutes to toast bread, which works out to roughly 100,000 joules of energy per slice, about 100 kilojoules, or 0.1 megajoules. Not much energy in the grand scheme. A car uses thousands of times more energy to drive a mile. Your body burns more than that just maintaining itself for an hour. But multiply it by 100,000 slices, and you're talking about 10 billion joules, 10 gigajoules, which is approximately the energy content of a single bolt of lightning. One bolt, 10 gigajoules. Enough to toast 100,000 slices of bread if you could somehow capture and direct that energy efficiently, which you can't, but theoretically. Lightning is a massive electrical discharge. When it strikes, current flows, typically 20,000 to 200,000 amperes, though some strikes can reach 1,000,000 amperes. That's orders of magnitude more than household current, which is typically 10 to 20 amperes. The voltage is also enormous, hundreds of millions of volts between cloud and ground. For comparison, a standard outlet is 120 or 240 volts. Lightning operates at voltages 1,000,000 times higher, but the duration is short. A lightning bolt lasts only about a millisecond, sometimes less, rarely more than a few milliseconds. So despite the enormous current and voltage, the total energy is somewhat limited by time. Still, multiply amperage by voltage by time, and you get energy. About 1,000,000,000 joules for a typical lightning strike, give or take an order of magnitude depending on the specifics of the strike. 1,000,000,000 joules is a lot of energy. It's about 278 kilowatt hours, which is enough to run a typical household for a month. It's the energy in about 7 gallons of gasoline. It's enough to heat several hundred gallons of water to boiling, or to toast 100,000 slices of bread. The problem is capturing it. Lightning is unpredictable. You can't predict exactly where or when it will strike. And even if you could, the power delivery is so concentrated in time and space that most storage systems would be overwhelmed. Batteries charge slowly. Capacitors can handle rapid charging. But you'd need enormous capacitors to store 1,000,000,000 joules, and the infrastructure to safely channel lightning into them would be expensive and difficult. So while lightning contains significant energy, it's not a practical power source. The energy density in time is too high, the unpredictability too great, the infrastructure requirements too demanding. But the energy is real. When lightning strikes sand, it can melt it into glass, creating fulgurites, hollow tubes of fused silica following the lightning's path into the ground. When it strikes trees, the moisture inside can vaporize so quickly the tree explodes, wood splitting and flying apart from the expansion of steam. When it strikes metal, it can vaporize the surface, creating tiny beads of molten metal that solidify as the strike ends. When it strikes people, it can stop hearts, disrupt neural function, cause severe burns, the current passing through the body, superheating tissue, disrupting electrical signals that coordinate muscle contraction and nerve transmission. All of that from 1,000,000,000 joules delivered in a millisecond, and it happens constantly. Right now, somewhere on Earth, lightning is striking. About 100 times per second globally, roughly 8 million strikes per day, over 3 billion strikes per year, each one carrying enough energy to toast tens of thousands of slices of bread. If we could somehow capture all of it, all the lightning worldwide, every strike, all year, the total energy would be significant. Hundreds of terawatt hours annually, which sounds like a lot until you compare it to global energy consumption of about 170,000 terawatt hours per year. Lightning would provide maybe 0.5% of global energy needs if we could capture it all, which we can't. so it's not a solution to energy problems, but it's a reminder of how much energy is constantly moving through the atmosphere, how much power is available in natural phenomena, if only we could harness it efficiently. A single bolt, a billion joules, 100,000 slices of bread, or a month of household electricity, or 7 gallons of gasoline, or enough heat to boil hundreds of gallons of water. All of it released in a millisecond, a fraction of a second, a flash of light and heat that briefly connects sky and ground, equalizes charge, then disappears. The energy dissipates into heat, into sound, thunder, into electromagnetic radiation across the spectrum. Some goes into chemical reactions, producing nitrogen compounds from atmospheric nitrogen and oxygen, which eventually fall to the ground as natural fertilizer. But most of it just becomes waste heat, warming the air along the lightning channel, spreading outward, diluting into the environment, ultimately radiating into space. A billion joules, released and dissipated in moments, enough to toast 100,000 slices of bread. If only we could catch it. The coldest temperature ever recorded on Earth was 128.6 degrees in Antarctica, but the coldest temperature ever created in a lab was just a billionth of a degree. Above absolute zero. Cold is the absence of heat. That's all it is, fundamentally. Not a substance, not a force, just the lack of thermal energy, the slowing of molecular motion, the approach toward stillness. The coldest natural temperature ever recorded on Earth was 128.6 degrees Fahrenheit, measured at the Soviet Vostok Station in Antarctica on July 21, 1983. That's 89.2 degrees Celsius, or about 184 Kelvin. At that temperature, exposed skin freezes in seconds. Metal becomes brittle. Ordinary materials behave strangely. Rubber shatters like glass. Oils solidify. Air begins to liquefy if you cool it just a bit more. It's hostile to life, to machinery, to almost everything we think of as normal. And yet, it's not even close to absolute zero. Absolute zero is 0 Kelvin, or 273.15 degrees Celsius, or 459.67 degrees Fahrenheit. It's the theoretical lower limit of temperature, the point at which all thermal motion stops, where molecules have the minimum possible energy allowed by quantum mechanics. You can't reach absolute zero. The third law of thermodynamics says it's impossible. You can approach it asymptotically, getting closer and closer, but never quite arriving. Every step towards zero requires exponentially more effort, more sophisticated cooling techniques, more energy and time. But we've gotten close, incredibly close. The coldest temperature ever created in a laboratory was achieved by researchers at MIT in 2003, cooling a cloud of sodium atoms to about 450 picokelvin, 450 trillionths of a degree above absolute zero. That's 0.0045 Kelvin, a temperature so cold it has no natural equivalent anywhere in the universe that we know of. At that temperature, atoms move incredibly slowly. They're not frozen solid. Quantum mechanics forbids complete stillness, but their motion is reduced to quantum fluctuations, tiny vibrations that represent the minimum energy required by the uncertainty principle. Strange things happen at extreme cold. Atoms begin to behave less like individual particles and more like waves, their quantum nature becoming dominant. They can overlap, share space, act collectively in ways that don't happen at higher temperatures. This is how Bose-Einstein condensates form, clouds of atoms cooled so close to absolute zero that they all drop into the same quantum state, becoming a kind of superatom, thousands or millions of individual atoms acting as one coherent quantum object. In this state, the atoms are described by a single quantum wave function. They're not separate entities anymore, but parts of a collective, exhibiting properties that don't exist at normal temperatures. Superfluidity, for instance, the ability to flow without viscosity, to climb up walls, to pass through barriers that would stop normal fluids. Or superconductivity, where electrical resistance disappears completely and current can flow forever without dissipating energy. Some materials become superconducting at relatively high temperatures, still cold by everyday standards, but not requiring exotic cooling. Others only superconduct near absolute zero, their electrons forming Cooper pairs that move through the material without scattering, without losing energy to heat. These aren't theoretical effects. They're real, observable, useful. MRI machines use superconducting magnets cooled to a few Kelvin. Quantum computers require temperatures near absolute zero to maintain coherence in qubits, to prevent thermal noise from disrupting calculations. We build machines to reach these temperatures using multiple stages of cooling. First, conventional refrigeration to get down to maybe 100 Kelvin, then liquid nitrogen cooling to reach 77 Kelvin, then liquid helium to reach 4 Kelvin, then more sophisticated techniques, dilution refrigerators, evaporative cooling, laser cooling, each step bringing the temperature down by another order of magnitude. Laser cooling sounds paradoxical, using light, which carries energy, to cool atoms. But it works by carefully tuning lasers to slow atoms down, to remove kinetic energy, to trap atoms in optical molasses where they can barely move. Then evaporative cooling takes over, selectively removing the fastest atoms from the cloud, leaving behind the slowest, coldest ones, like blowing on hot soup, to cool it by removing the hottest molecules. The result is temperatures colder than anything in nature, colder than interstellar space, which averages about 3 Kelvin due to the cosmic microwave background, colder than the coldest known natural objects in the universe. And at these temperatures, the universe reveals behaviors we'd never see otherwise. Quantum effects become macroscopic, visible, demonstrable. Atoms' wave functions overlap. Matter behaves like waves. Fluids flow without friction. Conductors conduct without resistance. It's a different regime of physics, where classical intuitions break down and quantum mechanics dominates, even at scales large enough to see with the naked eye. But reaching it requires enormous effort. The coldest lab temperatures require vacuum chambers, magnetic traps, multiple cooling stages, constant energy input to maintain the systems. You're fighting the second law of thermodynamics. Heat always flows from hot to cold. Disorder always increases. And creating perfect order, zero temperature, requires removing all disorder from your system and dumping it elsewhere. The energy cost is high. The equipment is expensive. The time scales are slow. Cooling atoms to picokelvin temperatures takes seconds or minutes of carefully controlled laser pulses and evaporation. And once you have them there, at those extreme temperatures, the slightest disturbance warms them up. A stray photon, a vibration from machinery, any interaction with the environment adds energy, raises the temperature, destroys the delicate quantum state you've created. So experiments at extreme cold are fleeting. You create a Bose-Einstein condensate. Study it for a few seconds or minutes, then it's gone, warmed by interactions. returning to a more ordinary state. But in those brief moments, we see the universe as it almost never is, at the edge of stillness, where quantum weirdness emerges from the cold, where matter stops behaving like solid stuff and starts behaving like probability waves, where the rules change and new physics appears. From 128.6 degrees on a frozen plateau in Antarctica, cold enough to kill, cold enough to challenge survival, but still almost 400 degrees above absolute zero, to 450 picokelvin in a lab, a temperature so extreme that molecules barely move, that atoms merge into quantum superpositions, that the fabric of reality becomes strange and quantum, and nothing like everyday experience. Cold isn't just the absence of heat. At extreme cold, it's the gateway to different physics, to behaviors matter can only exhibit when thermal energy is stripped away, when motion slows to quantum minimums, when the universe reveals possibilities that heat normally conceals. We can't reach absolute zero, but we can get close enough to see what waits there, in the near stillness, in the quantum regime, in temperatures colder than nature produces anywhere. And what we find is beautiful, strange, useful in ways we're still discovering. Bose-Einstein condensates, superfluids, superconductors, quantum behaviors at macroscopic scales, all of it hidden in the cold, waiting for us to cool atoms to a billionth of a degree above absolute zero and observe what happens when heat almost, but not quite, disappears. About 330 billion cells die in your body every day, yet most of them are replaced. You are dying, constantly, cell by cell, in a process so continuous and thorough that you're essentially being rebuilt in real time, old parts discarded, new parts grown, the whole system maintained through endless cycles of death and renewal. About 330 billion cells die in your body every day. That's roughly 1% of your total cells, dying, being broken down, cleared away, replaced. 330 billion every day. It sounds catastrophic. It sounds like cellular apocalypse happening inside you continuously. But it's normal, necessary, healthy. Most cells have lifespans. They're not meant to last forever. They divide, they function, they age, they die. Some die from damage, infections, toxins, mechanical stress, random accidents of chemistry. But most die on a schedule, programmed cell death called apoptosis, a deliberate self-destruction that eliminates old or damaged cells before they become problems. Apoptosis is controlled suicide. The cell detects signals, internal timers, damage sensors, instructions from immune cells, and activates its own death machinery. Enzymes called caspases chop up proteins, dismantle cellular structures, fragment DNA. The cell shrinks. Its membrane forms blebs. It packages itself into neat little bundles that neighboring cells or macrophages can engulf and digest. Cleanly. No mess. No inflammation. No release of toxic contents into surrounding tissue. Just orderly dismantling, recycling of components, space made available for new cells to take its place. Different cells have different lifespans. Red blood cells last about 120 days, circulating through your bloodstream carrying oxygen, then dying and being recycled by the spleen and liver. White blood cells vary, some last days, others years, depending on type and function. Cells lining your small intestine last only about 5 days, constantly abraded by food passing through, replaced continuously to maintain the protective barrier. Skin cells on the surface last about 2 to 4 weeks before they die and flake off. You shed millions of them daily, dead cells becoming dust. a continuous sloughing off of your outermost layer. The cells beneath divide to replace them, pushing upward, differentiating, eventually reaching the surface where they too will keratinize, die, flake away. Some cells last much longer. Neurons in your brain and spinal cord are mostly not replaced. You have roughly the same neurons at age 70 that you had at age 7, though they've changed, grown new connections, pruned old ones, adapted over time. Cardiac muscle cells are also long-lived, though there's some slow replacement throughout life, about 1% per year renewed, but most cells turn over. Most are replaced on schedules ranging from days to months to years. Add it all up, and about 330 billion cells die per day. Most are blood cells and gut lining cells, tissues with high turnover rates. But every tissue contributes: bone cells, liver cells, lung cells, muscle cells, all dying and being replaced according to their respective schedules. And somehow, through all this death, you remain you. Your tissues maintain their structure. Your organs continue functioning. Your body persists despite being in constant flux at the cellular level. It's like the ship of Theseus, the philosophical thought experiment. If you replace every plank in a ship over time, is it still the same ship? Your body does this continuously. Every few years, most of your cells have been replaced. The atoms in those cells have been replaced even faster, cycled through metabolism, taken in from food, expelled in waste or breath or sweat. You are not the same physical matter you were a decade ago. You're a pattern, a process, a continuous replacement of parts that somehow maintains identity despite having almost nothing in common materially with your past self. The dead cells are cleared away efficiently. Macrophages, immune cells specialized for phagocytosis, patrol tissues, engulfing dead cells, debris, anything marked for removal. They digest what they eat, break it down into components that can be recycled or excreted. Some cell death is wasteful, spilling contents into tissues, causing inflammation, requiring cleanup. This is necrosis, uncontrolled cell death from injury or disease. It's messy, damaging to surrounding cells, something the immune system has to deal with aggressively. But most cell death is apoptosis, clean and controlled, cells dismantling themselves neatly, minimizing impact on neighbors, making recycling easy. And then new cells replace them. Stem cells divide, differentiating into whatever cell type is needed. Progenitor cells committed to specific lineages divide and mature. Existing cells in some tissues divide directly, one becoming two, maintaining population size. The balance is precise. Too much cell death without replacement causes tissue atrophy, organs failing, systems declining. Too much cell division without death causes tumors, uncontrolled growth, cancer. The equilibrium, death matched by replacement, division matched by apoptosis, maintains health. This is why chemotherapy is so harsh. It targets rapidly dividing cells, which include cancer, but also hair follicles, gut lining, bone marrow producing blood cells. The treatments kill cells indiscriminately in high turnover tissues, causing hair loss, digestive problems, immune suppression. The cancer dies, hopefully, but so do many healthy cells, and recovery depends on those healthy tissues regenerating faster than the cancer. But normally, the system works. 330 billion cells die per day, and roughly the same number are born, keeping everything in balance, maintaining you as a coherent organism despite the constant cellular turnover. It's happening right now. As you lie there, cells in your gut are dying. sloughing into the intestinal lumen to be digested and excreted. Red blood cells are dying, being filtered out by your spleen. Skin cells on your surface are dying, flaking off onto sheets and clothes. Immune cells are dying, having completed their missions or reached their lifespans. And beneath, new cells are being born. Stem cells in bone marrow producing new blood cells. Basal cells in skin dividing to replace the surface layer. Intestinal stem cells in crypts dividing to renew the gut lining. Birth and death, constantly everywhere in your body, maintaining the pattern that is you through continuous renewal. You are not a static thing, you're a process. A river that stays the same shape while the water flows through. A flame that maintains its form while consuming fuel and releasing exhaust. 330 billion cells dead today. Tomorrow, another 330 billion. Every day for your entire life until the balance finally tips, until renewal can't keep pace with death, until the system fails and you die not cell by cell but all at once, systemically, the whole pattern collapsing when critical components can no longer be replaced. But until then, you persist. You endure. You continue being you through endless cycles of cellular death and rebirth, the ship of Theseus rebuilt plank by plank, never the same matter but always the same you. Dying and being reborn, 330 billion cells at a time, every single day. The longest living organism on Earth is a clonal colony of aspen trees in Utah called Pando, estimated to be 80,000 years old. There's a forest in Utah that's older than human civilization, older than agriculture, older than writing, older than any of the monuments we think of as ancient. And it's not a forest of many trees. It's one organism. Pando, Latin for ice spread, is a clonal colony of quaking aspen trees in the Fish Lake National Forest. From the surface, it looks like a normal aspen grove, about 47,000 individual stems spread across 106 acres, each tree with its own trunk, branches, leaves, appearing separate and independent. But underground, they're all connected. All 47,000 stems share a single root system, massive and ancient, spreading through the soil, sending up new shoots continuously. The entire grove is genetically identical, all grown from one original tree, cloning itself through root suckers for tens of thousands of years. The above-ground stems are young, relatively. Individual trunks live about 130 years before dying, and being replaced by new shoots from the root system. So the forest you see is constantly regenerating, new stems growing while old ones die, the visible parts no more than a century old. But the root system, the organism itself, is estimated to be about 80,000 years old, maybe older. Dating is difficult because roots don't form annual rings the way trunks do, and radiocarbon dating has limitations for organisms still alive. But genetic analysis, growth rates, and comparison with other aspen clones suggest Pando has been alive for at least 80,000 years, possibly much longer. 80,000 years. That's before the last ice age, before humans left Africa, before Neanderthals went extinct, before cave paintings at Lascaux, before megalithic temples, before any of recorded history. Pando was alive when mammoths walked North America, when dire wolves and saber-toothed cats hunted across the continent, when glaciers covered much of the northern hemisphere and sea levels were 400 feet lower than today. And it's still alive, still growing, still sending up new shoots, expanding slowly across the landscape. A single organism that weighs approximately 6,000 tons, the heaviest known organism on Earth, covering 106 acres, surviving through climate changes and ice ages and everything that's happened since the late Pleistocene. How does it survive so long? Aspen clones have several advantages. The root system is protected underground, insulated from fire, sheltered from weather, hidden from herbivores. While the above-ground stems can be damaged or destroyed, the roots survive and send up new growth. The trees are also adapted to disturbance. Fire, which kills many trees, actually helps aspen by clearing competing vegetation and triggering new shoots from the roots. Aspen are pioneer species, quick to colonize disturbed areas, and Pando's strategy of spreading through root suckers rather than relying on seeds makes it resilient to conditions that would prevent seed germination. But Pando is struggling now. The clone hasn't expanded recently. New shoots are being eaten by deer and elk before they can mature. Overgrazing by these herbivores, populations artificially high due to elimination of predators like wolves, means young stems don't survive long enough to replace dying trunks. The root system is still alive, still trying to send up new growth. But if the above-ground stems continue dying without replacement, the clone could shrink, eventually losing its ability to photosynthesize, to produce energy to maintain the root system. It survived 80,000 years, but human activity in the last century, eliminating wolves, suppressing fire, allowing deer populations to explode, might succeed where ice ages and climate shifts failed. There are efforts to protect it, fencing to exclude deer, allowing some areas to regenerate, controlled burns to mimic natural fire regimes, recognition of Pando as a unique organism worthy of conservation. But it's unclear if these efforts will be enough. An organism that survived for 80,000 years is now vulnerable in ways it's never been before, threatened by ecological changes happening too quickly for it to adapt. Still, for now, it persists. The root system sprawls beneath the soil, ancient and vast, genetically identical across 106 acres, a single organism that remembers, if organisms can remember, a world we can only know through fossils and ice cores. Pando has seen the entire span of human culture. All of it, from the first migrations out of Africa to the present day, is contained within the lifespan of this single clonal aspen colony. It was alive when the first humans reached North America, crossing the Bering Land Bridge, or traveling along coastlines, spreading across a continent empty of human presence. It was alive during the Younger Dryas, the cold snap that interrupted warming at the end of the last ice age. It was alive when agriculture began in the Fertile Crescent, when pyramids rose in Egypt, when Rome fell, when Columbus sailed, when the Industrial Revolution transformed human society. All of human history is a recent development from Pando's perspective. If a tree could have perspective, we're newcomers, brief occupants of a world the tree has inhabited for 80 millennia. And it's just one organism, one individual, spread across a hillside, cloning itself continuously, replacing its above-ground parts while the underground self persists, ancient and slow, growing outward at a pace too gradual to notice in a human lifetime, but relentless over geological time. There are other old organisms, bristlecone pines over 5,000 years old, sea sponges possibly older than Pando, bacterial colonies that might have persisted for hundreds of thousands of years. Age is difficult to measure, especially for clonal organisms or those without clear growth rings. But Pando is among the oldest, certainly, and definitely the most massive, at 6,000 tons of Biomass all genetically identical, all connected, all technically one living thing. It's a reminder that individuals can persist far longer than we do, that an organism's strategy for survival, cloning, spreading, replacing damaged parts while maintaining a protected core, can enable lifespans that dwarf human experience. 80,000 years, and counting if we let it continue. If we protect it from the threats we've created, if we give it space to keep doing what it's done since the last ice age, growing, spreading, persisting, being. Pando, I spread, still spreading after 80,000 years, still here, still alive. The oldest living organism we know of, unless something older is hiding somewhere, undetected, equally patient, equally persistent. Waiting as Pando waits for whatever comes next. Sound cannot travel through space because there are no molecules to vibrate and carry the sound waves. Space is silent, completely, utterly, absolutely silent, not quiet, not the muffled stillness of a library or the hushed calm of falling snow. Silent in a way that has no equivalent on Earth, where air and water and solid ground carry vibrations constantly, where sound is almost unavoidable except in special isolation chambers designed to block it. In space, there is no sound, cannot be sound. The physics don't allow it. Sound is a mechanical wave, a vibration propagating through a medium by making molecules bump into their neighbors, which bump into their neighbors, passing the vibration along from source to destination. In air, sound makes air molecules oscillate back and forth in the direction of propagation, creating alternating regions of compression and rarefaction that we perceive as sound when they reach our ears. But space is vacuum. Near vacuum, anyway. There are particles out there, atoms of hydrogen, cosmic dust, ionized plasma, but they're incredibly sparse. In the interstellar medium, there might be 1 atom per cubic centimeter. In interplanetary space within the solar system, maybe 10 atoms per cubic centimeter in some regions, fewer in others. On Earth, air at sea level contains about 10-19 molecules per cubic centimeter, 10 billion molecules in a thimbleful of air. Space has maybe 10 atoms in that same volume. The density is so low that molecules almost never collide, almost never interact, can't transfer vibrations to neighbors because there are no neighbors close enough to bump into, so sound can't propagate. A vibration in space just stays local. It doesn't spread as a wave because there's no medium to carry it. This means all those dramatic explosions in space movies, the roar of engines, the boom of ships exploding, the whoosh of fighters zipping past, are all fictional, artistic license, dramatic effect. In reality, all of it would happen in complete silence. The Death Star exploding in Star Wars, silent. A massive, catastrophic detonation that would be deafening on Earth, but in space, no sound at all. You'd see the light, the flash, the expanding debris, the radiation, but you wouldn't hear anything. A rocket engine firing? Silent from outside. The astronauts inside the rocket would hear it through conduction, vibrations traveling through the rocket's structure to the air inside the cabin, but outside, in vacuum, nothing. Even the Apollo astronauts, walking on the moon, couldn't hear each other except through radios. The moon has no atmosphere, so sound can't travel between them. They could see each other, wave, gesture, but any sound they made, voice, footsteps, tools clanging, stayed trapped in their suits or conducted through the ground to their own boots, never reaching the other person as airborne sound. There's something eerie about that. Space seems violent, stars exploding, black holes consuming matter, galaxies colliding, cosmic rays streaming at near light speed. And all of it happens in silence, no soundtrack, no audio accompaniment to the visual chaos. The sun is constantly roaring with nuclear fusion, with flares and coronal mass ejections, and convection currents moving plasma at thousands of kilometers per hour. If you could somehow survive the heat and radiation and stand next to the sun, you still wouldn't hear it. The fusion, the magnetic storms, the massive eruptions throwing billions of tons of plasma into space, all silent because there's no air to carry the sound. Jupiter's Great Red Spot, a storm larger than Earth that's been raging for centuries, rotates in complete silence. Lightning flashes through its clouds, winds scream at hundreds of miles per hour, but there's no one to hear it and no medium to carry the sound anyway. Even on Earth, at high altitudes where the atmosphere becomes very thin, sound changes. At 100,000 feet, the air is so thin that sound propagates poorly. You'd need to shout to be heard from a few feet away. Higher still, approaching the Kármán line at 100 kilometers, where space officially begins, sound essentially stops working. There is one exception, sort of. In the densest parts of intergalactic space, where gas clouds are thick enough, very low-frequency vibrations can propagate. Not sound as we'd recognize it, frequencies far below what human ears can detect, with wavelengths measured in light years, oscillating once per million years or slower. These are pressure waves in galaxy clusters, vibrations moving through hot ionized gas, detectable by X-ray telescopes that can see temperature variations corresponding to compressions and rarefactions. Scientists have recorded these vibrations, translated them into audible frequencies by speeding them up enormously, creating sounds that represent what a galaxy cluster's oscillations would sound like if you could hear them and if they vibrated a trillion times faster. It's technically sound, sort of, maybe, if you define sound very broadly as any mechanical wave in a medium. But it's not sound as we experience it, not vibrations we could hear, not frequencies our ears could detect, not timescales we could perceive. For practical purposes, space is silent. Astronauts on the ISS sometimes report hearing sounds, creaks and groans from the station's structure, expanding and contracting with temperature changes as it moves in and out of sunlight, humming from equipment, the whoosh of air circulation. But these are all sounds inside the station, transmitted through air in the pressurized cabin or through the structure itself. Outside, in the vacuum surrounding the station, there's nothing. Radio transmissions work. Electromagnetic waves that don't need a medium, that propagate through vacuum just fine. Light works. Radiation works. But sound, specifically, does not. This is why spacesuits have radios, why ships communicate electronically, why you need instruments to detect vibrations if you're trying to measure oscillations in spacecraft or satellites, because you can't just listen. Sound is local to mediums, air, water, solid materials. Where there's matter dense enough for molecules to bump into each other at reasonable frequencies, sound can propagate. Where there isn't, it can't. Space mostly isn't. So space is silent, will always be silent, can only be silent given the physics of vacuum and the nature of mechanical waves. No sound has ever crossed the void between stars. No vibration has propagated through interstellar space as sound. It's all light, radiation, cosmic rays, magnetic fields, forces and particles that don't need air. But sound? Sound requires matter, requires density, requires molecules close enough to jostle each other. Space has none of that. So all those dramatic explosions happen silently. All those massive cosmic events unfold without soundtrack. The universe is full of light and violence and beauty and drama, and all of it happens in complete, unbroken, eternal silence, which maybe makes it more profound in a way. The violence without noise, the spectacle without fanfare, just light and motion and change unfolding in the deepest quiet imaginable. The human nose can detect over 1 trillion different scents, far more than previously thought. For a long time, scientists believed humans could distinguish about 10,000 different odors. That was the accepted number, repeated in textbooks, cited in papers, taught to students. 10,000 seemed like a lot, more than enough to navigate the world, identify foods, detect dangers, appreciate the subtle variations in wine or coffee or perfume. But it was wrong, dramatically wrong. In 2014, researchers at Rockefeller University tested human olfactory abilities more rigorously. Instead of using familiar scents like vanilla or roses, they created novel mixtures of odor molecules, combinations subjects had never smelled before, that had no names, no associations, no learned responses. They mixed these molecules in different proportions, creating blends that were chemically similar but perceptibly different if your nose was sensitive enough. Then they tested whether subjects could distinguish between them. The results were surprising. Humans could distinguish far more combinations than expected. Extrapolating from their data, the researchers estimated that the human nose can detect over 1 trillion different scents. 1 trillion. Not 10,000. 1 trillion. That's 100 million times more than the old estimate. It's more scents than there are colors we can see, more than sounds we can distinguish, more than any other sensory modality we possess. Your nose, which you might think of as a secondary sense compared to vision, is actually extraordinarily sophisticated, capable of discriminating between chemical mixtures with astonishing precision. How does this work? You have about 400 different types of olfactory receptors in your nose, protein molecules embedded in the membranes of olfactory neurons in the nasal epithelium. Each receptor type responds to certain molecular features, shapes, sizes, functional groups, chemical properties. When you breathe in, odor molecules dissolve in the mucus lining your nasal cavity and bind to these receptors. Each molecule might activate several receptor types to different degrees, creating a pattern of activation, a signature that your brain interprets as a specific smell. The trillion scent estimate comes from combinatorics. With 400 receptor types, each capable of responding at different intensities, the number of possible patterns is astronomically large. Most odors are mixtures, hundreds of different molecules, each activating multiple receptors, creating complex patterns that your brain can learn to recognize and distinguish. This is why you can tell the difference between Granny Smith and Red Delicious apples, even though both smell like apple. The specific mixture of molecules is slightly different, creating different activation patterns, which your brain perceives as distinct scents. It's why wine experts can identify not just grape varieties, but regions, vintages, production methods. Each variable changes the chemical composition slightly, creating a different olfactory signature, a different pattern recognizable to a trained nose. Your olfactory system is also surprisingly fast. Odor information reaches your brain in milliseconds, faster than visual processing for complex scenes. You can detect some odors at concentrations as low as a few parts per trillion, individual molecules among trillions of air molecules, low enough that you're detecting perhaps a few hundred molecules total. Some odors you're incredibly sensitive to. Mercaptans, the sulfur compounds in natural gas and skunk spray, can be detected at less than 1 part per billion. Geosmin, the earthy smell of rain on dry soil, at about 5 parts per trillion. These are concentrations so low that your nose outperforms many analytical instruments designed to detect trace chemicals. This sensitivity served our ancestors well, detecting rotten food before tasting it, identifying which plants are edible, recognizing the scent of predators or fire, finding mates through pheromones and body odor. All of this depended on olfaction, on being able to distinguish between chemically similar but functionally different scents. We think of ourselves as visual creatures, and we are. Our visual cortex is huge. Our acuity is excellent compared to many animals, but our noses are better than we give them credit for. We just don't train them the way we train our eyes, don't attend to smells as consciously as we attend to sights, don't have vocabulary for describing odors as rich as our vocabulary for colors or shapes. But the hardware is there. The sensitivity exists. 1 trillion distinguishable scents, all accessible to your nose right now if you pay attention. Every breath you take carries information, molecules from your environment, from people around you, from distant sources, all of it dissolving in the mucus in your nose, binding to receptors, creating patterns that your brain analyzes and interprets. You're smelling constantly, even when you're not aware of it. Your brain filters most of it out, focuses attention on novel or important scents, lets the familiar background fade into unconsciousness. But the information is there, processed, available if you choose to notice. This is why scent is so strongly tied to memory. The olfactory bulb, where scent information first arrives in the brain, connects directly to the hippocampus and amygdala, regions involved in memory and emotion. Scent bypasses the thalamus, the relay station that other senses go through, giving it a more direct route to emotional and memory centers. This is why a particular smell can trigger vivid memories, transport you instantly to childhood or a specific moment years ago. The neural pathways are short, direct, emotionally charged. 1 trillion scents. Most of them you'll never encounter, never learn to recognize, never have occasion to distinguish. But the capacity is there, built into your nose, ready to detect chemical variations at resolutions finer than you'd ever consciously notice. Your nose is a precision chemical detector, capable of analyzing mixtures, distinguishing components, identifying sources, all in real time as you breathe. More sensitive than you thought, more powerful than vision in some ways, more sophisticated than almost any technology we've built for chemical analysis. 1 trillion scents, all of them accessible to you right now if you breathe deeply and pay attention. The world is full of odors, subtle and varied, and your nose can detect nearly all of them. You just have to notice. Quantum entanglement allows 2 particles to remain connected across any distance, so that measuring one instantly affects the other. When 2 particles become entangled through interactions, through their creation in certain processes, through various methods, physicists have developed. They form a connected system, not connected by any force we know of, not linked by strings or fields or anything we can detect, but connected nonetheless through their quantum states. Measure one particle, and you instantly know something about the other. Change one, and the other changes correspondingly. No matter how far apart they are, no matter if they're separated by inches or light years, the distance doesn't matter. The connection persists. Einstein hated this. He called it spooky action at a distance, and argued it couldn't be real, that there must be hidden variables, some underlying mechanism we weren't seeing that explained the correlations without requiring instantaneous effects across space. He was wrong. Experiments have confirmed over and over that entanglement is real. The correlations exist. The connection persists across arbitrary distances, and there are no hidden variables. Quantum mechanics really does describe reality this way, strange as it seems. Here's a simplified example. You create two entangled photons with correlated polarizations. Send them in opposite directions, miles or light years apart. Before you measure either one, neither has a definite polarization. Both exist in superposition, simultaneously all possible polarizations at once. But the moment you measure one photon's polarization, forcing it to choose vertical or horizontal or some angle, the other photon's polarization becomes determined instantly. If you measured vertical on one, the other will measure horizontal when you check it. If you measured diagonal on one, the other is the opposite diagonal. The correlation is perfect, instantaneous, independent of distance. This seems to violate relativity. Information appears to travel faster than light. You measure one particle and instantly the other knows what happened. But it doesn't actually allow faster than light communication. You can't control what result you get when you measure the first particle. It's random, probabilistic, fundamentally unpredictable. So you can't encode a message by choosing outcomes. The second observer measuring their particle just sees random results unless they compare notes with you later. Only then, traveling at light speed or slower, do they discover that your measurements were correlated. The correlation is real, but it doesn't transmit information faster than light, doesn't violate causality. It's like magic with very specific limitations. The connection exists, but you can't use it to communicate. You can't send messages, can't transmit data, can't coordinate actions faster than light. What you can do is verify that the connection is real, that measuring one particle affects the other, instantly, regardless of separation. And this has been tested exhaustively. Experiments have entangled photons and separated them by kilometers, then measured them at precisely synchronized times, confirming that the correlations exist even when the measurements happen too quickly for any light-speed signal to pass between them. Other experiments have closed various loopholes, eliminated possible alternative explanations, confirmed that yes, entanglement is real, it works the way quantum mechanics says it does, and reality is genuinely this strange. It's being used now. Quantum cryptography relies on entanglement to create perfectly secure communication channels. Any eavesdropping disturbs the entangled state, revealing the intrusion. Quantum computers use entanglement to create qubits that are correlated in ways classical bits can't be, enabling certain calculations that would be impossible otherwise. But at a fundamental level, entanglement remains deeply mysterious. What is the connection? How does measuring one particle affect the other? Is there some underlying mechanism, or is this just how reality works at the quantum level, without deeper explanation? We don't know. The math works. The predictions match experiments. But what it means, what entanglement tells us about the nature of reality, about space and time and causality, remains debated. Some interpretations say the particles don't have definite properties until measured, and measurement on one forces both to choose consistent values. Others say the universe splits into branches, and you measure one outcome in your branch, while another version of you measures a different outcome in another branch. Still others invoke non-local hidden variables, or pilot waves, or various other exotic explanations. All of them match the data. None can be definitively ruled out or confirmed. What we know is the phenomenon is real. Two particles entangled remain connected regardless of distance. Measure one and the other is affected instantly, no matter how far apart they are. Einstein called it spooky. He was right about that much. It is spooky. It violates our intuitions about locality, about objects having independent existence, about the universe being made of separate parts that only interact through local contact or field influences. Entanglement says particles can be non-local. That separation in space doesn't always mean separation in state. That two things can be one thing in a quantum sense, spread across space, connected in ways we can measure but not fully understand. It's as if the universe doesn't care about distance at the quantum level, as if space itself is less fundamental than we thought, just a classical approximation that breaks down when you look closely at the quantum foundations of reality. Two particles, any distance, instant correlation, no mechanism, no signal, no explanation that makes intuitive sense, just entanglement, one of the strangest confirmed features of reality, happening continuously in labs and experiments and quantum computers, defying explanation while enabling technologies we're only beginning to explore. Spooky action at a distance, real, measurable, still mysterious after a century of quantum mechanics. The universe is stranger than it appears. Entanglement proves it. The Amazon rainforest produces approximately 20% of the world's oxygen, but it also consumes nearly all of it through respiration and decomposition. There's a myth about the Amazon rainforest that feels right, that sounds true, that gets repeated so often it's become accepted fact. The Amazon is the lungs of the earth, producing 20% of the world's oxygen, essential for global breathing, irreplaceable as an oxygen source. The first part is true. The Amazon does produce about 20% of global oxygen through photosynthesis, trees and plants converting carbon dioxide and water into sugars and oxygen, using sunlight as energy. Billions of tons of oxygen released annually into the atmosphere. But here's what's left out. The Amazon also consumes nearly all of that oxygen. Plants respire. At night, when there's no sunlight for photosynthesis, they consume oxygen and release carbon dioxide, just like animals. They're burning sugars to produce energy, using oxygen to do it, releasing CO2 as waste. And during the day, while they're producing oxygen through photosynthesis, they're simultaneously consuming some of it through respiration. The net production is positive. More oxygen created than consumed, but not by as much as you might think. Then there's decomposition. Dead leaves, fallen branches, trees that die and collapse, all of it covered with fungi, bacteria, insects, decomposers that break down organic matter and return nutrients to the soil. And decomposition consumes oxygen, lots of oxygen, the microbes respiring, the chemical reactions oxidizing organic compounds, all of it drawing oxygen from the air. Add it all up. Photosynthesis creating oxygen, plant respiration consuming it, decomposition consuming more, and the net oxygen contribution from the Amazon is close to zero. Nearly all the oxygen produced gets consumed within the forest ecosystem. This doesn't mean the Amazon isn't important. It stores enormous amounts of carbon in its biomass, trees, soil, organic matter. It regulates regional climate, generates rainfall through transpiration, maintains biodiversity, provides habitat for millions of species. But as an oxygen source for the planet, minimal. So where does our oxygen come from? Mostly the ocean. Phytoplankton, microscopic photosynthetic organisms floating in sunlit surface waters, produce about 50 to 80% of Earth's oxygen. They're tiny, often single-celled, but they're everywhere in vast numbers, photosynthesizing continuously, releasing oxygen that doesn't get consumed locally, because the open ocean doesn't have the same dense decomposition ecosystem that terrestrial forests do. Some of that oxygen dissolves in seawater, supporting marine life, but much of it escapes into the atmosphere, accumulating over geological time, building up the 21% oxygen concentration we breathe. The rest comes from various terrestrial ecosystems, grasslands, tundra, boreal forests, and importantly, from the past. The oxygen in the atmosphere is mostly legacy oxygen, produced over hundreds of millions of years and accumulated because not all of it was consumed. Organic matter gets buried before decomposing, turned into coal, oil, peat, sediment, locking away carbon and leaving oxygen behind. This is how Earth's atmosphere became oxygen-rich in the first place. Early photosynthetic organisms, starting about 2.5 billion years ago, began producing oxygen faster than it was consumed by chemical reactions and respiration. Oxygen accumulated, eventually reaching levels high enough to support aerobic life, to create ozone layers, to change the planet fundamentally. And it's still accumulating, slowly, as organic carbon gets buried and oxygen remains in the atmosphere. Though human fossil fuel burning reverses this, we're taking buried carbon and reoxidizing it, consuming oxygen to burn coal and oil and gas, releasing CO2 and depleting atmospheric oxygen slightly. But the oxygen content is so large, about 1 billion tons in the atmosphere, that even our massive consumption barely affects it. We could burn all known fossil fuel reserves, and oxygen would drop by less than 1%. It's not oxygen depletion we need to worry about. It's carbon dioxide accumulation, climate change, ecosystem disruption. Still, the myth persists. The Amazon is Earth's lungs, producing our oxygen, essential for breathing. It's emotionally true, maybe. The Amazon feels vital, irreplaceable, worth protecting. And it is all of those things, just not because of oxygen. Lose the Amazon and oxygen levels wouldn't change noticeably. But lose the Amazon and you lose carbon storage. Billions of tons of CO2 released as trees burn or rot. You lose rainfall generation. The Amazon creates its own weather, recycling moisture through transpiration, generating rain that supports agriculture downwind. You lose biodiversity, millions of species, many undiscovered, endemic to specific regions, unable to survive elsewhere. You lose an entire ecosystem, a functioning whole, a piece of planetary machinery that's taken millions of years to develop and can't be recreated once destroyed. So the Amazon is worth protecting, desperately worth it, just not for the reason most commonly cited, not for oxygen. The oceans do that, and they do it better, producing more net oxygen, distributing it globally through atmospheric mixing, keeping us breathing through phytoplankton that most people never see and rarely think about. The Amazon matters for carbon, for climate, for water, for species, for indigenous peoples, for countless reasons that make it irreplaceable. But oxygen? The Amazon produces a lot and consumes nearly all of it, balanced, cycling internally, contributing little to the global oxygen budget. The lungs of the earth are actually the oceans, phytoplankton, microscopic and vast, invisible but essential, producing the oxygen we breathe while the Amazon quietly cycles carbon and water and maintains one of the most biodiverse ecosystems on the planet. Both are worth protecting. Both are essential. Both are threatened. But understanding what they actually do versus what we think they do matters for knowing how to protect them, for prioritizing conservation, for recognizing where the real dangers lie. The Amazon isn't our oxygen source, but it's still irreplaceable, and that's enough. Time is not constant throughout the universe. It flows at different rates depending on gravity and velocity. Time is personal, not metaphorically, not in the sense that experience is subjective, but literally. The rate at which time passes depends on where you are, how fast you're moving, what gravitational field you're in. Your time and my time are different if we're in different circumstances. Not our perception of time, but actual time, the rate at which physical processes occur, clocks tick, particles decay, aging happens. This is relativity, not just Einstein's theory, but observed reality, confirmed by countless experiments, built into technologies we use daily. We've talked about gravitational time dilation, time moving slower in stronger gravity. But there's also velocity-based time dilation from special relativity, equally strange and equally real. Move faster, and time slows down for you relative to someone stationary. Not because of any mechanical effect, not because motion physically slows clocks, but because time itself passes more slowly for moving objects. This effect is tiny at everyday speeds. Drive a car at 60 miles per hour, and your clock runs slow by about 1/1000th of a second per hour compared to someone standing still. You'd never notice. The effect is negligible. But at speeds approaching light speed, it becomes dramatic. An astronaut traveling at 90% of light speed experiences time at about half the rate of someone on Earth. What feels like 1 year to the astronaut is 2 years for Earth. Travel for 10 years at that speed. 10 years by the astronaut's clock, aging 10 years, experiencing 10 years of life, and return to Earth to find 20 years have passed. Friends have aged 20 years. Children have grown up. The astronaut is younger than siblings who were younger when they left. This is the twin paradox, not actually a paradox, but a real consequence of relativity. If one twin stays on Earth and the other travels at high speed and returns, they'll have aged differently. The traveling twin will be younger, not because of any biological effect of space travel, but because time literally passed more slowly for them. At light speed, which is impossible for anything with mass, but hypothetically, time would stop completely from the perspective of the traveler. Photons, moving at light speed, experience no time. From a photon's perspective, if it could have one, It's created and absorbed in the same instant, regardless of how far it travels from our perspective. This seems impossible. How can time be different for different observers? Isn't time universal, absolute, the same for everyone? No, that's Newtonian physics, and it's wrong. Newton thought time was absolute, flowing uniformly everywhere, an external framework in which events occur. Einstein showed this was false. Time is relative, flexible, dependent on reference frame. There's no universal now that everyone can agree on. Simultaneity is relative. Events that are simultaneous in one reference frame occur at different times in another reference frame, moving relative to the first. This breaks our intuition completely. We think of time as a universal backdrop, everyone experiencing the same moment, the same flow, the same rate. But that's only approximately true when speeds are slow and gravity is weak. At high speeds or in strong gravity, the approximation breaks down, and we've tested this. Atomic clocks flown on airplanes show time dilation effects matching predictions. GPS satellites experience both gravitational time dilation, time runs faster in orbit where gravity is weaker, and velocity-based time dilation. Time runs slower because they're moving fast relative to Earth's surface. Both effects are significant, and GPS wouldn't work without corrections for both. Particle accelerators see time dilation constantly. Muons created in high-energy collisions have very short lifetimes, about 2.2 microseconds before decaying. But when they're moving at 99.9% of light speed, their lifetimes appear much longer from our reference frame. They travel farther than they should before decaying, because time is passing more slowly for them. From the muon's perspective, it lives exactly 2.2 microseconds. From our perspective, moving relative to the muon, it lives much longer. Both perspectives are correct. Both are valid. There's no absolute frame that determines which one is really right. Time is relative, different for different observers, dependent on motion and gravity, flexible in ways we don't experience, but that are absolutely real at extremes. This means there's no universal clock, no absolute time coordinating the universe. Every observer has their own time, their own flow, their own rate, and those rates disagree correctly because there's no single right answer. If you could travel at high speeds, you could effectively travel into the future. Not backwards. Causality is preserved. You can't go back, but forward. Travel at near light speed for what feels like a year, return to Earth, and decades or centuries might have passed. You've jumped forward in time, not by any mechanism beyond simply moving fast and letting time dilation do its work. This is how relativity allows something like time travel, forward only, one way, at different rates, depending on your velocity and path. It's not science fiction, it's physics. Impractical with current technology, but possible in principle. And at cosmic scales, time differences become extreme. Near a black hole's event horizon, time slows so much that you could watch the entire future of the universe unfold in what feels like minutes to you. The universe aging billions of years while you experience a brief fall toward the singularity, or orbiting close to a massive object at high speed. Time for you passes slowly while the rest of the universe ages quickly. Return from that orbit after what feels like a few years, and millennia might have passed elsewhere. Time is not constant, not universal, not the same for everyone. It flows differently depending on where you are, how you're moving, what gravity you're experiencing. Your time is yours, mine is mine, and they don't have to agree, don't have to match, don't have to flow at the same rate. Because time is relative, always has been, always will be, even if it feels absolute from where you're standing. The human genome contains about 3 billion base pairs, but if you printed them out in regular font, the stack would be 200 phone books high. Your genome is long, not metaphorically long, not a lot of information in some abstract sense, but physically long if you tried to write it out. About 3 billion base pairs, 3 billion letters in the genetic alphabet, A, T, G, C, arranged in specific sequences across 23 pairs of chromosomes. Each base pair is a rung on the DNA ladder, a pair of complementary nucleotides linked together, encoding 1 unit of genetic information. 3 billion of them, in every cell that has a nucleus. All of that information compressed into a space so small you need a microscope to see the cell, much less the nucleus, much less the DNA itself. But unpack it, translate it into text, and it becomes massive. If you printed the human genome in standard 12-point font, about 3,000 letters per page, it would take roughly 1 million pages. That's about 200 phone books, the old-style thick ones that used to show up on doorsteps before the internet made them obsolete. A stack 200 phone books high. Just to print the raw sequence, no annotations, no explanations, just A, T, G, C over and over in the specific order that defines you. And that's just one copy. You have 2 copies of most genes, 1 from each parent, so really you have about 6 billion base pairs total, though much of it is identical or nearly so between the 2 copies. Reading it would take forever. If you read at a typical pace, maybe 200 words per minute, and base pairs are sort of like letters, even though they're not words, it would take you over 50 years of continuous reading, 24 hours a day, to get through the entire sequence once. No one has done this. No one will. It would be meaningless anyway. Just endless strings of ATG, CAT, GSAT, GC, with patterns too subtle to recognize by eye, interrupted by long stretches of repetitive sequences that don't code for anything. Only about 1.5% of your genome actually codes for proteins, the genes that produce the molecules that do most of the work in your cells. The rest is regulatory sequences, introns that get spliced out, repetitive elements, viral DNA remnants, sequences with unknown function, and large stretches that seem to do nothing at all. But it's all there, in every cell, all 3 billion base pairs, maintained, replicated, passed on to daughter cells every time cells divide. The information density is extraordinary. 3 billion base pairs in a nucleus, a few micrometers across, organized into chromosomes that are visible under a microscope only when they condense during cell division, otherwise spread out as chromatin, so diffuse it's barely distinguishable from the rest of the nuclear contents. And yet, if you extracted it, uncoiled it, stretched it out, that DNA from one cell would be about 2 meters long, 6 feet, roughly human height. All packed into a nucleus 6 micrometers in diameter, about 1/10 the width of a human hair. That's a packing ratio of over 100,000 to 1, like fitting 60 miles of thread into a tennis ball. This is achieved through multiple levels of coiling and folding. DNA wraps around histone proteins, forming nucleosomes. Nucleosomes coil into chromatin fibers. Chromatin fibers fold into loops and domains, organized by scaffolding proteins. Everything packed together with extraordinary precision, allowing access when needed for transcription or replication, but keeping it compact the rest of the time. If you could print out the genomes of all the cells in your body, you'd need trillions of copies, one per cell, each one 200 phone books. The total would fill multiple large libraries. All of that information, carried in your body, in every cell, duplicated perfectly every time cells divide. The copying process is remarkably accurate. About 1 error per billion base pairs during replication, which sounds good until you realize you're copying 6 billion base pairs every time a cell divides. So there are several errors per cell division on average. Most are caught and corrected by proofreading mechanisms, but some slip through, becoming mutations, changes in the sequence that get passed on to daughter cells. Over your lifetime, your cells accumulate mutations. Most are harmless, occurring in non-coding regions or in genes that aren't essential, or in ways that don't affect function. Some cause problems: cancer, aging, genetic diseases. A few might be beneficial, though beneficial mutations in somatic cells don't get passed to offspring and don't affect evolution. But the genome persists, mostly unchanged, through all of this. 3 billion base pairs, carefully maintained, repaired when damaged, copied precisely enough that you're still recognizably you, despite trillions of cell divisions since you were a single-cell embryo. And it's old. The sequences in your genome have been passed down through generations, through your parents and grandparents, and back through evolutionary time, with small changes accumulating, but much of it conserved, recognizable, shared with other humans and with related species. Some sequences in your genome are identical to sequences in mice, in fish, in fruit flies, because they perform essential functions that haven't changed significantly in hundreds of millions of years. Evolution keeps what works, modifies what needs improvement, experiments with new combinations, but it all comes down to those base pairs. A, T, G, C. 3 billion of them, arranged in orders that define you, that code for proteins that build your body, that regulate when genes turn on or off, that contain your evolutionary history and your individual uniqueness. 200 phone books, 1 million pages, 50 years of continuous reading, all of it packed into every cell in your body, invisible, essential, defining what you are at the most fundamental biological level. The instruction manual for building and maintaining you, written in 4 letters, 3 billion letters long, compressed into spaces so small you can't see them but present in every living cell. Your genome, long enough to fill libraries, if printed, compact enough to fit in spaces smaller than dust in reality. Information made physical, inherited and maintained, the code that makes you possible, 3 billion base pairs, 200 phone books high, all of it inside you. Dark matter makes up about 27% of the universe, but we can't see it, touch it, or detect it directly. We only know it exists by its gravitational effects. Most of the universe is missing, not missing in the sense that it disappeared or that we lost track of it. Missing in the sense that it's there. We can detect its effects, measure its influence, calculate how much of it exists, but we can't see it, can't touch it, can't interact with it through any means except gravity. This is dark matter, and it makes up about 27% of the universe's total mass energy content. Everything we can see, stars, planets, gas clouds, galaxies, all the normal matter made of protons, neutrons, electrons, all the stuff we're familiar with. makes up less than 5% of the universe. The rest is dark, hidden, present but undetectable except through its gravitational influence. We discovered dark matter by noticing that galaxies don't behave the way they should if they only contain the matter we can see. Stars at the edges of galaxies orbit too fast. They should fly off into space, unable to remain bound to the galaxy unless there's more mass present than we can account for. So either our understanding of gravity is wrong, which is possible but seems unlikely given how well general relativity works everywhere else, or there's mass we can't see, dark matter distributed in a halo around galaxies, providing the extra gravity needed to hold everything together. Galaxy clusters show the same effect. They're too massive, gravitationally, for the visible matter they contain. And gravitational lensing, the bending of light around massive objects, reveals mass distributions that don't match where the visible matter is. The light bends around dark matter halos, showing us where the mass is even though we can't see what's causing it. The cosmic microwave background, the afterglow of the Big Bang, also shows evidence for dark matter. The patterns of temperature fluctuations match models that include dark matter, but don't match models with ordinary matter alone. All the evidence points to dark matter existing. About 5 times more dark matter than ordinary matter in the universe, distributed in halos around galaxies, forming the scaffolding on which large-scale structure is built, influencing the evolution of the cosmos from the earliest moments after the Big Bang. But we don't know what it is. It's not normal matter. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. It doesn't seem to interact via the strong nuclear force or the weak nuclear force either, or if it does, so weakly we can't detect it. It only interacts gravitationally, as far as we can tell. Mass that pulls on other mass, bending space-time, affecting the motion of stars and galaxies, but otherwise invisible and intangible. Candidates have been proposed. WIMPs, weakly interacting massive particles, were a leading contender for years. Theoretical particles that would have mass would interact gravitationally, might interact weakly through the weak nuclear force, but so rarely we'd never notice. Experiments have searched for WIMPs for decades, building detectors deep underground to shield them from cosmic rays, looking for the rare interaction where a WIMP collides with a normal atom. Nothing. No definitive detection. Either WIMPs don't exist, or they interact even more weakly than predicted, or we're looking in the wrong places. Other candidates, axions, sterile neutrinos, primordial black holes, exotic particles not part of the standard model. Each has advantages and problems. None has been confirmed. We know dark matter exists because of its gravitational effects, but what it's made of remains one of the biggest unsolved problems in physics. And dark matter is just part of the story. Another 68% of the universe is dark energy. Even more mysterious, an unknown force causing the universe's expansion to accelerate, pushing galaxies apart at ever-increasing speeds. We know even less about dark energy than dark matter. So adding it up, 5% ordinary matter, the stuff we can see and touch and interact with, 27% dark matter, invisible but gravitationally present, 68% dark energy, even stranger, causing cosmic acceleration. We understand less than 5% of the universe's contents. The rest is dark, unknown, detectable only through its effects on the small fraction of reality we can actually observe. This should be humbling, We've mapped the cosmos, built telescopes to see the most distant galaxies, calculated the age and size of the universe, understand stellar evolution and galaxy formation and cosmology in impressive detail. But all of that is based on understanding 5% of what's out there. The rest is mystery. We know it's there, we've measured its abundance. We can see what it does, but we don't know what it is. Dark matter could be exotic particles unlike anything we've discovered, or something weirder, modifications to gravity we haven't understood, extra dimensions affecting how mass behaves, physics beyond our current theories. We're searching. Detectors deep underground, particle accelerators creating collisions at high energies, hoping to produce dark matter particles we can detect. Telescopes mapping dark matter distributions through gravitational lensing. All of it trying to answer, what is this stuff? Because it's not optional. It's not a detail we can ignore. Dark matter dominates the universe's mass. It shaped cosmic structure, enabled galaxies to form, affects everything we see even though we can't see it. And dark energy dominates the universe's energy, determining its ultimate fate, pushing everything apart until eventually galaxies beyond our local group recede beyond the cosmic horizon, unreachable, invisible, leaving the universe dark and empty and cold. 5% visible, 27% dark matter, 68% dark energy. We're living in a universe we barely understand, made mostly of things we can't detect, surrounded by mysteries we're only beginning to probe. And yet we know these things exist, know they're real, know their abundances, their distributions, their effects. We just don't know what they are. Dark matter, invisible, present, essential. 27% of everything, hidden in plain sight, detectable only through the gravitational fingerprints it leaves on the 5% we can actually see. The universe is mostly dark, mostly unknown, and we're searching for lights in that darkness, trying to understand what fills the cosmos, what shapes reality, what makes up most of everything that exists. Someday, maybe, we'll find answers, detect dark matter directly, understand dark energy, fill in the missing 95%. Until then, we navigate a universe where most of what's real is invisible, known only through its effects, present but fundamentally mysterious. Dark matter, dark energy, the dark universe, waiting to be understood. The quietest place on Earth is a room at Microsoft headquarters with sound absorption at 20.6 decibels. Silence has a sound. Not metaphorical silence, not the quiet of a library, or the stillness of a winter night. Real silence, physical silence, the absence of nearly all acoustic vibration. And it's louder than you think, or stranger anyway. At Microsoft's headquarters in Redmond, Washington, there's a room called an anechoic chamber, a space designed to absorb all sound, to eliminate reflections, to create an environment as close to perfect acoustic silence as human engineering can achieve. The walls, floor, and ceiling are covered in wedges of sound-absorbing foam, arranged in precise patterns that trap incoming sound waves, preventing them from reflecting back into the room. The entire chamber sits on springs, isolated from the building around it, preventing vibrations from outside from entering. The room's background noise measures at 20.6 decibels. That's negative decibels, quieter than the threshold of human hearing, which is defined as 0 decibels. The room is so quiet that it goes below 0, into a range where sound is present but undetectable to normal hearing. At 20.6 dB, there's almost no sound at all. No air conditioning hum, no traffic noise, no electrical buzz, no distant voices, nothing. And in that silence, strange things happen. You hear yourself. Not your voice, necessarily, though that too. You hear your body. Your heartbeat becomes audible, a rhythmic thump you've lived with your entire life, but never consciously heard because it's always masked by environmental noise. Your breathing sounds loud, intrusive, each inhale and exhale obvious. Your joints creak when you move, your stomach gurgles. Blood rushing through vessels near your ears creates a whooshing sound, pulsing in time with your heartbeat. Your ears themselves generate faint sounds, spontaneous otoacoustic emissions, tiny vibrations of the hair cells in your cochlea that happen even in silence. You hear the electrical activity of your nervous system, some people report. Or you think you do, whether it's actual neural noise or something else. Some artifact of your auditory system trying to make sense of the absence of input isn't entirely clear. Most people can't stay in the room for long. The longest anyone has lasted is about 45 minutes. It's disorienting, unsettling, almost unbearable after a while. Your sense of balance, which partly depends on spatial cues from sound reflections, stops working properly. You lose spatial orientation. Some people hallucinate, seeing or hearing things that aren't there as their brains try to fill the sensory void. This is partly because humans aren't designed for total silence. We evolved in environments with constant acoustic information: wind, water, animals, other people, rustling vegetation, our own footsteps. Our auditory system expects input, processes it constantly, uses it for spatial awareness, threat detection, social communication. Take all that away, and the system struggles. It searches for signal, amplifies internal noise, tries to construct a soundscape from anything available. And what's available is your body, your heartbeat, breathing, digestion, all the internal sounds normally masked by the world around you. The room is used for testing. Microsoft uses it to test audio equipment, speakers, microphones, headphones, in an environment with no acoustic interference. You can measure exactly what a device produces or detects without contamination from room reflections or background noise. It's also used for research. Audio engineers study sound propagation, psychoacoustics, how humans perceive silence and quietness. Because silence isn't just the absence of sound, it's a perceptual state, something your brain constructs and responds to, something that can be disorienting or calming or eerie, depending on context. In normal environments, silence is never complete. There's always something: air molecules vibrating, pressure fluctuations, distant sounds attenuated but present. A quiet room might measure 30-40 dB. A whisper is about 30 dB. Rustling leaves, 20 dB. Breathing, 10 dB. But in the anechoic chamber, you drop below all of that, below breathing, below the quietest whisper, below the threshold of hearing, into a regime where sound effectively stops. And it's strange, uncomfortable, alien, because we're not meant to experience it. Silence like this doesn't exist naturally. Even in the deepest caves, the most remote deserts, the quietest nights, there's always something: wind moving air, earth settling, your own movement. Complete silence requires artificial construction, engineered spaces designed specifically to eliminate sound. And when you experience it, when you sit in that 20.6 dB chamber, you realize that silence isn't empty. It's full of you, your body, always making noise, always vibrating, always present, but normally hidden beneath the acoustic noise of the world. In true silence, you become the loudest thing. Your heartbeat, your breathing, your joints, your digestion, all of it foreground instead of background. Impossible to ignore, sometimes overwhelming. 45 minutes is the record. Most people last less. They leave feeling disoriented, relieved to return to normal acoustic environments where background noise masks internal sounds, where reflections provide spatial cues, where the world sounds like it should. The quietest place on earth. 26 decibels. Quieter than any natural environment. So quiet it reveals sounds you didn't know you were making, that you've carried with you your entire life, that only emerge when everything else is silenced. And it's unsettling. Beautiful in a way, this engineered perfection, this achievement of near total silence, but also uncomfortable, alien, wrong, because humans need sound, need acoustic information, need the world to make noise, even if it's just a little, even if it's barely noticeable. Complete silence isn't peaceful. It's disorienting. It's too much absence, too much isolation, too much of your own body and not enough of everything else. The quietest place on earth, where silence has sound, where you become the loudest thing, where 45 minutes is the limit of human tolerance, because silence, perfect silence, is stranger than you'd think. Dolphins have names for each other and will respond when called by their signature whistle. We've known for a long time that dolphins are intelligent. They solve problems, use tools, exhibit self-awareness, recognize themselves in mirrors, cooperate in complex hunting strategies. They have large brains relative to body size, with regions associated with higher cognition developed to degrees comparable to primates. But intelligence is one thing, language is another, and dolphins appear to have something very much like names. Each dolphin develops a signature whistle, a unique acoustic pattern, usually established in the first year of life, that identifies that individual. It's not random. It's not instinctive. Each dolphin invents their own signature, different from their parents, different from siblings, different from any other dolphin in their social group. And other dolphins learn these signatures. They recognize them. They respond to them. Researchers have played recorded signature whistles to dolphins and observed their reactions. When a dolphin hears its own signature whistle played back, it responds, approaches the speaker, vocalizes, exhibits behaviors consistent with recognizing that someone is calling them. When they hear another dolphin's signature, they don't respond the same way. They recognize it as not theirs, as belonging to someone else. Sometimes they'll produce that other dolphin's signature, copying it, as if saying the other dolphin's name. This is unprecedented in non-human animals. Other species use calls to communicate, alarm calls, mating calls, territorial calls. Some species have regional dialects, learned variations in calls that differ between populations. But signature whistles appear to be something more, individual identifiers, used referentially, calling specific individuals the way we use names. Dolphins use these signatures throughout their lives. Mothers and calves call to each other using signatures, maintaining contact even when separated. Social groups use signatures to coordinate, to identify who's who, to maintain relationships. And here's what's particularly striking. When dolphins are separated, when a calf is taken from its mother, or when social groups are split, the dolphins will call each other's signatures for extended periods, as if searching, as if trying to make contact with a specific individual they recognize and miss. It looks functionally like calling someone's name, not just making noise, not just generic social calling, but producing a specific signal associated with a specific individual, expecting that individual to respond. This implies several cognitive abilities. Dolphins must have some concept of individual identity, that other dolphins are distinct individuals, that there's a specific other who corresponds to a specific signature. They must remember these signatures, store them in memory, associate them with individuals. They must be able to voluntarily produce another's signature, copying it accurately enough to be recognized. And they must use these signatures intentionally, communicatively, to refer to specific others in a way that approximates naming. This is complex. It requires social cognition, memory, vocal learning, intentional communication. It's far beyond simple, conditioned responses or instinctive vocalizations. It's closer to language than anything we've seen in non-human animals, outside of maybe some great apes using sign language or symbol systems taught by humans. But dolphins do this naturally, without human teaching, using their own vocal system, in the wild and in captivity, as part of their ordinary social behavior. The signature whistles are part of a larger communication system. Dolphins produce many sounds, clicks for echolocation, burst pulses in social contexts, various whistles beyond signatures. They seem to combine sounds in ways that might carry meaning, though we don't understand their communication system well enough to translate it. But signatures we understand. Their names, individual identifiers, used to call specific others, responded to when heard, copied and produced by social partners. Dolphins have names, for themselves, for each other, and they use them the way we do, to maintain contact, to call attention, to refer to absent individuals, to coordinate socially, to express relationships. This changes how we think about dolphin intelligence, about communication in non-human species, about whether language, or something like language, something that serves similar functions, is unique to humans, or emerges naturally in species with the right cognitive abilities and social structures. Dolphins aren't speaking human languages. They're not constructing complex grammar or abstract concepts the way we do, but they're naming each other, calling, responding, recognizing individuals through acoustic signatures that function as names. It's a form of symbolic communication, a sound standing for an individual used referentially, understood by social partners, maintained across lifespans. Language or proto-language or something in between. Dolphins with names, calling to each other across the ocean, responding when called, remembering signatures of individuals they've known, using those signatures to maintain social bonds, coordinate behavior, express recognition, and relationship. We're not the only species that names, that calls to specific others, that uses symbolic sounds to refer to individuals. Dolphins do it too, have been doing it for millions of years, long before humans existed, swimming through oceans, calling names, maintaining relationships through sound, intelligent, social, communicative in ways we're only beginning to understand. Dolphins with names, speaking to each other, recognizing each other, calling through the water, waiting for the response that says, "Yes, I'm here. I hear you. I know who you are, because you called my name, and I know my name, and I know yours." The speed of light is not the universe's speed limit for space itself, only for objects moving through space. The speed of light is absolute. Nothing with mass can reach it. No signal, no information, no influence can travel faster. It's the universal speed limit, fundamental to relativity, built into the structure of space-time. But that's only for objects moving through space. Space itself isn't limited. Space can expand faster than light, and does. This seems like a contradiction. How can anything be faster than light if light is the ultimate speed limit? But it's not a contradiction because expansion isn't motion through space. It's space itself growing, stretching, increasing the distance between objects without the objects actually moving. Think of it like raisins in a rising loaf of bread. As the bread bakes and expands, the raisins move apart from each other, not because they're moving through the bread, but because the bread itself is expanding, carrying the raisins along with it. The raisins aren't violating any speed limits. They're stationary relative to the dough around them. It's the dough itself that's expanding. The universe works the same way. Galaxies aren't moving through space faster than light. They're being carried apart by the expansion of space between them. And that expansion has no speed limit because it's not motion in the traditional sense. Einstein's equations allow this. General relativity doesn't forbid space from expanding at any rate. The speed limit applies to objects moving through space-time, not to space-time itself changing. And we observe this. Distant galaxies are receding from us faster than light speed, not because they're moving faster than light through space, but because space between us and them is expanding so rapidly that the distance grows faster than light could cross it. These galaxies are beyond the cosmic horizon, the distance beyond which light hasn't had time to reach us since the Big Bang. We can't see them. We never will. They're receding faster than their light can travel toward us. The light leaves the galaxy traveling toward us at light speed, but space is expanding fast enough that the distance actually increases, despite the light's motion. It's like swimming against a current that's faster than you can swim. You're moving forward, but the current carries you backward faster, so you lose ground despite your effort. Distant galaxies are like that. Their light is traveling toward us, but space expands faster than it travels, so the light never gets closer. It's trapped in expanding space, unable to cross the gap no matter how long it travels. This is why the observable universe has a limit, not because space ends, but because light from beyond a certain distance can't reach us. The expansion is too fast. The universe is too young for light to have covered that distance, despite expansion working against it. Currently, the observable universe is about 46 billion light-years in radius, much larger than 13.8 billion light-years, which you might expect if light had been traveling for 13.8 billion years since the Big Bang. But space has been expanding during that time, stretching distances, pushing distant objects farther away. So light emitted 13.8 billion years ago has been traveling through expanding space, and the objects that emitted it are now much farther than 13.8 billion light-years away. And the expansion is accelerating. Dark energy, that mysterious 68% of the universe's content, is pushing space apart faster over time. Eventually, in the distant future, distant galaxies will recede so fast that they disappear beyond the cosmic horizon, their light unable to ever reach us again. the universe will appear to empty out. Local galaxies, bound together by gravity in our galaxy cluster, will remain, but everything else will recede, redshift into invisibility, vanish beyond the horizon as expansion accelerates. Billions of years from now, observers in our galaxy would see a much emptier universe, fewer galaxies, less cosmic microwave background radiation, less evidence of the Big Bang. They might conclude they live in a small, isolated universe, not realizing that countless galaxies exist beyond the horizon, receding faster than light, forever out of reach. This is allowed because space isn't a thing that moves. It's the fabric within which motion happens, and the fabric can stretch without limit because it's not moving through anything. It's expanding into itself, carrying everything with it, respecting local speed limits while violating global ones. Nothing travels faster than light through space, but space itself expands faster than light, carrying distant galaxies away from us at speeds that make them unreachable, invisible, forever beyond the horizon of what we can observe. The speed of light is the universe's speed limit for motion, for particles, for information, but not for space. Space plays by different rules, expands at its own pace, accelerates or decelerates based on its energy content, carries galaxies along for the ride without moving them at all in the traditional sense. And the result is a universe where distant objects recede faster than light, where horizons limit what we can see, where the cosmos is larger than we can ever observe, because expansion has pushed most of it beyond reach. The speed of light is absolute. The speed of space is not, and that makes all the difference. Your brain is more active when you're asleep than when you're watching television. Sleep is not rest, not for your brain. Your body rests, yes. Muscles relax, heart rate slows, metabolism decreases, energy is conserved. But your brain? Your brain works differently, maybe even harder, during sleep than during much of waking life. Brain activity during sleep is intense, not uniformly. Sleep has stages, cycles, each with different patterns of neural activity. But during REM sleep, when you dream, brain activity in many regions exceeds waking levels. Neurons fire rapidly, networks activate intensely, blood flow increases, glucose consumption rises. Your brain is busy, processing memories, consolidating learning, maintaining neural connections, clearing waste products, doing maintenance that can only happen when you're not conscious, when you're not demanding attention and resources for sensory processing and voluntary action. Compare this to watching television. When you watch TV, your brain is relatively passive. You're receiving visual and auditory input, processing it, understanding narrative or information, but you're not generating much, not solving problems, not creating memories worth consolidating, not engaging motor systems or decision-making processes. You're consuming, not producing. Brain activity during passive TV watching is lower than during reading, lower than during conversation, lower than during problem-solving or creative work. Definitely lower than during REM sleep, where your brain is generating entire imagined worlds, crafting narratives, simulating experiences, all without external input. This is measurable. fMRI scans show lower overall brain activity during TV watching compared to sleep, particularly compared to REM sleep. EEG shows different patterns, slow waves during TV watching indicating relaxed waking states, versus the high-frequency activity during REM, that resembles waking consciousness. Television is designed to be easy to process. It feeds you information at a controlled rate, with visual and auditory channels conveying meaning directly, requiring minimal effort to understand. It's relaxing because it's not demanding. Your brain can coast, passively receiving without much active processing. This isn't necessarily bad. Relaxation has value. Rest has value. Not every moment needs to be cognitively demanding. But it does mean TV watching isn't particularly stimulating to the brain, isn't challenging in ways that promote learning or growth, isn't activating networks associated with creativity or problem solving. Sleep, meanwhile, is essential. Deprive someone of sleep and cognitive function deteriorates rapidly. Memory consolidation fails. New information doesn't transfer from short-term to long-term storage. Decision-making suffers. Mood deteriorates. Eventually, hallucinations begin. Psychosis sets in. The brain starts failing at basic functions. This is because sleep isn't downtime. It's work time. The brain is sorting memories, deciding what's worth keeping, strengthening connections that matter, weakening those that don't. It's clearing out waste products that accumulate during waking, beta amyloid and tau proteins that, if left uncleaned, contribute to neurodegenerative diseases. The glymphatic system, a waste clearance system in the brain, is most active during sleep. Cerebrospinal fluid flushes through brain tissue, washing away metabolic byproducts, keeping the neural environment clean. This can only happen efficiently during sleep, when neurons aren't firing constantly, when there's space between cells for fluid to flow. Dreams are byproducts of this processing, or maybe they're integral to it. We're not entirely sure. But REM sleep, when most vivid dreams occur, is when the brain is most active, when consolidation is most intense, when emotional processing happens. Your brain is working, harder than during TV watching, harder than during much of waking life, except the most cognitively demanding tasks. This is why sleep deprivation is so harmful. You're not just tired, you're preventing essential maintenance, skipping processes that can only happen during sleep, allowing waste to accumulate and memories to degrade. And why television, despite being relaxing, isn't restorative in the same way. It's passive consumption, easy, undemanding. Your brain activity drops, you relax, but you're not getting the active processing that sleep provides, not consolidating or clearing or maintaining. Sleep is essential. Television is optional. And your brain knows the difference, responds differently, works harder during sleep, despite your subjective experience of unconsciousness and rest. So when you sleep, your brain is busy, more active than when you're staring at screens, absorbing content, coasting through passive entertainment. Sleep is work, essential work, the kind your brain needs to function, to maintain itself, to stay healthy and sharp and capable. Television is rest, easy, undemanding, sometimes welcome after a long day, but don't confuse the two. Sleep is when your brain is most active, most essential, most irreplaceable, even if it doesn't feel like it. Even if you're unconscious, unaware, experiencing nothing or only dreams, your brain is working harder than you think, doing what needs to be done. And it's more active during that work than during most waking activities, including watching television. Sleep, essential, active, work, more than rest, more than downtime. The time when your brain does what it can't do while you're awake, processing, consolidating, clearing, maintaining, working harder than almost anything else you do, while you dream or don't, unconscious and resting, your brain intensely active in the darkness of sleep. Every person who has ever lived has looked at the same moon, seeing roughly the same face we see today due to tidal locking. There's something connecting all of us across time, something simple, ancient, shared by every human who ever lived. The moon. Every person in history, your ancestors, their ancestors, back through countless generations, back through the entire span of human existence, has looked up at night and seen the same moon you see. Not just a moon, the same moon, with the same face, the same pattern of dark Maria and bright highlands, the same features arranged in the same way. This is because the moon is tidally locked to Earth. It rotates on its axis at exactly the same rate it orbits Earth, so the same side always faces us. The rotation period equals the orbital period, about 27.3 days, meaning from Earth's perspective, the moon doesn't rotate at all. We always see the same face. This has been true for billions of years, since shortly after the moon formed. Tidal forces from Earth gradually slowed the moon's rotation until it became locked, synchronizing its rotation with its orbit, freezing one face toward Earth forever. So every human who's ever lived, from the first Homo sapiens 300,000 years ago, to your great-great-grandparents, to you, to everyone living today, has seen the same lunar face, the same patterns, the same dark seas, the same bright craters, the same rabbit or face or whatever pattern you see in the arrangement of light and dark. Ancient humans saw this moon, looked up at night, tracked its phases, used it to measure time, told stories about it, worshipped it, navigated by it. And they saw what you see, the same face, the same features, unchanging across millennia. Every culture that ever existed has known this moon. Every human has looked at it at some point. Some feared it, some loved it, some studied it, some painted it, some wrote poetry about it. But they all saw the same moon, the same face, the same pale light, reflecting from the same ancient surface. The features themselves are ancient. The dark Maria, seas, though they're not water, are basaltic lava plains formed by ancient volcanic eruptions, mostly between 3 and 4 billion years ago. The bright highlands are older crust, original moon material from when the moon formed about 4.5 billion years ago. The craters are impact scars from asteroids and comets, most of them also ancient, from early solar system bombardment billions of years ago. A few craters are relatively young. Tycho, bright and prominent with rays of ejecta spreading across the surface, is only 100 million years old. Copernicus is about 800 million years old. But most features, the ones that define the face we see, are billions of years old, unchanged since long before life existed on Earth. So every human has looked at ancient history, a surface that remembers the early solar system, that bears scars from bombardments that happened before Earth's continents formed, before oceans stabilized, before life began. And we've all seen it. All looked up at that same ancient face, seeing roughly what our ancestors saw, what their ancestors saw, back through the entire human lineage. The moon connects us, temporally across generations, geographically across cultures. We've had different languages, different religions, different technologies, different understanding of what the moon is, but we've all seen it, all looked up at night and found that pale light, that familiar face hanging in darkness. It's one of the few constants in human experience, The moon, unchanging, reliable, present for every person who ever lived to see it. A shared experience across all of human history, connecting us to ancestors we'll never know, who lived in worlds we can barely imagine, but who looked up at night and saw what we see. And it's not just humans. Every animal with eyes capable of seeing it has looked at the same moon. Dinosaurs saw this moon, though it was closer then, appearing larger in the sky. Early mammals scurrying through Mesozoic nights. Every species that's ever lived and looked upward has seen the same lunar face, the same patterns, the same light. The far side, of course, is different. We never see it from Earth. It's not dark. It gets just as much sunlight as the near side. But it's hidden from us, unseen until spacecraft orbited the moon and photographed it. And it looks different. Fewer Maria, more heavily cratered. A face we never knew about until the space age. But the near side, the face toward us, has been visible forever. Since the moon formed, since tidal locking occurred, that same face has watched Earth spinning beneath it, watched continents drift, oceans form, life evolve, species rise and fall, humans appear and spread across the planet. The moon is older than us, older than most things we encounter, and it's been showing us the same face the entire time, constant while everything else changed, reliable while civilizations rose and collapsed, still there above while generations lived and died. Every person who has ever lived has looked at the same moon, has seen the same face, has shared that experience across time, across culture, across every barrier that divides us. And maybe that's comforting. Maybe it suggests continuity, connection, something shared deeper than language or culture or time. Or maybe it's just tidal locking, physics doing what physics does, rotation and orbit synchronized through gravitational forces. Nothing meaningful, just coincidence that we happen to see the same side. But either way, it's true. Every human has looked at the same moon. Your ancestors saw what you see, their ancestors before them, all the way back through time, to the first humans who looked up and wondered what that light was, what it meant, why it changed shape but always showed the same patterns. They didn't know it was a world, a sphere, a place you could someday visit, but they saw it, the same face you see, the same moon. And every person who comes after you will see it too. Your children, their children, generations into the future. As long as humans exist and look upward, we'll see the same moon, the same face, the same ancient patterns, connecting all of us, past, present, future, human and animal. Every living thing that's ever looked up, all seeing the same moon, all sharing that experience, that light, that ancient familiar face hanging in darkness, constant, unchanging, shared. The moon, our moon, everyone's moon, the same moon, always. About 330 billion cells die in your body every day, yet most of them are replaced. You are dying, constantly, cell by cell, in a process so continuous and thorough that you're essentially being rebuilt in real time, old parts discarded, new parts grown, the whole system maintained through endless cycles of death and renewal. About 330 billion cells die in your body every day. That's roughly 1% of your total cells, dying, being broken down, cleared away, replaced. 330 billion every day. It sounds catastrophic. It sounds like cellular apocalypse happening inside you continuously. But it's normal, necessary, healthy. Most cells have lifespans. They're not meant to last forever. They divide, they function, they age, they die. Some die from damage, infections, toxins, mechanical stress, random accidents of chemistry. But most die on a schedule, programmed cell death called apoptosis, a deliberate self-destruction that eliminates old or damaged cells before they become problems. Apoptosis is controlled suicide. The cell detects signals, internal timers, damage sensors, instructions from immune cells, and activates its own death machinery. Enzymes called caspases chop up proteins, dismantle cellular structures, fragment DNA. The cell shrinks. Its membrane forms blebs. It packages itself into neat little bundles that neighboring cells or macrophages can engulf and digest cleanly. No mess, no inflammation, no release of toxic contents into surrounding tissue. Just orderly dismantling, recycling of components, space made available for new cells to take its place. Different cells have different lifespans. Red blood cells last about 120 days, circulating through your bloodstream carrying oxygen, then dying and being recycled by the spleen and liver. White blood cells vary, some last days, others years, depending on type and function. Cells lining your small intestine last only about 5 days, constantly abraded by food passing through, replaced continuously to maintain the protective barrier. Skin cells on the surface last about 2 to 4 weeks before they die and flake off. You shed millions of them daily, dead cells becoming dust, a continuous sloughing off of your outermost layer. The cells beneath divide to replace them, pushing upward, differentiating, eventually reaching the surface where they too will keratinize, die, flake away. Some cells last much longer. Neurons in your brain and spinal cord are mostly not replaced. You have roughly the same neurons at age 70 that you had at age 7, though they've changed, grown new connections, pruned old ones, adapted over time. Cardiac muscle cells are also long-lived, though there's some slow replacement throughout life, about 1% per year renewed, but most cells turn over. Most are replaced on schedules ranging from days to months to years. Add it all up, and about 330 billion cells die per day. Most are blood cells and gut lining cells, tissues with high turnover rates. But every tissue contributes: bone cells, liver cells, lung cells, muscle cells, all dying and being replaced according to their respective schedules. And somehow, through all this death, you remain you. Your tissues maintain their structure. Your organs continue functioning. Your body persists despite being in constant flux at the cellular level. It's like the ship of Theseus, the philosophical thought experiment. If you replace every plank in a ship over time, is it still the same ship? Your body does this continuously. Every few years, most of your cells have been replaced. The atoms in those cells have been replaced even faster, cycled through metabolism, taken in from food, expelled in waste or breath or sweat. You are not the same physical matter you were a decade ago. You're a pattern, a process, a continuous replacement of parts that somehow maintains identity despite having almost nothing in common materially with your past self. The dead cells are cleared away efficiently. Macrophages, immune cells specialized for phagocytosis, patrol tissues, engulfing dead cells, debris, anything marked for removal. They digest what they eat, break it down into components that can be recycled or excreted. Some cell death is wasteful, spilling contents into tissues, causing inflammation, requiring cleanup. This is necrosis, uncontrolled cell death from injury or disease. It's messy, damaging to surrounding, Cells, something the immune system has to deal with aggressively. But most cell death is apoptosis, clean and controlled, cells dismantling themselves neatly, minimizing impact on neighbors, making recycling easy. And then new cells replace them. Stem cells divide, differentiating into whatever cell type is needed. Progenitor cells committed to specific lineages divide and mature. Existing cells in some tissues divide directly, one becoming two, maintaining population size. The balance is precise. Too much cell death without replacement causes tissue atrophy, organs failing, systems declining. Too much cell division without death causes tumors, uncontrolled growth, cancer. The equilibrium, death matched by replacement, division matched by apoptosis, maintains health. This is why chemotherapy is so harsh. It targets rapidly dividing cells, which include cancer, but also hair follicles, gut lining, bone marrow producing blood cells. The treatments kill cells indiscriminately in high turnover tissues, causing hair loss, digestive problems, immune suppression. The cancer dies, hopefully, but so do many healthy cells, and recovery depends on those healthy tissues regenerating faster than the cancer. But normally, the system works. 330 billion cells die per day, and roughly the same number are born, keeping everything in balance, maintaining you as a coherent organism despite the constant cellular turnover. It's happening right now. As you lie there, cells in your gut are dying, sloughing into the intestinal lumen to be digested and excreted. Red blood cells are dying, being filtered out by your spleen. Skin cells on your surface are dying, flaking off onto sheets and clothes. Immune cells are dying, having completed their missions or reached their lifespans. And beneath, new cells are being born. Stem cells in bone marrow producing new blood cells. Basal cells in skin dividing to replace the surface layer. Intestinal stem cells in crypts dividing to renew the gut lining. Birth and death, constantly everywhere in your body, maintaining the pattern that is you through continuous renewal. You are not a static thing, you're a process, a river that stays the same shape while the water flows through, a flame that maintains its form while consuming fuel and releasing exhaust. 330 billion cells dead today. Tomorrow, another 330 billion. Every day for your entire life, until the balance finally tips, until renewal can't keep pace with death, until the system fails and you die not cell by cell but all at once, systemically, the whole pattern collapsing when critical components can no longer be replaced. But until then, you persist, you endure, you continue being you through endless cycles of cellular death and rebirth, the ship of Theseus rebuilt plank by plank, never the same matter but always the same you, dying and being reborn, 330 billion cells at a time, every single day. The longest living organism on Earth is a clonal colony of aspen trees in Utah called Pando, estimated to be 80,000 years old. There's a forest in Utah that's older than human civilization, older than agriculture, older than writing, older than any of the monuments we think of as ancient. And it's not a forest of many trees. It's one organism. Pando, Latin for ice bread, is a clonal colony of quaking aspen trees in the Fish Lake National Forest. From the surface, it looks like a normal aspen grove, about 47,000 individual stems spread across 106 acres, each tree with its own trunk, branches, leaves, appearing separate and independent. But underground, they're all connected. All 47,000 stems share a single root system, massive and ancient, spreading through the soil, sending up new shoots continuously. The entire grove is genetically identical, all grown from one original tree, cloning itself through root suckers for tens of thousands of years. The above-ground stems are young, relatively. Individual trunks live about 130 years before dying, and being replaced by new shoots from the root system. So the forest you see is constantly regenerating, new stems growing while old ones die, the visible parts no more than a century old. But the root system, the organism itself, is estimated to be about 80,000 years old, maybe older. Dating is difficult because roots don't form annual rings the way trunks do, and radiocarbon dating has limitations for organisms still alive. But genetic analysis, growth rates, and comparison with other aspen clones suggest Pando has been alive for at least 80,000 years, possibly much longer. 80,000 years. That's before the last ice age, before humans left Africa, before Neanderthals went extinct, before cave paintings at Lascaux, before megalithic temples, before any of recorded history. Pando was alive when mammoths walked North America, when dire wolves and saber-toothed cats hunted across the continent, when glaciers covered much of the northern hemisphere and sea levels were 400 feet lower than today. And it's still alive, still growing, still sending up new shoots, expanding slowly across the landscape. A single organism that weighs approximately 6,000 tons, the heaviest known organism on Earth, covering 106 acres, surviving through climate changes and ice ages and everything that's happened since the late Pleistocene. How does it survive so long? Aspen clones have several advantages. The root system is protected underground, insulated from fire, sheltered from weather, hidden from herbivores. While the above-ground stems can be damaged or destroyed, the roots survive and send up new growth. The trees are also adapted to disturbance. Fire, which kills many trees, actually helps aspen by clearing competing vegetation and triggering new shoots from the roots. Aspen are pioneer species, quick to colonize disturbed areas, and Pando's strategy of spreading through root suckers rather than relying on seeds makes it resilient to conditions that would prevent seed germination. But Pando is struggling now. The clone hasn't expanded recently. New shoots are being eaten by deer and elk before they can mature. Overgrazing by these herbivores, populations artificially high due to elimination of predators like wolves, means young stems don't survive long enough to replace dying trunks. The root system is still alive, still trying to send up new growth. But if the above-ground stems continue dying without replacement, the clone could shrink, eventually losing its ability to photosynthesize, to produce energy to maintain the root system. It survived 80,000 years, but human activity in the last century, eliminating wolves, suppressing fire, allowing deer populations to explode, might succeed where ice ages and climate shifts failed. There are efforts to protect it, fencing to exclude deer, allowing some areas to regenerate, controlled burns to mimic natural fire regimes, recognition of Pando as a unique organism worthy of conservation. But it's unclear if these efforts will be enough. An organism that survived for 80,000 years is now vulnerable in ways it's never been before, threatened by ecological changes happening too quickly for it to adapt. Still, for now, it persists. The root system sprawls beneath the soil, ancient and vast, genetically identical across 106 acres, a single organism that remembers, if organisms can remember, a world we can only know through fossils and ice cores. Pando has seen the entire span of human culture. All of it, from the first migrations out of Africa to the present day, is contained within the lifespan of this single clonal aspen colony. It was alive when the first humans reached North America, crossing the Bering Land Bridge, or traveling along coastlines, spreading across a continent empty of human presence. It was alive during the Younger Dryas, the cold snap that interrupted warming at the end of the last ice age. It was alive when agriculture began in the Fertile Crescent, when pyramids rose in Egypt, when Rome fell, when Columbus sailed, when the Industrial Revolution transformed human society. All of human history is a recent development from Pando's perspective. If a tree could have perspective, we're newcomers, brief occupants of a world the tree has inhabited for 80 millennia. And it's just one organism, one individual, spread across a hillside, cloning itself continuously, replacing its above-ground parts while the underground self persists, ancient and slow, growing outward at a pace too gradual to notice in a human lifetime, but relentless over geological time. There are other old organisms, bristlecone pines over 5,000 years old, sea sponges possibly older than Pando, bacterial colonies that might have persisted for hundreds of thousands of years. Age is difficult to measure, especially for clonal organisms or those without clear growth rings. But Pando is among the oldest, certainly, and definitely the most massive, at 6,000 tons of biomass, all genetically identical, all connected, all technically one living thing. It's a reminder that individuals can persist far longer than we do, that an organism's strategy for survival, cloning, spreading, replacing damaged parts while maintaining a protected core, can enable lifespans that dwarf human experience. 80,000 years, and counting if we let it continue. If we protect it from the threats we've created, if we give it space to keep doing what it's done since the last ice age, growing, spreading, persisting, being. Pando, I spread, still spreading after 80,000 years, still here, still alive. The oldest living organism we know of, unless something older is hiding somewhere, undetected, equally patient, equally persistent. Waiting as Pando waits for whatever comes next. Sound cannot travel through space because there are no molecules to vibrate and carry the sound waves. Space is silent, completely, utterly, absolutely silent, not quiet, not the muffled stillness of a library or the hushed calm of falling snow. Silent in a way that has no equivalent on Earth, where air and water and solid ground carry vibrations constantly, where sound is almost unavoidable except in special isolation chambers designed to block it. In space, there is no sound, cannot be sound. The physics don't allow it. Sound is a mechanical wave, a vibration propagating through a medium by making molecules bump into their neighbors, which bump into their neighbors, passing the vibration along from source to destination. In air, sound makes air molecules oscillate back and forth in the direction of propagation, creating alternating regions of compression and rarefaction that we perceive as sound when they reach our ears. But space is vacuum. Near vacuum, anyway. There are particles out there, atoms of hydrogen, cosmic dust, ionized plasma, but they're incredibly sparse. In the interstellar medium, there might be 1 atom per cubic centimeter. In interplanetary space within the solar system, maybe 10 atoms per cubic centimeter in some regions, fewer in others. On Earth, air at sea level contains about 10-19 molecules per cubic centimeter. 10 billion molecules in a thimbleful of air. Space has maybe 10 atoms in that same volume. The density is so low that molecules almost never collide, almost never interact, can't transfer vibrations to neighbors because there are no neighbors close enough to bump into, so sound can't propagate. A vibration in space just stays local. It doesn't spread as a wave because there's no medium to carry it. This means all those dramatic explosions in space movies, the roar of engines, the boom of ships exploding, the whoosh of fighters zipping past, are all fictional, artistic license, dramatic effect. In reality, all of it would happen in complete silence. The Death Star exploding in Star Wars, silent. A massive, catastrophic detonation that would be deafening on Earth, but in space, no sound at all. You'd see the light, the flash, the expanding debris, the radiation, but you wouldn't hear anything. A rocket engine firing? Silent from outside. The astronauts inside the rocket would hear it through conduction. Vibrations traveling through the rocket's structure to the air inside the cabin, but outside, in vacuum, nothing. Even the Apollo astronauts, walking on the moon, couldn't hear each other except through radios. The moon has no atmosphere, so sound can't travel between them. They could see each other, wave, gesture, but any sound they made, voice, footsteps, tools clanging, stayed trapped in their suits or conducted through the ground to their own boots, never reaching the other person as airborne sound. There's something eerie about that. Space seems violent, stars exploding, black holes consuming matter, galaxies colliding, cosmic rays streaming at near light speed. And all of it happens in silence, no soundtrack, no audio accompaniment to the visual chaos. The sun is constantly roaring with nuclear fusion, with flares and coronal mass ejections, and convection currents moving plasma at thousands of kilometers per hour. If you could somehow survive the heat and radiation and stand next to the sun, you still wouldn't hear it. The fusion, the magnetic storms, the massive eruptions throwing billions of tons of plasma into space, all silent because there's no air to carry the sound. Jupiter's Great Red Spot, a storm larger than Earth that's been raging for centuries, rotates in complete silence. Lightning flashes through its clouds, winds scream at hundreds of miles per hour, but there's no one to hear it and no medium to carry the sound anyway. Even on Earth, at high altitudes where the atmosphere becomes very thin, sound changes. At 100,000 feet, the air is so thin that sound propagates poorly. You'd need to shout to be heard from a few feet away. Higher still, approaching the Kármán line at 100 kilometers where space officially begins, sound essentially stops working. There is one exception, sort of. In the densest parts of intergalactic space, where gas clouds are thick enough, very low-frequency vibrations can propagate. Not sound as we'd recognize it, frequencies far below what human ears can detect, with wavelengths measured in light years, oscillating once per million years or slower. These are pressure waves in galaxy clusters, vibrations moving through hot ionized gas, detectable by X-ray telescopes that can see temperature variations corresponding to compressions and rarefactions. Scientists have recorded these vibrations, translated them into audible frequencies by speeding them up enormously, creating sounds that represent what a galaxy cluster's oscillations would sound like if you could hear them and if they vibrated a trillion times faster. It's technically sound, sort of, maybe, if you define sound very broadly as any mechanical wave in a medium. But it's not sound as we experience it, not vibrations we could hear, not frequencies our ears could detect, not timescales we could perceive. For practical purposes, space is silent. Astronauts on the ISS sometimes report hearing sounds, creaks and groans from the station's structure, expanding and contracting with temperature changes as it moves in and out of sunlight, humming from equipment, the whoosh of air circulation. But these are all sounds inside the station, transmitted through air in the pressurized cabin or through the structure itself. Outside, in the vacuum surrounding the station, there's nothing. Radio transmissions work. Electromagnetic waves that don't need a medium, that propagate through vacuum just fine. Light works. Radiation works. But sound, specifically, does not. This is why spacesuits have radios, why ships communicate electronically, why you need instruments to detect vibrations if you're trying to measure oscillations in spacecraft or satellites, because you can't just listen. Sound is local to mediums, air, water, solid materials. Where there's matter dense enough for molecules to bump into each other at reasonable frequencies, sound can propagate. Where there isn't, it can't. Space mostly isn't. So space is silent, will always be silent, can only be silent given the physics of vacuum and the nature of mechanical waves. No sound has ever crossed the void between stars. No vibration has propagated through interstellar space as sound. It's all light, radiation, cosmic rays, magnetic fields, forces and particles that don't need air. But sound? Sound requires matter, requires density, requires molecules close enough to jostle each other. Space has none of that. So all those dramatic explosions happen silently. All those massive cosmic events unfold without soundtrack. The universe is full of light and violence and beauty and drama, and all of it happens in complete, unbroken, eternal silence, which maybe makes it more profound in a way. The violence without noise, the spectacle without fanfare, just light and motion and change unfolding in the deepest quiet imaginable. The human nose can detect over 1 trillion different scents, far more than previously thought. For a long time, scientists believed humans could distinguish about 10,000 different odors. That was the accepted number, repeated in textbooks, cited in papers, taught to students. 10,000 seemed like a lot, more than enough to navigate the world, identify foods, detect dangers, appreciate the subtle variations in wine or coffee or perfume. But it was wrong, dramatically wrong. In 2014, researchers at Rockefeller University tested human olfactory abilities more rigorously. Instead of using familiar scents like vanilla or roses, they created novel mixtures of odor molecules, combinations subjects had never smelled before, that had no names, no associations, no learned responses. They mixed these molecules in different proportions, creating blends that were chemically similar but perceptibly different if your nose was sensitive enough. Then they tested whether subjects could distinguish between them. The results were surprising. Humans could distinguish far more combinations than expected. Extrapolating from their data, the researchers estimated that the human nose can detect over 1 trillion different scents. 1 trillion. Not 10,000. 1 trillion. That's 100 million times more than the old estimate. It's more scents than there are colors we can see, more than sounds we can distinguish, more than any other sensory modality we possess. Your nose, which you might think of as a secondary sense compared to vision, is actually extraordinarily sophisticated, capable of discriminating between chemical mixtures with astonishing precision. How does this work? You have about 400 different types of olfactory receptors in your nose, protein molecules embedded in the membranes of olfactory neurons in the nasal epithelium. Each receptor type responds to certain molecular features, shapes, sizes, functional groups, chemical properties. When you breathe in, odor molecules dissolve in the mucus lining your nasal cavity and bind to these receptors. Each molecule might activate several receptor types to different degrees, creating a pattern of activation, a signature that your brain interprets as a specific smell. The trillion scent estimate comes from combinatorics. With 400 receptor types, each capable of responding at different intensities, the number of possible patterns is astronomically large. Most odors are mixtures, hundreds of different molecules, each activating multiple receptors, creating complex patterns that your brain can learn to recognize and distinguish. This is why you can tell the difference between Granny Smith and Red Delicious apples, even though both smell like apple. The specific mixture of molecules is slightly different, creating different activation patterns, which your brain perceives as distinct scents. It's why wine experts can identify not just grape varieties, but regions, vintages, production methods. Each variable changes the chemical composition slightly, creating a different olfactory signature, a different pattern recognizable to a trained nose. Your olfactory system is also surprisingly fast. Odor information reaches your brain in milliseconds, faster than visual processing for complex scenes. You can detect some odors at concentrations as low as a few parts per trillion, individual molecules among trillions of air molecules, low enough that you're detecting perhaps a few hundred molecules total. Some odors you're incredibly sensitive to. Mercaptans, the sulfur compounds in natural gas and skunk spray, can be detected at less than 1 part per billion. Geosmin, the earthy smell of rain on dry soil, at about 5 parts per trillion. These are concentrations so low that your nose outperforms many analytical instruments designed to detect trace chemicals. This sensitivity served our ancestors well, detecting rotten food before tasting it, identifying which plants are edible, recognizing the scent of predators or fire, finding mates through pheromones and body odor. All of this depended on olfaction, on being able to distinguish between chemically similar but functionally different scents. We think of ourselves as visual creatures, and we are. Our visual cortex is huge. Our acuity is excellent compared to many animals, but our noses are better than we give them credit for. We just don't train them the way we train our eyes, don't attend to smells as consciously as we attend to sights, don't have vocabulary for describing odors as rich as our vocabulary for colors or shapes. But the hardware is there. The sensitivity exists. 1 trillion distinguishable scents, all accessible to your nose right now if you pay attention. Every breath you take carries information, molecules from your environment, from people around you, from distant sources, all of it dissolving in the mucus in your nose, binding to receptors, creating patterns that your brain analyzes and interprets. You're smelling constantly, even when you're not aware of it. Your brain filters most of it out, focuses attention on novel or important scents, lets the familiar background fade into unconsciousness. But the information is there, processed, available if you choose to notice. This is why scent is so strongly tied to memory. The olfactory bulb, where scent information first arrives in the brain, connects directly to the hippocampus and amygdala, regions involved in memory and emotion. Scent bypasses the thalamus, the relay station that other senses go through, giving it a more direct route to emotional and memory centers. This is why a particular smell can trigger vivid memories, transport you instantly to childhood or a specific moment years ago. The neural pathways are short, direct, emotionally charged. 1 trillion scents. Most of them you'll never encounter, never learn to recognize, never have occasion to distinguish. But the capacity is there, built into your nose, ready to detect chemical variations at resolutions finer than you'd ever consciously notice. Your nose is a precision chemical detector, capable of analyzing mixtures, distinguishing components, identifying sources, all in real time as you breathe. More sensitive than you thought, more powerful than vision in some ways, more sophisticated than almost any technology we've built for chemical analysis. 1 trillion scents. All of them accessible to you right now if you breathe deeply and pay attention. The world is full of odors, subtle and varied, and your nose can detect nearly all of them. You just have to notice. Quantum entanglement allows two particles to remain connected across any distance, so that measuring one instantly affects the other. When two particles become entangled through interactions, through their creation in certain processes, through various methods physicists have developed, they form a connected system, not connected by any force we know of, not linked by strings or fields or anything we can detect, but connected nonetheless through their quantum states. Measure one particle, and you instantly know something about the other. Change one, and the other changes correspondingly. No matter how far apart they are, no matter if they're separated by inches or light years, the distance doesn't matter. The connection persists. Einstein hated this. He called it spooky action at a distance, and argued it couldn't be real, that there must be hidden variables, some underlying mechanism we weren't seeing that explained the correlations without requiring instantaneous effects across space. He was wrong. Experiments have confirmed over and over that entanglement is real. The correlations exist. The connection persists across arbitrary distances, and there are no hidden variables. Quantum mechanics really does describe reality this way, strange as it seems. Here's a simplified example. You create two entangled photons with correlated polarizations. Send them in opposite directions, miles or light years apart. Before you measure either one, neither has a definite polarization. Both exist in superposition, simultaneously all possible polarizations at once. But the moment you measure one photon's polarization, forcing it to choose vertical or horizontal or some angle, the other photon's polarization becomes determined instantly. If you measured vertical on one, the other will measure horizontal when you check it. If you measured diagonal on one, the other is the opposite diagonal. The correlation is perfect, instantaneous, independent of distance. This seems to violate relativity. Information appears to travel faster than light. You measure one particle and instantly the other knows what happened. But it doesn't actually allow faster than light communication. You can't control what result you get when you measure the first particle. It's random, probabilistic, fundamentally unpredictable. So you can't encode a message by choosing outcomes. The second observer, measuring their particle, just sees random results unless they compare notes with you later. Only then, traveling at light speed or slower, do they discover that your measurements were correlated. The correlation is real, but it doesn't transmit information faster than light, doesn't violate causality. It's like magic with very specific limitations. The connection exists, but you can't use it to communicate. You can't send messages, can't transmit data, can't coordinate actions faster than light. What you can do is verify that the connection is real, that measuring one particle affects the other, instantly, regardless of separation. And this has been tested exhaustively. Experiments have entangled photons and separated them by kilometers, then measured them at precisely synchronized times, confirming that the correlations exist even when the measurements happen too quickly for any light-speed signal to pass between them. Other experiments have closed various loopholes, eliminated possible alternative explanations, confirmed that yes, entanglement is real, it works the way quantum mechanics says it does, and reality is genuinely this strange. It's being used now. Quantum cryptography relies on entanglement to create perfectly secure communication channels. Any eavesdropping disturbs the entangled state, revealing the intrusion. Quantum computers use entanglement to create qubits that are correlated in ways classical bits can't be, enabling certain calculations that would be impossible otherwise. But at a fundamental level, entanglement remains deeply mysterious. What is the connection? How does measuring one particle affect the other? Is there some underlying mechanism, or is this just how reality works at the quantum level, without deeper explanation? We don't know. The math works. The predictions match experiments. But what it means, what entanglement tells us about the nature of reality, about space and time and causality, remains debated. Some interpretations say the particles don't have definite properties until measured, and measurement on one forces both to choose consistent values. Others say the universe splits into branches, and you measure one outcome in your branch, while another version of you measures a different outcome in another branch. Still others invoke non-local hidden variables, or pilot waves, or various other exotic explanations. All of them match the data. None can be definitively ruled out or confirmed. What we know is the phenomenon is real. Two particles entangled remain connected regardless of distance. Measure one and the other is affected instantly, no matter how far apart they are. Einstein called it spooky. He was right about that much. It is spooky. It violates our intuitions about locality, about objects having independent existence, about the universe being made of separate parts that only interact through local contact or field influences. Entanglement says particles can be non-local, that separation in space doesn't always mean separation in state, that two things can be one thing in a quantum sense, spread across space, connected in ways we can measure but not fully understand. It's as if the universe doesn't care about distance at the quantum level, as if space itself is less fundamental than we thought, just a classical approximation that breaks down when you look closely at the quantum foundations of reality. Two particles, any distance, instant correlation, no mechanism, no signal, no explanation that makes intuitive sense, just entanglement, one of the strangest confirmed features of reality, happening continuously in labs and experiments and quantum computers, defying explanation while enabling technologies we're only beginning to explore. Spooky action at a distance, real, measurable, still mysterious after a century of quantum mechanics. The universe is stranger than it appears. Entanglement proves it. The Amazon rainforest produces approximately 20% of the world's oxygen, but it also consumes nearly all of it through respiration and decomposition. There's a myth about the Amazon rainforest that feels right, that sounds true, that gets repeated so often it's become accepted fact. The Amazon is the lungs of the earth, producing 20% of the world's oxygen, essential for global breathing, irreplaceable as an oxygen source. The first part is true. The Amazon does produce about 20% of global oxygen through photosynthesis, trees and plants converting carbon dioxide and water into sugars and oxygen, using sunlight as energy. Billions of tons of oxygen released annually into the atmosphere. But here's what's left out. The Amazon also consumes nearly all of that oxygen. Plants respire. At night, when there's no sunlight for photosynthesis, they consume oxygen and release carbon dioxide, just like animals. They're burning sugars to produce energy, using oxygen to do it, releasing CO2 as waste. And during the day, while they're producing oxygen through photosynthesis, they're simultaneously consuming some of it through respiration. The net production is positive. More oxygen created than consumed, but not by as much as you might think. Then there's decomposition. Dead leaves, fallen branches, trees that die and collapse, all of it covered with fungi, bacteria, insects, decomposers that break down organic matter and return nutrients to the soil. And decomposition consumes oxygen, lots of oxygen, the microbes respiring, the chemical reactions oxidizing organic compounds, all of it drawing oxygen from the air. Add it all up. Photosynthesis creating oxygen, plant respiration consuming it, decomposition consuming more, and the net oxygen contribution from the Amazon is close to zero. Nearly all the oxygen produced gets consumed within the forest ecosystem. This doesn't mean the Amazon isn't important. It stores enormous amounts of carbon in its biomass, trees, soil, organic matter. It regulates regional climate, generates rainfall through transpiration, maintains biodiversity, provides habitat for millions of species. But as an oxygen source for the planet, minimal. So where does our oxygen come from? Mostly the ocean. Phytoplankton, microscopic photosynthetic organisms floating in sunlit surface waters, produce about 50 to 80% of Earth's oxygen. They're tiny, often single-celled, but they're everywhere in vast numbers, photosynthesizing continuously, releasing oxygen that doesn't get consumed locally, because the open ocean doesn't have the same dense decomposition ecosystem that terrestrial forests do. Some of that oxygen dissolves in seawater, supporting marine life, but much of it escapes into the atmosphere, accumulating over geological time, building up the 21% oxygen concentration we breathe. The rest comes from various terrestrial ecosystems, grasslands, tundra, boreal forests, and importantly, from the past. The oxygen in the atmosphere is mostly legacy oxygen, produced over hundreds of millions of years and accumulated because not all of it was consumed. Organic matter gets buried before decomposing, turned into coal, oil, peat, sediment, locking away carbon and leaving oxygen behind. This is how Earth's atmosphere became oxygen-rich in the first place. Early photosynthetic organisms, starting about 2.5 billion years ago, began producing oxygen faster than it was consumed by chemical reactions and respiration. oxygen accumulated, eventually reaching levels high enough to support aerobic life, to create ozone layers, to change the planet fundamentally. And it's still accumulating, slowly, as organic carbon gets buried and oxygen remains in the atmosphere. Though human fossil fuel burning reverses this, we're taking buried carbon and reoxidizing it, consuming oxygen to burn coal and oil and gas, releasing CO2 and depleting atmospheric oxygen slightly. But the oxygen content is so large, about 1 billion tons in the atmosphere, that even our massive consumption barely affects it. We could burn all known fossil fuel reserves, and oxygen would drop by less than 1%. It's not oxygen depletion we need to worry about. It's carbon dioxide accumulation, climate change, ecosystem disruption. Still, the myth persists. The Amazon is Earth's lungs, producing our oxygen, essential for breathing. It's emotionally true, maybe. The Amazon feels vital, irreplaceable, worth protecting. And it is all of those things, just not because of oxygen. Lose the Amazon and oxygen levels wouldn't change noticeably. But lose the Amazon and you lose carbon storage. Billions of tons of CO2 released as trees burn or rot. You lose rainfall generation. The Amazon creates its own weather, recycling moisture through transpiration, generating rain that supports agriculture downwind. You lose biodiversity, millions of species, many undiscovered, endemic to specific regions, unable to survive elsewhere. You lose an entire ecosystem, a functioning whole, a piece of planetary machinery that's taken millions of years to develop and can't be recreated once destroyed. So the Amazon is worth protecting, desperately worth it, just not for the reason most commonly cited, not for oxygen. The oceans do that, and they do it better, producing more net oxygen, distributing it globally through atmospheric mixing, keeping us breathing through phytoplankton that most people never see and rarely think about. The Amazon matters for carbon, for climate, for water, for species, for indigenous peoples, for countless reasons that make it irreplaceable. But oxygen? The Amazon produces a lot and consumes nearly all of it, balanced, cycling internally, contributing little to the global oxygen budget. The lungs of the earth are actually the oceans, phytoplankton, microscopic and vast, invisible but essential, producing the oxygen we breathe while the Amazon quietly cycles carbon and water and maintains one of the most biodiverse ecosystems on the planet. Both are worth protecting. Both are essential. Both are threatened. But understanding what they actually do versus what we think they do matters for knowing how to protect them, for prioritizing conservation, for recognizing where the real dangers lie. The Amazon isn't our oxygen source, but it's still irreplaceable, and that's enough. Time is not constant throughout the universe. It flows at different rates depending on gravity and velocity. Time is personal, not metaphorically, not in the sense that experience is subjective, but literally. The rate at which time passes depends on where you are, how fast you're moving, what gravitational field you're in. Your time and my time are different if we're in different circumstances. Not our perception of time, but actual time, the rate at which physical processes occur, clocks tick, particles decay, aging happens. This is relativity, not just Einstein's theory, but observed reality, confirmed by countless experiments, built into technologies we use daily. We've talked about gravitational time dilation, time moving slower in stronger gravity. But there's also velocity-based time dilation from special relativity, equally strange, and equally real. Move faster, and time slows down for you relative to someone stationary. Not because of any mechanical effect, not because motion physically slows clocks, but because time itself passes more slowly for moving objects. This effect is tiny at everyday speeds. Drive a car at 60 miles per hour, and your clock runs slow by about a billionth of a second per hour compared to someone standing still. You'd never notice. The effect is negligible. But at speeds approaching light speed, it becomes dramatic. An astronaut traveling at 90% of light speed experiences time at about half the rate of someone on Earth. What feels like 1 year to the astronaut is 2 years for Earth. Travel for 10 years at that speed. 10 years by the astronaut's clock, aging 10 years, experiencing 10 years of life, and return to Earth to find 20 years have passed. Friends have aged 20 years. Children have grown up. The astronaut is younger than siblings who were younger when they left. This is the twin paradox, not actually a paradox, but a real consequence of relativity. If one twin stays on Earth and the other travels at high speed and returns, they'll have aged differently. The traveling twin will be younger, not because of any biological effect of space travel, but because time literally passed more slowly for them. At light speed, which is impossible for anything with mass, but hypothetically, time would stop completely from the perspective of the traveler. Photons, moving at light speed, experience no time. From a photon's perspective, if it could have one, it's created and absorbed in the same instant, regardless of how far it travels from our perspective. This seems impossible. How can time be different for different observers? Isn't time universal, absolute, the same for everyone? No, that's Newtonian physics, and it's wrong. Newton thought time was absolute, flowing uniformly everywhere, an external framework in which events occur. Einstein showed this was false. Time is relative, flexible, dependent on reference frame. There's no universal now that everyone can agree on. Simultaneity is relative. Events that are simultaneous in one reference frame occur at different times, in another reference frame, moving relative to the first. This breaks our intuition completely. We think of time as a universal backdrop, everyone experiencing the same moment, the same flow, the same rate. But that's only approximately true when speeds are slow and gravity is weak. At high speeds or in strong gravity, the approximation breaks down. And we've tested this. Atomic clocks flown on airplanes show time dilation effects matching predictions. GPS satellites experience both gravitational time dilation, time runs faster in orbit where gravity is weaker, and velocity-based time dilation. Time runs slower because they're moving fast relative to Earth's surface. Both effects are significant, and GPS wouldn't work without corrections for both. Particle accelerators see time dilation constantly. Muons created in high-energy collisions have very short lifetimes, about 2.2 microseconds before decaying. But when they're moving at 99.9% of light speed, their lifetimes appear much longer from our reference frame. They travel farther than they should before decaying, because time is passing more slowly for them. From the muon's perspective, it lives exactly 2.2 microseconds. From our perspective, moving relative to the muon, it lives much longer. Both perspectives are correct. Both are valid. There's no absolute frame that determines which one is really right. Time is relative, different for different observers, dependent on motion and gravity, flexible in ways we don't experience, but that are absolutely real at extremes. This means there's no universal clock, no absolute time coordinating the universe. Every observer has their own time, their own flow, their own rate, and those rates disagree correctly because there's no single right answer. If you could travel at high speeds, you could effectively travel into the future. Not backwards. Causality is preserved. You can't go back, but forward. Travel at near light speed for what feels like a year, return to Earth, and decades or centuries might have passed. You've jumped forward in time, not by any mechanism beyond simply moving fast and letting time dilation do its work. This is how relativity allows something like time travel, forward only, one way, at different rates, depending on your velocity and path. It's not science fiction, it's physics. Impractical with current technology, but possible in principle. And at cosmic scales, time differences become extreme. Near a black hole's event horizon, time slows so much that you could watch the entire future of the universe unfold in what feels like minutes to you. The universe aging billions of years while you experience a brief fall toward the singularity, or orbiting close to a massive object at high speed. Time for you passes slowly while the rest of the universe ages quickly. Return from that orbit after what feels like a few years, and millennia might have passed elsewhere. Time is not constant, not universal, not the same for everyone. It flows differently depending on where you are, how you're moving, what gravity you're experiencing. Your time is yours, mine is mine, and they don't have to agree, don't have to match, don't have to flow at the same rate. Because time is relative, always has been, always will be, even if it feels absolute from where you're standing. And so we arrive at the end, and there are millions more facts we didn't cover, millions more wonders waiting to be discovered. The universe is inexhaustible. You could spend multiple lifetimes learning and barely scratch the surface of everything that's been discovered, much less everything there is to know. But for tonight, these are enough. Let them drift through your mind as you fall asleep. Let them become dreams if they want. Let them go if that's easier. The universe will still be here tomorrow, still strange, still beautiful, still full of facts that make you feel small and large at the same time. Small in the face of cosmic vastness, large in your capacity to understand it. Thank you for listening, for spending this time here, in the dark or near dark, letting these words carry you towards sleep. I hope you rest well. I hope your dreams are gentle. I hope you wake refreshed, ready for whatever tomorrow brings. And maybe, when you look up at the sky, you'll remember. You're made of star stuff, looking back at stars, briefly conscious, briefly aware, briefly capable of understanding that the universe exists and that you're part of it. Good night.